So welcome students to one more session of your grade 11 CBSE. So the other day I've kept one community tab. I've asked I asked you all to cast votes based on your opinion what to complete next after periodicity. So I think periodicity was a complete revision from JD Lee, Pradeep, comprehensive, NCERT, all books together, and I've combined and I've done the periodicity chapter. Done. So now I'm going to start based on the votes which you have casted. I'm going to start the next chapter, organic chemistry. So I've asked you whether should I start states of matter, should I start should I start equilibrium, should I start redox reactions, organic chemistry. Almost 80% votes they've casted for organic chemistry. So now I'll be starting with the next important chapter, or that is hydrocarbons of your organic chemistry. Ma'am, what happened to GOC, general organic chemistry? You would have got a doubt. GOC is already done and kept in the playlist. Please go and watch the videos. Further, if you still have doubts in GOC, I'll try to do that. So in organic chemistry chapter, what is the weightage of organic chemistry? It's almost 12 marks in your grade 11, right? And very important chapter, the lot of reasoning questions. Reasoning questions means organic reasoning questions. So let's see the index, what is there in this chapter, right? So when I have to come back to hydrocarbons, this is the only organic chemistry chapter. You also have GOC, as I said. So let's see what topics are we going to learn in this. So in hydrocarbons, I'll be teaching you about the classification of hydrocarbons. What are we going to learn in that? We're going to learn what is aliphatic hydrocarbons, aromatic hydrocarbons, that is alicyclic, cyclic, and everything. I'll be teaching the classification. Again, they are divided into alkenes, alkenes, alkynes. Aromatic are again divided into cycloalkenes, cycloalkenes, cycloalkanes, like that. Classification part, I'll be dealing it clearly for you. Done. After that, after the classification, once we know what are aliphatic hydrocarbons, which is a classification of alkanes, alkenes, and alkynes, I'll be teaching you the different subparts of this. In alkenes, alkenes, and alkynes, I'll be teaching about nomenclature, right? So for nomenclature, I'm going to do the worksheet part. I picked up a lot of questions in the form of worksheet. I'll be making you do the worksheet also, where you'll be learning how to... Unacademy, the biggest online platform, learning platform in India. Let's crack it. I'm Vani Potepalli, the verified educator for grade 12 students, CBSE, ICSE, as well as state board students are with me. The upcoming classes which I'll be going to take are aldehydes, ketones, and carboxylic acids. Along with that, solutions chapter would be done, and a revision series on board examination and how to crack board 2021. I'm going to give you a clear analysis of the revision series. And in the special classes, I would be taking 3 sessions continuously. That is how to learn chemistry in Telugu. It will be on the respective dates. And I will also be taking a special class where you can plan it, and you can just meet me on December 21st and 22nd. I'll be discussing what is the revision series, what is the revision strategy for board exam 2021. These are the Unacademy Plus subscription features, where you have daily practice sessions, mock tests which are going on, live quizzes which will be going on, subjective test series coming soon. Join us. Unacademy iconic subscription features include personal mentors. You have live doubt clearing sessions. Weekly reports will be sent to the parents. Parent Connect, where the report will be sent to the parent and the educators are in contact with the parents too. A study planner is perfectly planned, and all benefits of Plus also will come under iconic subscription. This is the class 11 subscription. Don't forget to use my referral code, that is Vani10 or Vani Life. This is the subscription rates you can go through. Grade 11 iconic subscription prices, that is again Vani10, Vani Life. Note my referral code. Next comes your grade 12 subscription, where prices are given. You have an option of 3 months and 6 months. Please try to use the code Vani10 or Vani Life to get the 10% discount. Then comes the grade 12 iconic subscription, 6 months, very less amount. So you can take that particular thing, use my referral code Vani10 on Vani. Unacademy introduces Career Quest, Break the Norm. It's a free summit with power pack sessions which will help learners to explore exciting career options with the guest speakers, that is Bhimani. Gautam Bhimani would be one of the featuring guests. Then comes Kunal Vijaykar, Philip Ross, and many more. This event is on 20th December. Event time would be 10 AM to 6 PM. Where is this happening? It's happening at Unacademy app and website. So download the app immediately, students.
This particular career quest and a plan to the successful roadmap for your future would be taken up. Note the date, that is on 20th December. Time would be 10 a.m. to 6 p.m. and immediately download the app. And most important thing, remember, if you want to enjoy all the free courses which I am going to conduct, you can use this referral code VANI10 or VANILIVE to unlock that particular series, and you can enjoy the free special classes which are conducted with quality, quantity, and most important, it's going to give you a clear analysis of how to prepare for the upcoming board examinations. So don't forget, students, VANI10 or VANILIVE is my referral code. Name the compound. You'll be learning what is the criteria for naming the compound. You'll also be learning the same for alkanes, alkenes as well as alkynes. Done. After that, I'll be teaching some important topic in alkanes, that is conformations, right? In that conformations, you'll be studying that conformations only in alkanes. That is two types: a Sawhorse conformation as well as Newman's conformation. That is Newman's projection formula. I'll be dealing that. After that, I'll be going into a topic called isomerism. That's the same for alkenes, alkenes as well as alkynes. We'll be learning about position isomerism. I'll be teaching about geometrical isomerism. I'll be teaching you in that geometrical cis and trans isomerism, all the different types. I'll again be doing a worksheet on that. Done. After that, I'll be going into the structure of alkanes, alkenes and alkynes. I'll be taking methane example, I'll be taking ethene example, I'll be taking acetylene example, and I'll be showing you what is the hybridization in that, bond angle in that, bond length in that. All the concepts will be dealt in. And after that, after teaching you the structure, I'll be going into a topic called physical properties. I'll be teaching what is the solubility factor, melting point factor, boiling point factor, density. All these concepts will come under physical properties. After I give you an idea of physical properties, I'll go into a concept called chemical properties. Right? In chemical properties, very important. Basically, in organic chemistry, why chemical properties are very important? Because every reaction, but suppose if I take a chemical property of pyrolysis, that has a lot of depth in that. If I speak about a property of oxidation with KMnO4, there is a lot of depth. It will explain you what conditions is it undergoing oxidation, what are the temperature conditions, what are the reagents you should do. From that reactant, where can I convert it into product? So different concepts will be covered under chemical properties. I'll be listing out the chemical properties which we are going to study for alkanes, alkenes and alkynes also. So all these topics are there in the chapter. Please, my request is keep noting and keep following on a daily basis. Done. After that, I'll be teaching a topic called aromatic compounds. So aromatic compounds, here in grade 11, you have a compound called benzene which you're going to study. So under benzene, I'll be teaching you the preparations of benzene from alkynes. We'll be learning the preparations of benzene from acids, that is aromatic acids, that is benzoic acid. I'll be teaching from phenol, say 6H5OH. I'll be teaching by a reaction called Friedel-Crafts reaction. I'll be teaching the preparation of benzene from all these. After preparation, I'll be teaching you a concept called structure of benzene. I'll be taking the orbital concept, resonance concept, all these, and I'll be giving you a clear idea of structure of benzene. After that, I'll be gradually taking into a concept called chemical properties. Very important chemical properties. That is, in chemical properties, it's going to show, means the type of property which benzene shows is ESR. ESR means electrophilic substitution reactions. So after electrophilic substitution reactions, again I have parts in that. I'll be dealing one after the other very slowly, no problem. We'll get all the 12 marks will be yours. Next will be addition reactions. I'll be teaching how it's going to add to different reactants. HCl, benzylic, HX, all different HOCl, all the things I'll be showing you how to add around benzene. Then I'll be teaching you orthodirecting, meta-directing, everything I'll be teaching you slowly. Done. After that, I'll be teaching you with oxidation reaction of benzene, where you'll be taking KMnO4 and you'll show your oxidizing agent. I'll be picking up KMnO4. I'll be showing how does it add, what is oxidation, what is controlled oxidation, what is ozonolysis here also. Everything I'll be dealing. After oxidation, I'll be going to the last topic called carcinogenicity and toxicity. So we'll be doing what are the carcinogenic or poisonous compounds, what are the effects of those, what are the toxic effects in our body. So this is your whole chapter, students. Very important. From now I'm telling, as I've covered periodicity, gradually I've done one after the other like that. Organic chemistry also will be done. Please maintain a separate notebook.
And most of the students, those who have joined newly into my channel, have been asking me, ma'am, to complete organic of grade 12. I have completed organic. It was a long journey. 12th is completely done and kept in the playlist. All the chapters are done and they're serial wise, order wise, one chapter after the other. It's kept in the playlist. Please check that. So I'll meet you again. Now this is the index for your hydrocarbons chapter. I'll meet you immediately after this next topic, that is what are the different chemical properties you should remember in alkenes, alkenes and alkynes. Then we will know what are the chemical properties you should remember in benzene also. Right. Now we have seen the main index, isn't it? Now let's see what are the different preparations we are going to learn in alkenes, alkenes and alkynes. Right. So when it comes to your alkenes, I have divided the page into 3. All the 3 preparations are dealt here. Let's see that. So here I am going to prepare alkanes from hydrocarbons. This is your hydrocarbon, isn't it? Okay, not hydrocarbon, alkyl halide I have to say. So RX is alkyl halide. I'll be showing from where are we getting alkyl halide from your this one. I'll be showing from the preparation from the alkane. We'll gradually go slowly into the concept because alkyl halide is a concept which is taught in grade 12. Okay, no problem. So I'll be preparing alkanes from alkyl halides by a reaction called Woods reaction. From Woods reaction, I'll also be teaching how are we going to do the reduction of halides. So I'll be taking out electronegative element, I'll be preparing alkanes, and I'll also be using Grignard's reagent, an organometallic compound which will be introduced in grade 11, and you will be learning a lot of reactions in grade 12 also. Right, so these are the reactions from alkyl halide. And then I'm going to prepare alkanes from unsaturated hydrocarbons also, right? So I'll be taking what are unsaturated, double bond and triple bond, isn't it? I'll be preparing alkanes from those 2 also. Done. From there I'll be going into the preparation of alkanes from acids. So here we have 2 types of reactions. One is soda lime decarboxylation reaction as well as electrolytic decarboxylation reaction. I'll be showing you what are the anodic reactions and cathodic reactions also here. Then after that I'll be teaching you how to prepare alkanes by reduction of fatty acids with HI. I'll be showing how is the iodine gas evolved, what are the products when we take the fatty acid and react it with HI, hydroiodic acid. Done. When I have to prepare alkenes, we are going to prepare alkenes again from alkyl halides. R stands for alkyl, X stands for halide. So a derivative of an alkane where we have taken out one hydrogen and replaced by an halogen. Then I'll be teaching you the preparation of alkenes from vicinal dihalides. So there are 2, one is vicinal and gem. So I'll be preparing from vicinal dihalides. I'll show you what is vicinal and gem when I do the reaction also. Then I'll be preparing alkenes from alcohols, from alkynes and a Kolb's electrolysis method. Very, very important reaction of alkenes. Then I'll be teaching you the preparation of alkynes by a method called dehydrohalogenation of dihalides. That means I'll be taking out, D means taking out, hydro means hydrogen and halogen also at once. Then I'll be teaching you reactions. These are very important specific reactions which we'll be doing with calcium carbide and water, carbon and water, as well as CHCl3 and silver. I'll be teaching that reaction. I'll be showing the mechanism also in that wherever it is required. Then I'll be preparing alkynes from ethynes also. Last but not the least, again electrolysis. Here it is Kolb's electrolysis method. Here we are going to learn electrolysis of potassium salts. That is potassium salts of fumaric acid. So that fumaric acid will be taking. I'll be showing anodic reaction as well as cathodic reaction. So these are the preparations of alkanes, alkenes and alkynes. Now we'll wind up the index topic by I'll show you the chemical properties. What are we going to study for alkanes, chemical properties for alkenes as well as chemical properties for alkynes. Last but not the least, chemical properties of benzene also. So what did we learn? We said chemical properties include electrophilic ESR reactions, addition reactions, oxidation reactions, isn't it? Yes, let's come back and finish off with the chemical property index and then start with the chapter. Right. So after preparations, now we'll come back to the next topic, that is chemical properties. The chemical properties of alkenes. What are the different things which we are going to learn in chemical properties? Let's see. So in alkenes, I'll be teaching about a halogenation reaction where we'll be adding halogen. Like I'll be showing that free radical substitution reactions also. We'll be adding halogen or a halogens, addition of fluorine, chlorine, bromine, iodine. But here I'll be showing the addition of chlorine every time, and we'll write the name of the products also. Then I'll be teaching you the process of combustion with alkenes. So basically the products formed are carbon dioxide and water. So what is combustion? Heating in the presence of oxygen. That is combusting, right? Just like your forest where they catch fire, isn't it? So that is combusting in the presence of oxygen. That means burning in the presence of oxygen. I'll be showing that reaction. After that, I'll be teaching you a reaction called controlled oxidation. There is oxidation, controlled oxidation also. So I'll be giving you the temperature conditions where under controlled conditions you are adding, or in the presence of an oxidizing agent you are showing the addition of oxygen. Then I'll be showing you isomerism also. We'll be learning the different products of isomers, that means different isomeric compounds formed. Then I'll be teaching reaction with steam also, right? General formula also I'll be teaching in that. After that, I'll be finishing off the chemical properties of alkenes by completing or teaching you crackling or pyrolysis process, breaking up into smaller fragments. Now we'll be coming back and seeing the chemical properties of alkenes, then alkynes, and finally end up with benzene. Right. After chemical properties of alkenes, let's come back and see the chemical properties. What are we going to learn in alkenes? Right. In alkenes, I'll be teaching you the addition reactions because of the presence of double bond in alkene. I'll be teaching you how to add hydrogen around the double bond, how to add halogen around the double bond. After that, you have one more concept. This is symmetrical, isn't it? Because hydrogen are hydrogen linked. But when it comes to unsymmetrical reagents, like where you have two different, one hydrogen H plus cation and Cl minus anion, we are going to learn a concept or a mechanism also, that is Markovnikov of addition and anti-Markovnikov of addition. I'll be dealing that also with you all. Then I'll be teaching you how are you going to add sulfuric acid around double bond, how are we going to add water around double bond, and how are we going to add hypochlorous acid, that is HOCl, around the double bond. Those are all coming under addition reactions. From there, I'll be teaching you what is meant by allylic substitution reactions also. I'll be showing what is allylic carbon. There I'll be comparing with vinylic carbon also. Then, last but not the least, I'm going to teach you the different oxidation reactions of alkenes. Very important concept here. In that oxidation, I'll be teaching about combustion. What did I say? Combustion is nothing but heating in the presence or burning in the presence of oxygen. So that combustion reaction also I'll be teaching. After that, I'll be teaching you about controlled oxidation. Under what conditions is oxidation process controlled? With that, I'll be also teaching you the controlled reaction with KMnO4. What is KMnO4? It is an oxidizing agent, isn't it? So we will see how is oxidation done in the presence of KMnO4. Then I'll be teaching you the oxidation under what conditions, under cold and dilute using alkaline KMnO4 also. Then last, I'll be doing under drastic conditions. How is the oxidation done using drastic? One is cold and dilute conditions, one is drastic conditions, very slowly, one is controlled oxidation conditions. That too I'm using KMnO4 every time. After that, I'll finish off the alkenes chemical properties using teaching you the process of ozonolysis. That is addition of ozone molecule. What is ozone molecule? O3, isn't it? So that O3 molecule I'll be adding around the double bond, where we get ozonoid. That also I'll be showing you. With this, the chemical properties of alkenes will be over. Now we'll come back and learn the chemical properties of alkynes. Right. Now we'll learn the chemical properties of alkynes. We'll see what are we going to do in the whole chapter. Done. When it comes to alkynes, I'll begin because as we have double bonds. So if you have double bond and triple bond, you'll be learning about addition reactions, because you'll break the pi bond and add hydrogen or chlorine around the double bond and triple bond. So the same common reaction in alkenes and alkynes, that is addition of hydrogen. After that, I'll be teaching you a concept called electrophilic addition reactions. Electrophilic addition, it is denoted by E plus. So electrophile, okay, nucleophiles are electron rich species, electrophile electron deficient species. So I'll be teaching how are you going to add halogen. X stands for halogen, HCN, addition of methanol, addition of acetic acid also. So all these additions were based on the, means I should be showing what is electrophile in this. Basically here if I break, this is CH3 plus, like that I'll be showing you what is electrophile in each case, and I'll be showing you the addition around the triple bond. Then I'll be teaching a reaction called polymerization reaction. So in that again there are two types, cyclic polymerization and linear polymerization. Both we will learn in this chapter. After that, I'll finish off alkynes, my reaction, showing you a reaction that is oxidation. In oxidation, you have combustion reaction, you have oxidation with KMnO4 as well as ozonolysis, that is addition of ozone around the triple bond. So these are the chemical properties of alkenes, alkenes and alkynes. So the last topic is your aromatic hydrocarbons. What is the example we have taken? It is benzene, isn't it? Now we'll see what are the different chemical properties of benzene. Right. Now the last topic of the chapter, that is chemical properties of benzene. In benzene, I'm going to teach you about substitution reactions as well as addition reactions. So ESR stands for electrophilic substitution reactions, where I'll be showing halogenation process, that is addition of halogen, which direction, ortho position, meta or para, that I'll be showing. Sulfonation, addition of SO3H, nitration, addition of NO2, Friedel-Crafts reaction, where I'll be adding alkyl, that is Friedel-Crafts alkylation reaction as well as Friedel-Crafts acylation reaction. Here you will be adding alkyl group and here you will be adding acyl group. Done. After that I'll be teaching you addition reactions, that is addition of hydrogen and X stands for halogens. I'll be showing that reaction also around the benzene ring. I'll finish off the topic by teaching you oxidation reactions of arene. Arene is nothing but the aromatic compound. There I'll be showing you combustion reaction as well as I'll be showing you the controlled oxidation reaction also. So students, this is the complete index of the chapter. So index is a bit big, but when you learn the reactions, it's very it's interesting basically. So almost I think I'm left with only four chapters of 11. We'll go gradually. Don't be in a hurry to complete. I'll complete your syllabus by almost October 1st. Then I'll start by October 1st or first week of October. Then I'll be revising and I'll be giving you more and more of JEE as well as NEET preparation for you all. So this is the index of the chapter. We have seen what is a nomenclature. We have seen what is the physical, first thing, that is physical properties. I've shown you what are the different chemical properties. So let's come back and start with the topic. Very important. I'll start first with the nomenclature, or first the classification of your hydrocarbons. So welcome back students to one more session. So in previous video, what did we learn? We've learned the classification as well as structure of alkenes, alkenes and alkynes. Now I picked up the topic, that is nomenclature. Here in nomenclature, what is nomenclature? Basically naming of the compound. I picked up a lot of examples for you all. As I said, I'll be doing in the form of a worksheet. So I picked up these examples which were available in the net. So let us practice now. Suppose in your exam, if your teacher has given you such compounds and ask you to name the compound, I'll be explaining the rules simultaneously. So what is the heading? Write the name of each of the hydrocarbon molecule shown below. Done. So I've already taught you. For alkene, the general formula is CnH2n plus 2. For alkene, it is CnH2n. And for alkyne, it is CnH2n minus 2. Suppose if I have to name this compound, right? How should you start? Now, first of all, first important thing is you need to number the carbon atoms. So what is this? You see, your concept should be rule number 1, numbering the carbon atoms. Rule number 2, you have to see are there any functional groups present in this. So this function groups concept you have studied in grade 10, isn't it? You have to study different function groups like alcohols, acids, aldehydes, ketones, esters, halides, such function groups if they are present. If there are no function groups present, not a problem at all. So in the first example, I've taken the basic example. So in this particular thing, let us start counting the number. No function groups, you can start directly. You can either start numbering from here or you can number from here. Suppose if I name the number this 1, 2, 3, 4, 5, 6, 7 and 8. 8, isn't it? So what is the name of this compound? If I have to say 8 carbon, this isn't, first of all, this is an alkane because there is no double bond in this, isn't it? Or triple bond. So 8 carbon atom or 8 carbon chain, this is called octane. Right? Octa means 8. Now, let us come back to the next example. Here let us see, are there any functional groups present? No functional group. Are there any substituents present? Yes. There is a substituent present here and there is a substituent present here. A side chain. Now start numbering it. No, there's no functional group, so not a problem. You can either start numbering it here or here. But remember, you need to number it in such a way that this gets the minimum number here. The substituent gets the minimum number. So here, if I have to, suppose if I start from here, 1, 2, 3, 4, it gets 4. But here, if I start, it is 1, 2. So minimum number, start from here. 1, 2, 3, 4, 5, 6, 7 and 8. Now see here, at second position as well as fifth position, you have methyl group. How to name? You should name it as 2. This one. First start from here, then comes 5. 2, 5. You need to name it as 2, 5. Then put a hyphen. How many methyl groups are there? 2 methyl groups. So it is dimethyl. Dimethyl. Okay. And dimethyl, what is the parent chain? It is octa. Isn't it? 8. So dimethyl octane. That's over. Let's come back to the third example. Now in this case, first of all, you should see whichever is the longest chain. So if I take this is the longest chain, isn't it? Done. After writing this, finding the longest chain, you should see whether there are any substituents. Okay, 2 substituents. You have to see whether there are any functional groups. So no functional groups. So as I said here, this particular the substituent, it should get the minimum number. Suppose if I start from here, this becomes 1, 2, 3, 4, 5. Suppose if I start from here, 1, 2, 3. Third carbon, you have methyl group. So you can start from that and start explaining the compound. But important thing is here, parent chain, first number it. Number the parent chain. Now, and one more concept you should remember here. See here, there is a double bond in the compound. This is where you need to be careful. This is a functional group almost, isn't it? Alkene is a group. So you should see that here there were no functional groups, not a problem, but here there is an alkene. So that alkene should get a minimum number compared to this alkene should get a minimum number. So from where should I start? I have to start numbering. So alkene first preference given, then goes to the substituent. So 1, 2, 3, okay, 4, this is 5, this is 6, this is 7. Now name the compound. It is, you have at the third carbon you have ene. And here in the fifth carbon you have methyl. So start writing from the substituents. 5, 5. Right? It is dimethyl. Okay, 5, 5 dimethyl. And where is the alkene double bond present? Here, isn't it? Now put a hyphen. 3 at the third position. What is the parent chain? 7 carbon. So heptene. 5, 5 dimethyl. 3 heptene. Done. Right? So next example. Let's come back to the 8th example and I'll move the paper above. So here in this particular thing, what is the example? They've given this compound. I need to write its name. Right. Let's start. Here I should see the longest chain. What is the longest chain? If I take like this, 1, 2, 3, 4, 5. Suppose if I take in this way, 1, 2, 3, 4. Isn't it? Now, suppose if I consider this as the longest chain, this one as the longest chain, 1, 2, 3, 4, 5, 6. Okay, right? So I can go with the longest chain, hexane. Now what are the substituents here? This is a substituent. Methyl group is one substituent. So I'll start from here like this one. 1, 2, 3, 4, 5, 6. So the longest chain would be this one. See here. Right? So this is a example and this is a substituent. Now number it. I said substituent group should be given a number in such a way that that particular number or that substituent should get minimum number. Suppose if I start from here 1, 2, 3, 4, but from if I start from here 1, 2, 3. So I can write it as 3 methyl. What? How many carbon atoms? 6 carbon atoms. 3 methyl hexane. Done? Yes. Now let's come back and see this. In this particular example, first I have to see what is the longest chain. The longest chain, according to this, if I start counting, I need to see the possibilities. What is the longest chain? Suppose if I take only consider this 1, 2, 3, 4, 5. It is only pent. Suppose if I consider like this 1, okay, 2, 3, 4. Again it is less. It is but. Now let me see in this way 1, 2, 3, 4, 5, 6. Again it is only oct. That means, how should I try? I need to start this. But is ruled out, oct is ruled out. I have to see anything 6 carbon. I have to see, is there any 7 carbon possibility? For that 7 carbon possibility, let me see. Suppose if I take, now what is this group? This is C2H5. Okay, I can make this a substituent and I can start from here. 1, 2, 3, 4, 5. Okay, this is also ruled out. Suppose if I take like this, 1, 2, 3, 4, 5, 6. Suppose if I take like this, 1, 2, 3, 4, 5, 6, 7. Yes, this is the biggest one. I am considering in this direction, see here. 1, 2, 3, 4, 5, 6, 7. Okay, done. So the heptane. Now start numbering it. You have start number because you should get the minimum number. This is 1, this is 2, this is 3. So in second and third you have methyl group. So 1, 2, 3, 4. On the fourth carbon you have ethyl. Now how should you write? Methyl and ethyl both are there. Alphabetical order. Start writing 4 ethyl 2, 3 dimethyl heptane, because it is 7 carbon chain. Suppose if I have to name this compound. Okay, right, let's start. Again, you need to see the longest chain. Now here the longest chain is straightly given, not a problem. 1, 2, 3, 4, 5, 6, 7, 8. Octane. So I'm going to take this as the longest chain. Now number the groups. 1, 2, 3. Here this is getting 3, isn't it? Suppose if I start from here, 1, 2. So this would be better because the substituent is getting a minimum number. So 1, 2, 3, 4, 5, 6, 7, 8. So at second carbon you have methyl. Fourth carbon you have methyl. Sixth carbon you have methyl. But where is the ethyl group? Ethyl group is present here at the fifth carbon. So ethyl and methyl alphabetical order. So start with ethyl. It is 5 ethyl, 2, 4, 6 trimethyl octane. Right, students? Hope this is clear to you all. I have given example. So let's come back and start with the next set of examples. Right? Yes, so this is over. Let us shift the paper above and see whether it is clear or not. Right. So suppose if I have to solve the fourth example. Yes. So in the fourth example, what do you have? This is one structure. Let's do this. First of all, this particular thing, you have a cyclic structure in this. That's very important. So what is the parent chain? This cyclic structure. How many carbons are there in the cyclic structure? 1, 2, 3, 4, 5. Pentane. Yes, but this is a cyclo group because you don't have any bonds inside. This is a cyclo group. So suppose if I start numbering this 1, 2, 3, 4, 5. At the first carbon you have, okay, let me see whether I am naming it properly or not. Yes, at the first carbon I have which group here? I have ethyl. At the third carbon also I have ethyl. So I can write 1, 3 diethyl cyclo. What is this compound? This is pentane. Done. Yes. Now let's come back and see this. I'm not going in the order because of the space factor. Now when I go with the 11th one, let's see. In the 11th one, I have to see the longest chain. Isn't it? Done. So if I have to see the longest chain, this is 1, 2, 3, 4, 5, 6. This is longer. Suppose if I count like this, 1, 2, 3, 4, 5, 6. This is also fine. Suppose if I count like this, 1, 2, 3, 4, 5, 6. All the ways it is hex only. But what should you remember? There is an alkene group here that you should be careful. The alkene functional group should get minimum number. Then comes your substituent. When they should get the minimum number, that means I have to start from here. 1, 2. 3, 4, 5, 6. Yes, so this is done. Now start naming it. This particular compound, now what will alkene, I said minimum number, I've done that. Now I have to see the substituent. Where is the substituent? Here at the third carbon there is a substituent. At the fourth carbon there is a substituent. Now start naming it. It is 3,4 diethyl hyphen 2 hexene, because after 2. Done. Let's see this. Now longest chain 1, 2, because it is only in one way. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 means 9 hydrocarbon is nonene. Correct? Now where is the double bond present? Double bond is present here, and it should get a minimum number. You should be careful. Suppose if I start numbering here 1, 2, 3, 4, 5. Suppose if I number from here 1, 2, 3, 4. So this is the right way. This is the right way, because this should get a minimum number. So now what do I get? I get 4 nonene, because it is double bond. Now let me name this compound. This is a cyclo group. Yes. So how many carbons? But 4 carbons. But there is a double bond. So this is cyclobutene. Over. Let's name this. Here again it's a cyclo compound. There is no double bond, all single bond. That means it is an alkene. So cyclo, 3 carbons is propane. Cyclopropane. Suppose if I have to name this simple compound, this is benzene compound. Now I'll further move the sheet above, students, so that this also is clear. Right. Let's come back and do the 7th one. I think this is, I'll make this clear like this. So the 7th example. Okay. I think this whole structure, I'll just move the paper. Yes. So let's move. Yeah. Right. Yes. Now it's clear. Now let us name the 7th, 14th, 15th, 16th and 17th. I think when I come to the 7th example. So the 7th example is what? Here this is bond line structure. No carbon atoms given. But here there is a triple bond given. You have to be careful. This is an alkyne. Now start numbering. First carbon, second carbon, third carbon, fourth carbon, fifth carbon, sixth carbon, seventh carbon, eighth carbon. So the parent chain is octane, triple bond. Correct? Yes. Now, but important thing, what mistake did I do? I said the alkyne should get, the triple bond should get minimum number. That means I should not number like this. I should number in this way: 2, 3, this is 4, this is 5, this is 6, this is 7, this is 8, because the alkyne should get minimum number. So triple bond. So what is octane? Which octane is this? 2-octane. Now let us go to the substituent here. In which position? 1, 2, 3, 4, 5, 6. In the 6th position, what is this carbon? There is one carbon here. There is one carbon here, obviously. There is one more carbon. 2 carbons means ethyl group. So which one is that? Which position? 4-ethyl. 4-ethyl. 2-octane. Done. Now let's write this. Now count 1. Now first of all, before counting, you should see whether there is any double bond or triple bond. Here, do we have any double bond or triple bond? We don't have. So directly 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 means decane. It is decane. Now there is one substituent here, one substituent here, one substituent. So where is the substituent? Here there is one substituent is 1, 2. Okay, let us name this. There is one substituent where? 2. Should I start from here or should I start from here? Okay, I have to start from here only, because the minimum number to be given substituent. So this is 2, this is 7, this is 8. So what can I write? 2, 7, 8. And there is no place here. Trimethyl decane. Right. Suppose, okay, here 15th question. Simple, direct it is 1, 2, 3, 4, 5, 6. All are the same, but there is a double bond. Double bond should get minimum number. So start numbering from here 1, 2, 3. So it is 2-hexene. Done. Now let me move the paper ahead so that 16th and 17th also are clear. Here in this case, in the 16th one, I have to see the longest chain as the compound is given. Suppose if I count like this, 1, 2, 3, 4, 5, pent, done. Suppose if I count like this, 1, 2, 3, 4, 5, pent, done. No problem. So either way or this way, right? Now suppose if you're counting like this, if you're counting like this becomes substituent, this also becomes substituent. Correct? Suppose if I count like this, 1, 2, 3, 4, 5. So both the ethyl groups will be present on either side. Right? So that would be convenient, I think, to name. So how will I take? I'll take this as the longest chain. 1, 2, 3, 4, 5. Done? Yes. So start naming it. So the third carbon, 1, 2, 3. The third carbon I have ethyl, and here also ethyl. So name it 3, 3. Diethyl pentane. Done. Now let us name this last one. Here, as soon as the compound is given, I have to see the longest chain. Suppose if I take this is the longest chain, 1, 2, 3, 4, 5, pent. Suppose if I consider like this, 1, 2, 3, 4, 5. Suppose if I consider like this, 1, 2, 3, 4, 5, all are 5 only, not a problem, right? Now, suppose if you consider this one like this, in the any side you can consider, but the substituent should be clearly mentioned. Suppose if I take like this whole thing, now what will happen? There is an ethyl group in the third carbon, 1, 2, 3 in the third carbon, right? Now methyl group here, it will become 4, but according to the alphabetical order, they should get minimum number. So 1, 2, 3, 4, 5. That is the concept. First pick the longest chain, then see the arrange accordingly to the alphabetical order. So methyl, then this is ethyl. First comes ethyl, then comes methyl. So this is 3 ethyl, 2 methyl pentane. So this is the concept, students. Hope the page is clear. I have done all the examples, students, from the beginning. I'll try to show the sheet again. I have done this example. I've written all examples like this in this way. Then I've gradually picked up. I've shifted the paper, and I picked up all the examples. So hope the concept is clear, students. Any doubt, please let me back, students. Now today's video will be learning the nomenclature of cyclic compounds. Done. So basically we have seen the other day, isn't it? From C1 to C20 were isolated, but among them 1 to 6 are well known to us. Yeah. So when I have to name the cyclic compounds, simple. First, as you know, whenever you have such compounds given, cyclo is the prefix which you have to use. And whatever the parent chain is there, you have to name the parent chain. For example, in this, see here, 1, 2, 3. So you have 3 carbons, so prop. So as I said, the prefix will be cyclo, it will be propane. Now, here 1, 2, 3, 4, 5. 5 are there. So cyclopentane, prefix is cyclo, pentane is a pentane. Suppose if I have this compound, right? So IUPAC name, they've asked me to number this. So first of all, just see here, how many are there? How many? Like 1, okay, well, let's see, 1, 2, 3, 4, right? So let's see again, this is 1, this is 2, this is 3, this is 4. So it is bute. Here how many are there? N joins 1 and 2. It is eth. Done. Means here they may be like and they've not given it in the N. I'm just counting the points. 1, 2, 3, 4. Okay. Or you can also make 1, 2, 3, 4. Bute. 1, 2. Eth. So the same thing, if I have to draw it, it looks like this. This is eth, isn't it? I said eth. It is right, eth. Here, this is bute. I said bute. Now name it. total, what is the parent chain? It is butane. So let us name this and start numbering according to the alphabetical order. I said but gets first. So this is the first one, this is the second one, this is the third one, this is the fourth one. Now name it. You have to name it in such a way that 1-butyl, because alphabetical order. After that, in the second one, 2-ethyl, cyclo, because this is a cyclo group. 4, it is butane, cyclobutane. Done. Alphabetical order of numbering. This is what we have taken. Now if I take this example, right? So again, how many are there? This is how much? Propyl group is into 3 carbons. Done. So let's name. Now this is 1 carbon atom only. How should I name? According to the alphabetical order, M. After that, P. So this is 1-methyl. At the third one, we have 3-propyl cyclohexane. Done. Simple. Let us name this compound now. Here, what did they give us? There are substituents here also, there are substituents here also. First of all, it is a cyclopropane group. Let us write off the parent chain, cyclopropane. Now, see here, at the first position, there are 2 groups. At the second position, there are 2 groups. At the third carbon, there are 2 groups. So name this 1, 1, 2, 2, 3, 3. How many? Total hexa. All are methyl groups only, because only 1 carbon, isn't it? So hexa methyl, okay, there's no place, hexa methyl cyclopropane. Done. Yes, students, so this is how you have to number the cyclo compounds. If it is there are no substituents, you directly number it. If there are substituents, you have to go with the alphabetical order. Done. Yes, so this is how is that. Now let's start with the nomenclature of unsaturated hydrocarbons. Suppose if there are alkenes, if there are alkynes given, how to name that thing. So whenever I said, whenever a compound is given, you have to check for the longest parent possible carbon chain. Whichever is longest, that will be considering as a parent chain. Right? Fine. So now, first let us see how should we do this, and next we will see which is wrong, which is right also in this. Suppose when you have alkenes, remember that should get, that particular carbon should get the minimum number. Right? Done? Yes. So start with 1. Then this is 2. Okay. This carbon, I have to say, okay, here we'll write 2. I'll go like this. 3, 4, 5, 6. This is the correct way, because I said alkene should get the minimum number. Suppose if you start numbering like this 1, 2, 3, 4, 5, 6, 7, you will get longest, but that is incorrect. Whenever you have alkenes, that should be given the preference first. Remember that. Yes. So based on this, let us start naming this compounds. So this is over. So alkanes should get, or the double bonded carbon should get minimum number. Remember this. So let us see this. So I said lowest number should be assigned or should be given first preference. Now here when I start from here, 1, 2, 3, 4, 5, 6. So the alkene is getting lowest number. Suppose if I start from here, 1, 2, 3, 4, 5. So it's getting more number, isn't it? So the correct order is 1, 2, 3, 4, 5 and 6. So parent chain is hex -2. After second carbon double bond is there, 2 ene. This is over. Now let us take this. Suppose if you have 2 double bonds like this, I told you, so the preference should be given, but here when you have a substituent also, so that one which has a substituent and a double bond, that should be given preference compared to this. Hope you understand, students. So the numbering will be 1, 2, 3, 4, 5. So how to name this? In the second position you have methyl 5 carbon, so it is penta. In the first you have where you have diene. Here this is one I said, isn't it? Yeah, at the first one as well as fourth one you have alkenes, means double bond, 1,4 diene. This is done. Yes. So now let's see one more. This part is over. Now let's see if what happens, or how should you name when you have triple bond. Alkenes are over. Now let's see when you have triple bond or alkynes, unsaturated compounds. So how should you name it? Right. Let's see. As I told you, the unsaturated one, or wherever there is double bond and triple bond, that carbon should get the minimum number, as I said. So we'll start numbering this one. So they should get the minimum number. Now, important thing, now compared to alkenes and alkynes, which should get minimum number, again the rule is alkyne should get the minimum number, then comes alkenes. So start numbering: 1, 2, 3, 4, 5, 6, 7, 8, 9. Done. So let us number this also. Now you have again alkynes and alkenes. Right. Now, when hydrocarbon contains, remember one more thing I'm telling. When hydrocarbons contain one double bond and one triple bond, what do we call this? We call them as alkynides. Alkynides. What are these called? Alkynides. Done. So here the parent chain is numbered in such a way that now multiple bonds, that is double or triple bond, they are assigned the lowest possible number. That is how we should remember. But when these are located at equivalent positions, right? So when they are located in equal positions, then double bond is given priority over the triple bond. Okay, equivalent position, then double bond, we will give more priority to the double bond than triple bond. Understood? Yes, right. In this case, I am start numbering it: 1, 2, 3. If it is equivalent position, then double bond will be given more preference. Right? 3, 4, 5, 6. Right? So now let's see this. Here they are at equivalent position. Double bond here, triple bond here. Yes or no? Yes. So I told which is given preference. Double bond is given preference. 3, 4, 5. Now let's see this. Here you have double bond. Here you have triple bond. So again the same: 1, 2, 3, 4, 5, 6. Let us number the first one. So here at the 7th position, basically the parent chain is 9, known. Okay, at the 7th carbon you have alkene, so nonene, and at the 2nd carbon you have alkyne, so 2-ine. This is how you have to name. Now again, in this case, the first carbon, now total is 6. No, 6 or 7. Let's see. Did I leave one? Yes, I've left one. 1, 2, 3. This is 4. This is 5. This is 6. This is 7. The parent chain is hept. So at the first position you have heptene. At the 4th position you have yine. That is 4-ine. Now in this case again, at the first carbon you have, but the parent chain is pent, alkene, so pentene. At the 4th one you have pentine. Now when I take this, once again the same thing, the parent chain is 6, hexa. So at you have at first carbon also double bond, 3rd carbon also double bond, hexa di in 5-ine. So this is how you're going to name the alkenes, and that is the unsaturated hydrocarbons when you have double bond and single bond. So only one thing you have to remember. What should you remember? When hydrocarbon contains one double bond and one triple bond, they are called as alkynides. Okay, alkynes, alkynides. But how is the parent chain numbered? In such a way that the double bond as well as triple bond is given the lowest possible number. Suppose if you have double bond and triple bond at equivalent positions like this, then what will you do? you will give preference to alkenes first, double bonds, then you will give preference to alkynes. So that is the concept, students. Hope this is clear. I'll be again meeting you all with the next session, in the next session, that is nomenclature of hydrocarbons. I'll be doing alcohol nomenclature, aldehydes, ketones, carboxylic acids, cyanides and isocyanides also. Thank you for watching. Welcome back, students, to one more session of your hydrocarbons. So today the topic which we are going to learn is isomerism. We have seen the nomenclature of alkenes in the previous video. Now once we learn the isomerism concept, it's easy for me to teach you the geometrical isomerism, position isomerism in alkenes, right? So basically when I have to speak or define this term isomerism, how can we basically isomerism, how can it be defined? It is a phenomenon, right? What is this phenomenon in which, suppose if I have a compound or two or more compounds where they have the molecular formula is similar. So with this concept of isomerism, I can assign different molecular structures to them. So once again, what is isomerism? Isomerism is a phenomena, or it is defined as a phenomena by virtue of which when two or more compounds, if they have the same molecular formula, we can assign them different molecular structures. That is the isomerism. So now what is important for us for naming the alkenes is classification. Basically, isomerism is classified under two categories. The first type is structural isomerism. It is also called as constitutional isomerism or isomers. So structural or constitutional isomers. This is the first classification of isomers or isomers. Mers means units. The second type of classification is called stereoisomers. It is STREO, stereo isomerism or stereoisomers. The structural isomer is again divided into different types. What are they? It's divided into chain isomerism. It can be divided into position isomerism. It can be divided into functional group isomerism. It can be divided, or the next category is called metamerism. The next class of category is tautomerism. I'll be teaching about all these. The next category is ring chain isomerism. Right. Fine. So now let us come back to stereoisomerism. Stereoisomerism is again classified into, if I have to see, it's again classified in chain isomerism also we have written. Right, now let us come back and write stereoisomerism. Stereoisomerism is again of two types. What is that? I mean, two types means it is also divided into geometrical isomerism, geometrical isomers or isomerism, and the second category is optical isomerism or optical isomers. Optical isomerism or optical isomers. Right. So geometrical isomerism is again divided into two types. What is that? Cis isomer and trans isomer. Optical isomers, they are again divided into enantiomers, diastereomers, like that. There is one more category of stereoisomerism which I have to mention you, that is called conformations. Right? Done. Now what am I going to use for your naming nomenclature of alkenes is, I'll be using cis and trans isomerism. I'll be also explaining you the position isomerism also. So as of now, I'm going to take cis and trans isomerism. I'll be taking the example or the concept of position isomerism as well as chain isomerism in this for explaining the alkenes. Right? Suppose if I have to speak about geometrical isomerism, first I'll be picking up this particular geometrical isomerism concept and then taking certain examples. Suppose if I have to take or speak about geometrical isomers. What are geometrical isomers? How many types? So I say geometrical isomers are again divided into cis and trans, isn't it? Isomerism, or the units are called isomers. What are they divided into? They are divided into cis isomer, and they are divided into trans isomer. Okay, let me take an example, then so many worksheets questions will be doing. Right. So this cis isomer and trans isomer, what actually do they mean? What is the example? We will see. Right. Suppose if I have to take cis isomer, the most important thing you should remember is this is shown by alkenes and not alkenes. Done? Right. Cis means same side. Trans means opposite side. Remember that. Suppose if I take an example, C double bond C, and around carbon tetravalency of 4. Here also C double bond C, around carbon tetravalency 4. Right. Cis means, suppose if I have one group here, hydrogen, on the same side I should have one more. Here if I have CH3, on the same side you should have CH3. So now total number of carbon atoms are 1, 2, 3, 4. It is bute. So what is the name of this compound? This is called cis bute 2-ene. This is the compound. Okay. Yes, cis isomer means having groups on the same side. Right. Now let us write this compound. Trans means what? I am taking the same example, but here hydrogen should be in opposite side. Now this CH3 and CH3 will be on the opposite side. So this is called trans bute 2-ene. So this is your trans isomer. Hope the concept is clear, students. Cis isomer means on the same side. Trans isomer means on the opposite side. Now basically when I have to speak about the what possibilities are there for forming a cis and trans isomer, that means which is possible. Suppose if I have to write about the possibilities of the conditions, always remember for a geometrical conditions for forming geometrical isomers or geometrical isomer or geometrical isomerism. Phenomenon is isomerism. Isomer means the units which are showing the concept. So the first condition for showing the geometrical isomerism is they should have presence of double bond. When there is double bond only, it's going to show geometrical isomerism. Remember that. Second important thing is the two atoms. In that, see, I told you, CH3. So two atoms or groups attached should be different. Attached should be different. Remember that. For example, see here, ABC, CAB. Now see here, the different, isn't it? So this is possible. Suppose if I take AAC, CAB, is this possible? Not possible. Why? It is not possible because two groups are similar here. So this is not possible. Suppose if I take this combination AAC, CBB, is this combination possible? This combination also is not possible because it has similar group. So the first condition for this is it should have double bond. Second condition is two atoms, whatever are there, it should have different groups. What are the properties of geometrical isomers? Let us see. Basically, this geometrical isomerism, what way are they different? Right? So geometrical isomerism or isomers, okay, geometrical isomers. What are the difference in properties? We have studied the conditions. Now we'll see what are the difference in properties. Suppose if I have to take the geometrical isomers, the first important property, dipole moment. Dipole moment. What are the two geometrical isomers? As I said, cis isomer and trans isomer. So when I have to speak about cis and trans isomer, first important thing, the dipole moment of these, it varies. Both cis and trans will vary. So we will write vary. means both will be different. Let us take an example. We take C double bond C, 1, 2, 3, 4. So this is cis isomer. Suppose if I take C double bond C, 1, 2, 3, 4, H, CH3, CH3. This is trans, isn't it? Right? Now I have to write cis and show you. So let me turn the page like this. Yes, this is H, this is H, CH3, CH3. This is cis isomer. So when I have to write the dipole moment of this, in the first case, the dipole moment of this and the dipole moment of this, both are on the similar side. So mu value will be equal to 0.33 d by. But here in this case, what's happening? They're in the opposite side. So this dipole moment and this dipole moment gets cancelled. So here the dipole moment is 0. So are you not finding the cis and the trans isomerism dipole moment is varying? So that's the first concept. Right. Now let's come back and see one more example. Let me adjust. Yes. Fine. So when I have to take the next example or the next property in which they vary, next property is boiling point. Right. So when I have to compare boiling point of both, always remember the cis isomer boiling point is greater than trans isomer. Remember that. Suppose if I take an example, the cis isomer. Here the cis isomer boiling point is 277 Kelvin. I have taken certain example. Here the trans isomer is 274 Kelvin only. Now what is the reason for this difference? So basically when I take a cis isomer, what will happen? There is greater polarity. Right? When there is greater polarity, what will happen? The stronger interparticular force, isn't it? Polarity is there. Here it got cancelled. But here polarity exists means what happens? Stronger interparticular forces will exist. So let us write the reason here. Greater polarity. I am writing the reason for what? Why is it more? Why is cis more than trans? So greater polarity means stronger interparticular forces. Yes. So because of this, cis isomer has a greater boiling point than trans. Now, next important, melting point. Let us write a concept of melting point. So when I have to speak about melting point, cis isomer melting point is less than trans. What is the reason? Boiling point we said it is more. But here melting point, cis isomer has a melting point lower than trans. What is the reason? So in trans what happens? Let us write the reason. In trans, molecules are closely packed. Molecules are closely packed in solid state. Why? Due to symmetry. Due to symmetry. That's the reason melting point is greater than because the crystal lattice is tightly packed. Because of this, the melting point is greater than cis isomer. So these are the conditions, students. Hope the concept is clear. Now I'll be doing a worksheet based on this, based on the geometrical isomerism as well as this one. Okay, so before I have to explain about the worksheet, I think I have to give you a small example also about the position isomerism. As I said, in the worksheet I'll be having both. Let me take that example also. Right, so now I'll give you an idea about position isomerism, then we will start with the worksheet. Suppose two things. I said according to classification we have position isomerism, chain isomerism, like that, isn't it? So let us see one example about position isomerism, and we will see an example about chain isomerism. Right. So suppose if I take a basic example. Let me take an example that is but1ene. So I've told you nomenclature. Let us write this. 1 but means 1, 2, 3, 4 carbon. In the first carbon there is double bond. Suppose if the same thing, I can shift the double bond from here till here. So this becomes but2ene. Isn't it? I'm just changing the position. The position of this double bond. So from here this becomes C, single bond, then becomes double bond, then now it is but2ene position. Now in the third one, what can I do? I can shift one methyl group to any of this position. I can shift this one here, or I can shift this one here. So the next combination is 2-methyl propene, because now double bond shifting is over. Now possibility is I can shift the methyl group. How does this look? 1, 2, 3. This is propene. So double bond here, and the second carbon you have methyl group. So this is 2-methyl, 1, 2, 2-methyl propene. Now let us number. This is 1, 2, and 3. Now, what are position isomers? Just see. 1 and 2 are position isomers. 1 and 2 are position isomers. What are chain isomers? 1 and 3 are chain isomers. What is this? Let us see. Position isomers means which differ in the position of the double bond or with the bond, or they differ in the position of the substituent or any functional group. When it comes to chain isomerism, what happened? Here it was straight chain. Now here it has become a branched chain, isn't it? So that's why they are called chain isomers, where a straight chain forms a branched chain. So hope students you've got an idea about geometrical isomers as well as position as well as chain isomers. So I'll meet you again in the next video with the nomenclature of alkenes. Right. So we have seen the index. Now we'll be starting with the classification, or the first topic of your chapter, hydrocarbons chapter, that is classification. So what actually are hydrocarbons? The compounds which has one hydrogen and one carbon are called hydrocarbons. Right? Just remember like that. So hydro means hydrogen and carbon together forming hydrocarbon. Simple, isn't it? Now, so when I have to classify that, so I'll be gradually taking you into the topic. Just see. When I have to classify hydrocarbons, first important thing you have to remember is, see, if I say, now this is your pen, this is a straight chain, straight, isn't it? Nothing linked. We have one corner here, one corner. Suppose if I'm joining one pen here, one more pen here, it will become cyclic, either straight or cyclic in nature. So in the same way, classification also, hydrocarbons are basically classified into the prime categories, that is both alicyclic as well as cyclic. Okay, okay, let us not write ali now. First we will write acyclic hydrocarbons. I'll be writing as HC. Acyclic means there is no cycle in this. A means without cycle. The same thing, the reverse order, it is cyclic hydrocarbon. That means there is a cyclic ring in that structure. That acyclic means without acid. This is further divided into 3 categories. This is your chapter, that is, it is divided into alkanes, it is divided into alkenes, it is divided into alkynes also. So as I've shown you the index, we'll be studying about the nomenclature, isomerism, chemical properties, physical properties of all these in the chapter hydrocarbons. Apart from that, cyclic hydrocarbons are again divided into 2 categories, that is, now it is alicyclic hydrocarbons and aromatic hydrocarbons. Aromatic hydrocarbons. Now alicyclic, that means, now see there's a little difference here. Acyclic means without a cycle. Alicyclic means they have a cyclic structure in them. What are they? They're again divided into, for alkanes we are going to study about cycloalkanes. For alkenes we'll be studying about cycloalkenes. For alkynes, we'll be studying about cycloalkynes. I'll be giving examples about everything. Suppose if I come to aromatic compound, aromatic compounds are again they are ring because they come under the cyclic structure only. They possess a ring, but only differences here they have alternate pi bonds. These pi bonds will be moving around, showing us the concept of resonance. So aromatic compounds, example again you have benzenoid, non-benzenoid compounds also in that. So aromatic compounds, the basic example I'm taking is benzene. Here we'll be studying about benzene, toluene, phenol, cresol or xylene. All these compounds are come under benzenoid compounds. So this is your classification. Simple classification, nothing much to remember. First is acyclic, means without ring. Cyclic, in that cyclic also you have two categories. Under alicyclic you have specific cyclocompounds, that is cycloalkanes without any means there is no double bond rather, because in alkenes, cycloalkanes you have a double bond. In cycloalkanes there is a triple bond present along with the ring. Yes. So after classification, let's learn the first structure of these compounds, hydrocarbons. First, if we know the structure, I can easily tell you where is it breaking or where is the bond forming. Right. So if I have to speak about alkenes, the first class of hydrocarbons. So under which do they come? They come under cyclic, or do they come under alicyclic? They come under, or acyclic rather. Sorry, I'm sorry. Do they come under cyclic or acyclic? They come under acyclic hydrocarbons. Acyclic means there is no ring in the structure. So when I speak about alkanes, the first class or the first group of hydrocarbons, so this alkane, the general formula is CnH2n plus 2. What is this? We will see. So I said hydrocarbons is a combination of carbon and hydrogen, isn't it? One carbon, one hydrogen. This N stands for the number of carbon atoms. That means, suppose if I take N is equal to 1, right? Now substitute in this formula C1H2 into 1 plus 2. Done. Now multiply, you get C1, 2 1s are 2, 2 plus 2, 4, CH4. So the first alkane is methane. So N is, it denotes the number of your carbon atoms, carbon chain. Here I've taken C as 1. Okay, now carbon, I'm substituting that number also there. It becomes CnH2n plus 2. The first alkane is methane. So I've drawn the structure of methane here. Suppose if I take the second alkane here, now I'm going to take N is equal to 2 here. Substituting the formula CnH2n plus 2, what do I get? C2H, 2 instead of N is 2, 2 into 2 plus 2. So this becomes C2, 2 2s are 4 plus 2, 6. The second hydrocarbon is ethane, like that, C3, C4, C5, like that. Done. Ma'am, I have directly drawn the structure because I've already done a chapter called chemical bonding for you all. Chemical bonding chapter, I've discussed about all the types of hybridizations in that. Please go to the playlist in my channel. There you will find, just find CBSE grade 11 topics. In that I have done a chapter called chemical bonding. In that chemical bonding, I've taught you about sp hybridization, sp2 hybridization, sp3 hybridization, sp3d2, dsp2, all sp3d2, all I have done in that. Please go and watch that for hybridization. So here I've directly taken the structure, but before that I'll give you a small idea, a short idea about the hybridization process. When I said methane, the first alkane, this is your methane molecule, formula is CH4, which we have got. Now how will I decide the hybridization of this? First of all, you take carbon, write the atomic number of carbon. Atomic number of carbon is 6. Write the, according to Avro principle, fill in the electrons. 1s2, 2s2, 2p, 2, 2, 4, 6. Now in the ground state of carbon, when I take, now write 1s2 according to Hund's rule, opposite spin, then 2s2, done. So 2p, 1, 2, half filled. First you should fill half, then come back, then pairing should be done. So according to this, now in the excited state, what happens? One electron, now this is 1s, this is 2s, this is 2p. One electron from here excites to the 2pz. So in the excited state, how does it look? This is 1s, this is half filled because one electron has shifted here, 2s, then comes your 2p, all are half filled. Done. Now what happens? 1s. Now how many hydrogens we have? We have 4 hydrogens, isn't it? So this and this will hybridize first. There will be a hybridization formed between these two. So what will happen? How does it look? This looks like this. 1, 2, 3, 4, half, 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 and your hydrogen. Now this is overlapping. They combine, atomic orbitals combine to form hybrid orbitals. So hybridization done. Then this hydrogen will come and occupy this 1, 2. So it is like this: 1, 2, 3, 4 hydrogens. Done. So what is the type of hybridization? sp3, 1s and 3p, 1s and 3p. That's why it is sp3 hybridization. So when they overlap, according to this concept, again I'm telling you, please watch the hybridization video. I have done clearly in that, in chemical bonding chapter. So here 1s and 3p are overlapping, forming hybrid orbitals. So this is how you get the orbital diagram. So 1s and 3p orbitals, after overlapping, they're going to combine with hydrogen, as I said, and forming sigma bonds. So this is the orbital diagram of methane. Whenever you're writing high structure, or whenever you're writing this particular representing the orbital diagram, 2 important things you should remember. What is that? The hybridization, type of hybridization. What is hybridization? It is 109.5 degree. Next important thing, you have to remember the shape. What is the shape? It is nothing but tetrahedral in shape, isn't it? So the shape is tetrahedral. So you need to remember that. Bond dissociation and enthalpy, that is 370 kilojoules per mole. Even if you don't remember, also not required. But here you need to mention the hybridization as well as the bond angle. Very important in this. Now when I come to the second alkane, that is ethane. The same concept. Carbon, you will write the ground state. You will write the excited state. Then you will finally hybridize it. So once you hybridize, again you will get sp3, isn't it? 1s and 3p. So here what happened? C2. So this is for one carbon. This one we have drawn here. This is for the second carbon. This is done. Both are overlapping, forming a sigma bond. We have 2 types of bonds. One is sigma bond and pi bond, isn't it? So forming a sigma bond here. Those. Now later, how many hydrogens are there? 6. So 1 hydrogen, second hydrogen, third hydrogen will combine. Here also 1 more hydrogen, second hydrogen, third hydrogen. All will combine together and form sigma. This is which bond? Sigma sp3. Here what is the bond? Sigma sp3. Here what is the bond? Sigma sp3. Here also sigma sp3, sigma sp3, sigma sp3. So finally, even in ethane, we have sp3 hybridization with the bond angle of this, and the shape is tetrahedral in arrangement. So whenever you're writing the structure, first important thing, knowing the configuration. This is the procedure. After writing this, you need to draw the structure. After drawing the structure, you need to tell the hybridization. After writing hybridization, you need to tell the shape of the molecule. Same here also with ethane. Right. So after alkene structure, that is the first hydrocarbon, what's the general formula? It is CnH2n plus 2. What examples we have seen? We have seen the examples of methane and ethane. Now we'll come to the next category of hydrocarbon, that is alkene. Here I picked up ethene. So what is the general formula which you should remember? For alkene, the general formula is CnH2n. Earlier it was CnH2n plus 2. Here it is CnH2n. Okay, suppose if I assume n is equal to 1. Let us substitute in this formula. It becomes Cn, that is C1 H2 into 1. So this becomes C1 H2. This concept only doesn't exist, isn't it? Because for a particular alkene to form, you require, means there should be a bond between 2 carbons. So this is ruled out. Suppose if I take n is equal to 2 here. So let us start, this becomes 2. So this becomes 2 into 2. So C2H4. So your alkene is going to start from n is equal to 2 because it is a bond formed between 2 carbon atoms. So what is C2H4 called? The basic alkene, that is ethene. I've drawn the structure of this. Again, I'm mentioning I have done the hybridization concept in chemical bonding chapter. Please watch the playlist in that for that particular concept. But here also I'll give you an idea about hybridization. So ethene, the formula is C2H4. Now let us take that C2H4. Now, first of all, you need to take carbon. Write the atomic number 6. So it is 1s2, 2s2, 2p2. In the ground state, when I have to show the configuration, it is 1s, filled. 2s, it is again filled. Now 2p, I need to show first half filling. Now what happens in the excited state, one electron from here, it gets excited to the 2p shell, 2p orbital. Then how does it look? I need to write ES, that is excited state. How does this look? This becomes 1s like this. Then this becomes 2s, that is half filled. Then you have 2p, which is again half filled. So these two will hybridize together. But what is the concept here? We have only 4 hydrogens, isn't it? Okay, 1, 2, 3, 4. So how many do we need here? First of all, then when they're combining, let's see this. So ethene, we have written double bond. Okay, so 4 hydrogens according to this. 1, 2, 3, 4. Done. Okay, both will combine together. Let me see. It, when they form hybrid orbitals, it is like this. 1, 2, 3. Yes, so fine. So this is 1, this is 2, this is 3, this is 4. Fine. So now what happened? Just see here. Carbon and carbon will combine. Okay. This carbon and the carbon, how many carbons are there? Only 2 carbons. This carbon and this carbon. So what will be the overlap? How will be the overlap? 1s and 2p only will overlap, isn't it? Yes. So 1s and 2p will overlap, and what will be left? There will be one unhybridized orbital. One in this carbon, like this, for one more carbon, one more unhybridized orbital. So now what happens here? The sp2 hybrid orbitals of one carbon will overlap. One more sp2 hybrid orbital, 1s and 2p will overlap and forming sp2 hybrid. And how many hydrogens? 1, 2, 3, 4 according to the formula. Now still we have one unhybrid orbital in the first carbon and one more unhybridized orbital in the second carbon. Those two will form a pi bond. That's why the hybridization is sp2 only here. Earlier it was sp3 done, but here it is sp2 hybridization only. So that unhybridized hybrid orbital will form a, this is what do you say, up and above and below, parallel bonds, right? So as a pi bond, one for the first carbon, one for the second carbon. So this is your structure. Now what is the bond angle and shape? I said the bond angle is, as I've already shown here, it is, if I say, it is 120 degrees for sp2 hybridization, and the shape of the molecule is trigonal planar. Trigonal planar structure. Right, now when I have to see the bond length, just see here, CH, single bond length is 110 picometer. For a double bond, C double bond C, the bond length is 134 picometer, larger than the single bond. So larger than the single bond is double bond. Done? Yes. So I think all the details, this is the hybridization part, this is the structure, this is the bond angle, this is the shape, and this is the bond length. Right, now let's come back and learn the structure of alkynes. Alkanes we have seen, general formula CnH2n plus 2. In alkenes, general formula CnH2n. Now when I come to alkyne, again the same hydrocarbon, one carbon, one more hydrogen. Here the general formula is CnH2n minus 2. Right, now suppose if I take N, I said alkene is formed between 2 carbons. In the same way, alkyne also is formed between 2 carbons. So I should not take N is equal to 1. It's going to start with N is equal to 2. Now substitute C2H2 to 2 minus 2. So this becomes C2, 2 to the 4 minus 2 is 2. So C2H2. So C2H2 molecule is called ethyne. C2H2. Around carbon there should be 4 bonds, means the valency is 4, tetravalent. So 1 hydrogen plus 3, 4. For this carbon 1 hydrogen plus 3, 4. So I've taken the example of ethyne. So let's write the ground state, again hybridization. Same carbon 6 atomic number, 1 is 2, 2 is 2, 2p2. In the ground state this looks like this, 1 is 2. Here it is 2 is 2. Here it is 2p2. In the excited state, one electron from here shifts to this, right? Now, how does this look? This looks like 1 is filled, half, 2s and 2p. But what is the formula? According to the formula is, it is C2H2. Here also I've written C2H2. So what happens? One s orbital and one p orbital will overlap. Okay, so there is an hybrid orbitals formed between 1s and 1p, because the formula is only C2H2. One hydrogen here, one more hydrogen here. So there is an overlap and forming what type of hybridization? sp hybridization. So now observe 1s and 1p. 1s and 1p of one carbon, 1s and 1p of the other carbon will overlap, forming sp hybridization. And how many are unhybridized here? 2. Both are forming a pi bond. This unhybridized electron of one carbon forms a pi bond. One more unhybridized forms one more pi bond. Okay, right. The second carbon, because we have C2, isn't it? For one C2 is one set, the second C2 is one more set. So they try to form one pi bond here. One more unhybridized forms one more pi bond, one more pi bond here. That's why in ethyne molecule there is 1 sigma and 2 pi bonds present. Here this is your structure. Here after hybridizing in this direction, it's going to overlap with hydrogen. How many hydrogens? 2 hydrogens. One hydrogen here and one more hydrogen. So I'm again mentioning, I have given a clear explanation of hybridization in chemical bonding chapter that is kept in the playlist. Please watch the chemical bonding chapter. There I have listed out all the types of hybridizations. Right, so now what happened here? This is the overlap. These two are pi bonds. We count only this, isn't it? For the angle, just this one. This is which? What is the angle here? It is 180 degrees. So the bond angle in hybridization here is, so the bond angle is 180 degree. Shape of the molecule is linear, because it is linear, isn't it? And what is the type of hybridization? The hybridization is sp hybridization. sp hybridization, 1s and 1p. So this is the concept. So this is the structure of ethyne molecule. So I hope the concept is clear. I've done the classification. I've taught you the structure of alkane, taking an example of methane and ethane. I've taught you the structure of ethene, that is under alkene. Then I've taught you the example of ethyne, that is under alkyne structure. Welcome back, students, to one more session of your nomenclature. In the previous video, I've taught you what actually is the classification of isomerism, isn't it? Then I've taught you about structural isomerism or constitutional isomerism. Then I've also taught you about stereoisomerism, isn't it? Yes. Please watch the previous video and then come back to this video. Right. Here I picked up a worksheet again. Hope that is clear for you all. Right, so let's start working on this, and then finally you will come to an understanding how to name a compound. Right, here they're given us draw and name the cis and trans isomer, cis and trans condensed structure of this. Fine, very interesting question. Let's see. Now first of all, they've asked me to draw the cis and trans condensed structure. So this is the structure given. I need to draw the condensed form of this. That means this is the whole structure. I need to condense it and write it as in the cis form, and name it, transform and name it. Done. Now your concentration should be on this double bond. Fine. Yes. So here first pick up that double bond. Right. C double bond C. Here also take the result C double bond C. Now around the carbon, around the double bond, how many other groups are there? This is one methyl group on this side. Here this is CH2, CH3, isn't it? And there is your H also, isn't it? To this carbon, just see here, to this carbon I've written here. Now what else is there? CH3 is here, one group. H is in this group. So I'm going to write CH3 on this group. This H on this side. Now what do we have? You have CH3, this is ethyl group, that is CH2, CH3. And the hydrogen which is here, isn't it? Now both the groups are on the same side. That's why it is cis isomer. Now when I have to draw the trans, 1, 2, 3, 4 lines, done. The same structure. This CH3 is here. Now this CH2, CH3 will come on this side, and hydrogen is here and it comes on the opposite side. Hope the concept is clear, students. This is the condensed formula. Now I need to write the name of this compound. Yes, so name of this compound, how to write? Basically this is cis isomer, so write cis, done, hyphen 2. In the second carbon we have first carbon, second carbon we have double bond 2. How many totally? 1 2 3 4 5, so it is pentene. Now this one, how to name? Small t trans 2 pentene. Hope the concept is clear, students. Done. Now let us name this. Name the following alkenes, including cis and trans for the alkenes that when appropriate. Okay, they ask us to name this. If there is cis, you need to mention it as cis, if it is a cis isomer. Otherwise, name it normally. So here, this is a group given to me. How should I start numbering? I should see in such a way that the alkene is getting a minimum number, means the double bond is getting a minimum number. So start numbering 1, 2, 3, 4, 5. 5 means pent. So which position is the double bond? It is in the first. So it is 1 pentene. Done, students? Yes. Now let's come back and do the next one. Yeah. Let me shift the page above a little bit so that even the second question and third question is visible to you all. Done. So what is this compound here in the B part? Again there is a double bond. So I should see that the double bond gets the minimum number. So I should start from here. 1, 2, 3, 4, 5, 6, 7. Hept. So it is 1 heptene. Done. Let me start with this. So this particular example, hope the example is clear to you all. Yes. Here, two things you should see. What is this? There is a double bond here. There is a substituent. So the double bond should get a minimum number. So I should start from here. 1, 2, 3. So this is 3. 4. Okay, let me number 1, 2, 3. This is 4. This is 5. This is 6. This is 7. This is 8. 8 means what? It is oct. But there is a double bond here at third carbon. So it is 3 octene. So where is the substituent? 7th. So you need to write 7 methyl dash 3 octene. Done? Yes. Now let us come back and do the D part. This one, the last this example. Fine. So here they asked us if there is cis isomer, you need to mention that cis isomer this side, isn't it? So here I am able to see a cis isomer because both the hydrogen atoms on similar side, both the methyl groups on similar side. So name this. Whenever you have a cis isomer, start with cis. 2 hyphen. So 1, 2. In the second carbon you have double bond. How many are there? 1, 2, 3, 4. So this is 2 butene. Clear? Yes, students. Done. Let us come back and do some more. Very interesting concept. Hope this is clear. I have a lot of examples here. Let me do these examples one after the other. Right. Now, in this E question, let's solve this question now. What do they give me? A big chain is given to me. Nothing to worry. Let us see how can we name it. First of all, I need to see the longest chain. When I have to see the longest chain, 1, 2, 3, 4, 5, 6, 7, 8, 9. Nonene. Why nonene? Because there is a double bond. Which position is a double bond? This should get the minimum number. Suppose if I start from here, 1, 2, 3, 4. This is the fifth carbon. Suppose if I start from here, 1, 2, 3, 4. So I should start from here. 1, 2, 3, because they should get the minimum number. 1, 2, 3, 4, 5, 6, 7, 8, 9. It is nonene. So which position? 1, 2, 3. This is fourth position. So the double bond is in the fourth position. So which isomer is this? See here. H and H are on the opposite side. So this is trans 4 nonene. Correct? Yes. Now let's come back and do the fifth F part. Yeah. In this compound, what do they give me? First I have to see, is there any double bond? Yes, there is a double bond. Then I have to see the longest chain. Done. So if I count from here, one more thing I should remember, the double bond should get minimum number 1, 2, 3, 4, 5, 6, 7. So it is hept. Suppose if I start from here, 1, 2, 3, 4, 5, 6, 7. So when I start from here, 1, 2, 3, 4, the double bond is getting 4th number. But when I start from here, 1, 2, 3, so 3. So the procedure is this: 1, 2, 3, 4, 5, 6, 6, 7. 1, 2, 3, 4, 5, 6, 7. So name it. It is Cis Isomer. Because why Cis Isomer? Yeah, just see here. The bonds here on this side, similar groups. This here around the double bond. This is one curve. This is one. Yeah, that's why it is Cis 3 heptene. Right? Yes. Now we will learn all the 3 structures now at once. Here they have given us one hexene. I need to draw line bond structure, condensed structure and skeletal structure. So all will be clear to you all students here. Just see. Draw the, they've asked me, take one hexene and draw the line bond structure. Line bond structure means it's a straight structure. Just right. So it is one hexene. So 1, 2, 3, 4, 5, 6. So this is one hexene. That means this is the carbon. So this is the first carbon. This is one hexene. Now in hydrogens, around carbon 4 hydrogens. 1. Okay, this is 4. For this carbon, done. For this carbon, done. For this carbon, H means total should be 4. See here, 1, 2, 3, 4. 1, 2, 3, 4, like that, 4. For this carbon, only one hydrogen because 1, 2, 3, 4 bonds. For this carbon, I have 2 hydrogens. This is line bond structure or bond line structure. Suppose if I have to do the condensed structure. Condensed structure is nothing this. See here, I am writing the condensed structure. 1, just instead of writing the hydrogens like this, we write it as CH2, double bond, CH, CH2, 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 CH3. Count once. 1, 2, 3, 4, 5, 6 because it is hexene. Now in the skeletal structure, I need to represent the 6 carbons, isn't it? 1, 2, 3, 4, 5. That means 1, 2, 3, 4, 5, 6. Where is the double bond? It is present in the first structure. That's it. This is how you're going to represent the line bond line structure, condensed structure as well as your skeletal structure. Now let us do this example. Here what did they give us? They've asked us to write the bond line structure for 4 isopropyl, 2 methyl, 1 nonene. Okay, so 4 isopropyl, 2 methyl and 1 nonene they said. Okay, let us write 4 isopropyl. A bit, it's going to take place. Let me write. So 4 isopropyl group they said and nonene. Nonene is 9 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9. A bit congested it is, no problem. And they said 4 isopropyl, 2 methyl. So 1, 2. This is 2, this is 3, this is 4. So in the second carbon, you have methyl group, 2 methyl. So methyl means CH3, H and H. 1, 2, 3. In the fourth carbon, you have isopropyl group. What is isopropyl group? Here again you have prop, 3 carbons along with their hydrogens. 1. Hope this is not congested, students. I picked up a thicker sketch pen, that's a problem. Yes. So here H, here H, here H. Now for this carbon H. This is over. Now fill the hydrogens for all. This is one I'm not writing, just I'm mentioning the dashes. H, 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 H. For this 1, 2, 3, so 1 H. For this 1, 2, H and H. For this 1, 2, 1, 2, 3, 4. For this 1, 2, 3 are there, there is one more H. So this is how it represents. I'm not representing the hydrogen because lack of space. So in the condensed structure, how should I write? CH2. This is double bond, isn't it? So there should be a double bond here. Because this is nonene, 1 nonene. So this bond will not be there for this. And does this have? This also will not have bond. 1 2 3 4, 1 2 3 4, right? So I'm writing the condensed structure: CH2, C, CH3, CH2, CH, CH3, CH, CH3. After that, after CH to CH2, there is no space. I'll extend this here. CH2, 1 2 3 4 5 6 7 8 9. I've extended the structure here. 1 2 3 4 5 6 7 8 9. This is the condensed structure. Now I'm drawing the skeletal structure here. Yes, this is the skeletal structure. 1 2 3 4 5 6 7 8 9. Easy, isn't it? Skeletal structure is easier. Hope the concept is clear, students. Now let us take one more example where I'm going to write for which structure is this? Cis 2-hexene. Okay, cis 2-hexene. They've asked me, right? Hope this is the example is clear. I'll start writing now. Cis 2-hexene. How to write? Fine. But this is in bond line structure, cis isomer will not be denoted. Only in the condensed structure will be showing that. Fine. So cis 2-hexene. 1 2. There's a 2-hexene. So 3 4 5 6. Now hydrogens, hydrogen, hydrogen, hydrogen. One more here, one more here. For this carbon, if I have to take, this is over. Around the double bond, 1 2 3. One more here. For this carbon, only one here. And for this carbon, H, H and H. Right. So 1 2 3 4 5 6. So cis. Let us write cis here. Now condensed structure, C double bond C. On this side, how many are there? 1 2 3 4. So write it as CH2, CH2, CH3. Because after double bond you should count. Only 3 are there. So 3. Down is H. This side is H. This side is CH3. This CH3 is here. This H is here. Now skeletal structure. I'm drawing it like this. Yes. This is the skeletal structure of cis 2-hexene. Now let us take one more example. I have 2 more examples left. Let me do that also. Here they've asked me trans 2-butene, isn't it? Right. So trans 2-pentene. Sorry, pent means 1 2 3 4 5. Done. This said 2-pentene. So in this particular thing, this is first carbon, this is second carbon. After second carbon, 2. Now filling hydrogens, 1 2 3. For this carbon, here and here. For this carbon, when I take 1 2 3 4 are there, 1. For this carbon, 1 2 3 4 1. For this carbon, H, H and H. Now I said in bond cis and trans can't be denoted in the bond line structure. It means only it will be shown in the condensed structure as well as skeletal structure. So write down C. 4 groups. Trans means the group should be on opposite side. This hydrogen I am taking it here. This CH3 here. This whole group CH2, CH3, CH2, CH3. Done. Skeletal structure, I'm just denoting directly. Yes. Why did I show you here? Because opposite sides. See here, this group is here, this group is here. Now, let me do the last one. Cis 2-methyl 3-hexene. Okay. So, because there's no space here, I will write it here. Hexene 1, 2, 3, 4, 5, 6. Now the set cis. I can't show cis here in bond line structure, isn't it? I need to show it only here in condensed and skeletal. So this is cis 2-methyl is it. First one, second carbon. In the second carbon you have methyl group H, H, H. Now this is cis 2-methyl 3-hexene. In the third one, 1,2-methyl, third there is a double bond. Done? Right. Let us fill the hydrogens. 1, okay, 2-methyl 3-hexene. Done. Okay. Hydrogen, 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 hydrogen for this 1, 2, 3, 4. For this carbon 1, 2, 3. For this carbon 1, 2, 3, 4. For this carbon all 3 hydrogens. Hope this is clear, students. Now I need to write the condensed structure. So 1 cis this it. So cis means same side. C. CH2, CH3, down H. Here it is CH, CH3, CH3, down H. See here, this group and this group is on the same side. That's why it is condensed structure. Now in the skeletal structure, yes. Now see here, both are on the same side. H. That's the cis isomer. Hope the concept is clear, students. I have picked up a lot of examples. So this is your nomenclature, that is your bond line structure, condensed structure, as well as skeletal structure. So thank you for watching, students. Stay connected and meet you again in the next concept, that is one more type of isomers to be written. To one more session of your isomerism concept. So in the previous video I've done the bond line structure, I've done the condensed structure, then I've done the skeletal structure of alkenes and as well as alkanes. Now not alkanes, I've done the straight chain structure for alkanes and condensed bond line as well as skeletal structure for alkenes. Now we'll be doing this concept. This is a worksheet again. Now let's see what is this question says. This is a quite common question in your CBSE. Done. Draw and name 12 isomers that have the formula C6H12. 12 isomers they've asked me to draw. Very nice, interesting. Let us draw this. They've asked me which is the formula C6H12. Now I'll pick up a different plain sheet so that this is visible to you all. I picked up sheet like this so that all the structures are here. Fine. So let me take this. Yes. Let me adjust my lens. Yes. Yeah. So first, what is the thing? 12 isomers I need to draw. Let me take the formula. It is C6H12. The first basic isomer which I can draw is start with 1. This is hex, no? Hex, because it is C6. But according to formula, CnH2n only. What is CnH2n? It is a general formula for alkene. Done? So the first one. I can write 1 hexene. 1, 2, 3, 4, 5, 6. First. So name it as 1 hexene. Now, second, shift 1 hexene to this position. 1, 2, 3, 4, 5, 6. Now this becomes 2 dash hexene. Don't forget that dash. Second isomer. Now I need to write 10 more isomers. Let me shift the page above. Yes. Now shift this second one to third position. 1, 2, 3. Now this is 3 hexene. Fourth one. Now over combinations, because hexene, whether I shift from here or shift from here, all the 3 are over. Now I have to be careful. Now shifting methyl groups. Now what you do, you shift this methyl group here. When you shift the methyl group here, it becomes, or this looks like this. C, one more C, one more C. Now you should not forget about the double bond. Where was the double bond? Double bond was initially here. So you can make it here. Now name it. It is 1, 2. So this is 2 methyl, 1 pentene, 1 pentene. Now what are we going to do? We are going to shift this methyl group from second position to third position, right? So shift it 1, 2, 3, 4, 5. A double bond from here also will shift here. Now name it. This is 3-methyl 1-pentene. Okay, yes. So here it is 2-methyl. Okay, let me make this as 1-pentene only. So later I can shift. So this one I'll shift this here only. So I'll make it 1-pentene. I'll shift 2-pentene later. How many over? 5 are over. Let me write the 6th one. Hope the page is clear, students. 6th one. I need to write total 12, isn't it? 6 more are left. In the 6th one, what am I going to do? This methyl group from here. So total are correct only pentene? Yes. Now from here, I'm going to shift this to this carbon. And the double bond will be there only. 1, 2, 3, 4 to this and this. Now this becomes 4-methyl 1-pentene. Try to make all 1-pentenes, then come back to 2. 7th. Now I'm going to shift. Now all combinations are over. Now I'm going to shift this double bond to second one. Till now it was here only. Now shift it to the second. Double and carbon here. Now this becomes 2-methyl 2-pentene. Okay, now carbon, every time this double bond will be here only, you will be shifting the methyl group. 8th one. Till now we have shifted methyl group and double bond was there. Now we will be shifting the methyl group, double bond will be there only. Right? Let's see this. 1. Now what 2 methyl we have written? We have written now 3. 1, 2, 3, this. Now double bond is here. Now this is 3-methyl 2-pentene. Now shift further. 9th one. From here I'll shift to this. 1, 2. Double bond will be there only. Second carbon. This is 4-methyl 2-pentene. Done. We'll write the 10th one. I'm left with only 2 more. 10, 11 and 12. Isn't it? Yes. Right. So 10th one when I have to write, I can write, yeah, this combination. See? C double bond C. Now I'm shifting 2 methyl groups above. So this becomes 2, 3 dimethyl 1-butene. Okay. 2, 3 dimethyl 1-butene. 11th combination. Now what am I going to do? This carbon I'm going to shift here. Basically you are trying all the possible ways. Shift. Name it 3, 3 dimethyl 1-butene. Last one. I'm going to shift the double bond was shifted second position, it was shifted first position. Now see here. I'm going to try the last one. This. Yes. This is 2, 3 dimethyl 2-butene. The students, done. So hope this is the concept. 12 isomers I've written for the given structure. Done? Right. So now what we'll do, we will try to take one more question of this and we will do. Let us take one more question. What did they give me? Next question, let's see. Right. Now, they've given me draw and name the isomers of C7H16. Isn't it? Right. And now what is C7? C7 is nothing but heptane or what we'll see in the formula. Okay. Here N is equal to 7. And let us substitute C7H. Okay, I think it is 2n plus 2. That is CnH2n plus 2. 7 into 2 plus 2. So this is C17. So C7H16. So this is an alkane. Now I'll take another page, students, because this is not. Now I'll write here. Now I need to write for C7H16. Draw and name also they've asked me to name it. I need to name the structures. Right. It's I said first of all try to write or leave it in a straight chain. Straight. Just go straight. Then slowly start branching it. First one. 1, 2, 3, 4, 5, 6, 7. So this is heptane 1. Now try to shift this one, this carbon to this. So this becomes 1. Or you can shift this carbon to this carbon. Okay, let this be here. Shift it to this one. 1, 2, 3, 4, 5, 6. What is this? This is 2-methyl hexane because it is only 6 carbons now. Now, what am I going to do? I am going to shift this methyl group to this. 1, 2, 3, 4, 5, 6. Now, what is this compound? This is 3-methyl hexane. Now, what am I going to do? I am going to shift this group also here. This will come here. 1, 2, 3, 4. What is this compound? 2,2 dimethyl pentane. Done? Just I've shifted the methyl groups because I need to write all the possible isomers, isn't it, students? Right. Now, next combination. From here, I'll be shifting this to this. 1, 2, this will be here only, carbon. Shift it here. This becomes 2, 3 dimethyl pentane. Right. Now, let me turn the page and take this. Next combination. 1, 2, this carbon, this, and this. 2, 4 dimethyl pentane. One more combination. 1, 3, C, and C. What is this? 3, 3 dimethyl pentane. One more possible combination. Let's see. Yes. So, what can I do? Yes, I can try this. 1, 2, 3. Yes. Yeah. This is 3-ethyl pentane. Last one. 1, 2, 3. This is 2, 2, again 3 trimethyl butane. Okay, students, right. So these are all the possible isomers of your C7H16. Done? Yes. This I'll take out this page. I'll take out this page also. Now, they've asked me to write the possible isomers for C4H10. C4H10 is nothing but what? Butane, isn't it? Yes. So basically C4H10, you can just write it as, like simple thing. It's very basic thing. Let's start with the first one. Normally, when I have to write butane isomer, right? You should have an idea what to write. I'll give you a clue here. Please practice by yourself. It will have 2 chain isomers. That is the C4H10. I will not do it because it's easy. I'm giving you a clue. It will have 2 chain isomers. One is N-butane and the other one is isobutane. So try it by yourself, students. It's easy. I'm already given a clue. You can just make the straight chain, then you can make the N-butane, that is N-butane is normal, then you can make the isobutane, almost your structure is done. But here, when you're writing combinations, I'll just tell you different types, how many you will be writing, how many types of isomers you get. So, thank you for watching, students. It's wonderful meeting you all. Any doubt, please let me know in the comment section. Stay connected. I'll meet you again with nomenclature of cyclocompounds. Right. So welcome back students to preparations of alkanes. So till now we have done a lot of topics in organic chemistry. Everything is kept in the playlist. Please watch that. I did nomenclature, I did hybridization, I did structure of this one, alkenes, alkenes and alkynes. Now I'm coming into the main concept of the chapter, that is your preparations. So starting from here, there will be a lot of reasoning questions which we'll be dealing with. We'll be doing one after the other. Please note it carefully, and my request is please watch the previous videos for better understanding of the chapter. So whenever I speak about alkenes, what is the general formula? It is CnH2n plus 2, isn't it? Now we are going to prepare alkane using Wood's reaction. So whenever name reactions are given to you, there are a lot of name reactions even in grade 12, almost 70 name reactions are there in grade 12. So what does the examiner want you to write? Basically, whenever you're writing a name reaction means specifically with the name. Just normally if it is like addition, substitution, like that, it is general reaction. But here, specifically if you have name reaction, you need to write the definition of that as well as reaction conditions of that, and find, as usual, you need to name the reactants and as well as the products. Done. So whenever I have to speak about Wood's reaction, first I'll write the reaction and then start writing the definition. Let's see. So first, for Wood's reaction, what is important? Important thing is I'm writing the general formula, then we will write the definition. Right. So for Wood's reaction to happen, I need a molecule called Rx. What is this? This is called alkyl halide. Okay, from where did I get this? Let me see this. So alkyl halide. Just come back. Now this is the basic methane. See alkane, CH4. See this one. Suppose if I take out one hydrogen from this, okay, I am taking out one hydrogen from this and I am going to introduce a halogen to this. Then this becomes alkyl halide, okay, done. I have taken the same thing instead of this whole R and X. That's what I have taken. Now I have taken one here, one more I am going to add on this side. In between these two, I am adding sodium metal. Because two molecules are here, I am adding sodium also. Done. This whole reaction occurs in the presence of a reaction condition, that is ether, dry ether. Now what happens? Initially X with sodium, it comes out as 2NaX, and what is left out? This alkyl group and this alkyl group joins and forms RR. RR is nothing but alkane. Now let us take an example and see how can we write this. So instead of alkyl group, I am going to take, instead of this, CH3. This X is X. This sodium is 2Na. This one is again X. This is CH3. Now let me tell you what is this X. X is nothing but halogen. Here halogen can be either bromine or halogen can be iodine. Done. So instead of this X, let me write here iodine. In this case, let me write iodine. Done. So now what happens? There is a cleavage here. When will this happen? When you have dry ether present in the reaction, then only. Done. So what is the product? This CH3 and this CH3 joins and forms a compound. And what is left out? 2NaI is formed. Now let us name the reactants and products. I should name it, isn't it? Now what is this? I said alkyl halide. Now instead of alkyl, what is this group? This group, let me erase this off. This group is what? Methyl. This is methyl. Halide is what? Iodide. Methyl iodide. So both the cases methyl iodide. Now what is this? This 2 carbon atom alkane. It is called ethane, isn't it? One is methane, one is ethane. Second is ethane. That. Now I have written the reaction. Let me explain. Now how will I write the definition? Let me take out this whole thing and start writing the definition of Wood's reaction. Seeing this, nothing to remember, nothing to by heart. You can write it by yourself. Wood's reaction. Just see here. Start. When alkyl halide, right? So 2 molecules of alkyl halide. Okay. Done. When 2 molecules of alkyl halide, let's write definition. When 2 molecules of alkyl halide are treated with sodium, metal. What is the reaction condition? In the presence of dry ether. In the presence of dry ether to form, what is it forming? It's forming alkane with same number of carbon atoms. See here, there are 2 carbon atoms here, here also 2 carbon atoms, to form alkanes of same number of carbon atoms. It's called Woods reaction. This is the definition. Definition over, general reaction over, example, specific example also over. Now, hope you have noted this. This is also clear, simplest reaction. Now we will learn why have I taken sodium, why have I taken dry ether in the reaction. Yes, let's erase this and start. Now, basically, whenever you have learned the reactivity series, you have learned your reactivity series in grade 10th only, isn't it? So, we have studied in that series of metals which have placed according to the reactivity. Sodium, you place sodium, again potassium, like that. Last would be your copper, silver, platinum, like that, isn't it? Done. Now, when I have to speak about sodium, what is the role? Okay, let us not write use, let us write role. Role of sodium Woods reaction. Basically, I said sodium is a highly reactive metal. So, because of this reactivity, we have taken not higher, it is highly reactive metal. Done. Because of its reactivity, I've picked up, I've taken that and used it. We have used it in Woods reaction because it can easily take out halide from that. Now, what is the role of dry ether? Done. So, here you should know one important concept. What is the concept? Basically, we have solvents with different types of solvents. I've already made one flow chart also for you. But here, when we are speaking about dry ether, what is the basic concept? There are 2 types of solvents, that is polar protic solvents, and next one, polar opposite is non-polar aprotic solvents. Okay, right. Now, what are polar protic solvents? We will see first. Basically, whenever I speak about, let me number this is 1, number this is 2. So, whenever I speak about polar protic, basically solvents, that means these are the solvents which have acidic hydrogen in them, H plus ion, very important. So, what is that? They have acidic H plus. Now, this acidic H plus should be attached to which atom? It should either be attached to oxygen or it should be either attached to nitrogen. Like example, if I take the basic water, see here, oxygen attached to nitrogen, so it is a polar protic solvent. Next, nitrogen attached to hydrogen, because I said nitrogen, hydrogen. Ammonia is a polar protic solvent. Next, HF. This also you can write because electronegative atom. Done. Next, formic acid. Here what happened? Oxygen attached to hydrogen, polar protic solvents. So these are all polar protic solvents. Done. Next important thing, you should know what actually is non-polar aprotic solvents. Right. The same thing again. Non-polar aprotic solvents are those which do not have acidic hydrogen. Here they have acidic hydrogen, but here you're going to write do not have acidic hydrogen, acidic H plus, like RMGX, Grignard's reagent. I've done a flow chart for this already. Then your dry ether. What is dry ether formula? ROR. Here are you finding in H plus? No. Here it is directly attached to alkyl group. Such compounds are aprotic solvents, non-polar. Now, when I have to come back to dry ether, which category it is coming? It is coming under non-polar aprotic solvents. So, first important thing, sodium, highly reactive, it will replace halides. This being non-polar, it will not allow, means it will just easily take out, it will not allow the further degradation or further movement of that alkane. Movement means it will give us the required alkane. It will not further, because it is non-polar, it will not ionize anything. It can easily take out the required product, that is alkane for us. So, because of its non-polar aprotic property. That's the use of dry ether as well as sodium. Done. So, next important thing, whenever you are learning Woods reaction, what should you remember? Basically, Woods reaction does not support the formation of alkanes with odd number, means odd number combination it will not allow. What is the reason? Suppose basically I said CH3I plus 2Na plus ICH3 in the presence of dry ether. Simple, I can easily get alkane like this, CH3 and 2 NaI I can easily get. But suppose if I have an odd electron like this, suppose C2H5I and 2 NaCH3I. Now see here, 2 plus 1, 3 carbon atoms, isn't it? Right? Such combinations are not basically supported or preferred by the product, is not much preferred by Wood's reaction. What is the reason? Here what happens? The difference in boiling point, when I take the odd electron, when I see the series, the difference in boiling point is very, very less. When it is less, for me, separation of the required alkene will become very difficult. So that's why Wood's reaction will not prefer elements or the reactions with odd electron compounds. So ruled out, we can take odd even number, I can easily prepare. So what's the reason? Because the difference in boiling point is very, very less. Isolation will be very difficult, isn't it? Done. Next important thing you have to remember, methane molecule or methane cannot be prepared by Wood's reaction. Why can't I prepare Wood's reaction methane? Because for Wood's reaction we require 2 molecules of alkyl halide. So methane cannot be prepared by Wood's reaction. So students, this is your Wood's reaction, starting from the definition, general formula, reaction, uses of the reaction, means I have taught you what is the use of sodium metal, what is the use of dry ether, then I have taught you what is not preferred in Wood's reaction. Right. So next, preparation of alkenes. We've already prepared alkenes with Wood's reaction. Let's see what are we going to learn here. So basically I can prepare alkenes by reduction of halides. Okay. So suppose there's one reaction given to you. Ma'am, how should I write in the exam? What are the products formed when such compounds are given? Let's see how to analyze the question. Right. So whenever like in grade 10th you've already studied what is reduction process. What is reduction? Either it is addition of hydrogen or removal of oxygen, right? Or removal of an electronegative atom also. 3 things you have learned. Now I said reduction of halides. Which halides? Halides are alkyl halides. So in Wood's reaction I've already taught you what are alkyl halides, isn't it? Yes. So let's see. So first of all, whenever you are going to study about a reduction reaction, you require reducing agents for this. Without reducing agents, you can't perform the reduction process. So what are the different reducing agents which you should remember? Why are we writing this reducing agents? Because in the exam, whenever you see this reducing agents on the top of the arrow, that means your teacher or your mentor wants you to prepare or take out hydrogen from the given reactant. What are the different reducing agents? It can be palladium in presence of hydrogen, or it can be nascent hydrogen also. None. It can be zinc in the presence of HCl, or zinc in the presence of copper and ethanol. This is we call it as couple. Done. Right. And next you can also use like platinum, palladium. I have written all the combinations. Done. Fine. So here, whenever you see such things, some such metals on the top of the arrow, you need to do the reduction. Let's take. Now I'm taking an alkyl halide, for example, I'm taking CH3CH2Br. Done. Ma'am, why did you start with Br? You would have started with chlorine, isn't it? Because fluorine is highly electronegative. That we will not take. You would have started with chlorine. But basically, whenever I see the order of alkyl halide, RCl is least reactive compared to RBr, compared to Ri. So among reduction, the order is the highest one is Ri. Ri easily undergoes reduction because of its size. Next comes RBr. So this is least reactive. That's the reason I've started with bromine. Done. Now I said I can use any of these conditions. So I'm adding hydrogen in the presence of which one? Palladium as a catalyst. It is a reducing agent. Okay. Now what happens? I said this is a reducing agent. Removal of electronegative atom and addition of hydrogen to this is called reduction. So this is going to add. Now what will happen? CH3 here, CH3 here. What has come out? HBr. Done. What is this? This is ethane. Now what is this? This is 2 carbon atom. It is ethyl bromide. Isn't it? Done. So this is your reduction process. Simple, isn't it? Just add hydrogen. If you see this in the exam paper, that means you should add hydrogen to the given reactant and take out the electronegative atom. That is bromine. Suppose if I have to speak about zinc couple, what is that? We will see. Let me erase this part and give you the next one. I said zinc couple ethanol. Yeah, done. Now if I am taking that reducing agent, how is this? It's going to combined with ethanol like this, zinc plus ethanol on this side in this way. Right, so where is it? It's going to cleave. Just see here, exactly there's a cleavage here, exactly there is a cleavage here. So oh no, let me write this H here better. Yeah, exactly there's a cleavage here. So zinc couple, what happens first? It's going to form a complex. How is the complex formed? This is minus, this is also minus, isn't it? This is plus. So this is going to form a complex like zinc O. How many C2H5s are there? 2 C2H5s are there. Now what is left? 2 hydrogens, 2 nascent hydrogens are left. Now this acts as a reducing agent. Now take an example now, simple, which according to the order CH3, CH2, Br plus 2 hydrogens. So what will happen? One hydrogen comes out with this Br and the other hydrogen adds here. This becomes CH3, CH3, that is ethane, and what is left out? Your HBr is left out, same as earlier. So what is this compound called? This is called zinc ethoxide. So this is zinc eth oxide, and this is your required alkane. Right, this is over simple, isn't it? Now we will do one question based on iodine, very famous question for this particular thing. So that question will be doing it. Right, now let's see the next question in this particular reduction. So this is very famous question here. Let's read this. What is the role of red phosphorus in the reduction of ethyl iodide? Okay, they said whenever you're taking ethyl iodide, done. Let me take that ethyl iodide, done. You're trying to reduce it in the presence of red phosphorus. Okay, you're trying to reduce it in the presence of red phosphorus. What is the temperature? 423 Kelvin. Right. So first important thing you should remember, whenever there is, or whenever you're trying to reduce ethyl iodide, that particular reaction is a reversible reaction. Done. Now let's see what products are we going to get. I'm going to take HI. There's a cleavage of bond here, there's a cleavage of bond, hydrogen gets added and iodine comes out. So I'm going to get C2H6 plus iodine. Done. Now what happens? The role of red phosphorus, that is what asked me, right? So this red phosphorus, what happens? It's going to combine with this iodine and it will allow the reaction to go to the forward direction. Here what's happening? I said reversible reaction, but basically I want this product. I want ethane. Suppose if you are not adding red phosphorus here, the reaction starts in the reverse order. Again it will form reactants. This will go to the backward direction. So what is this role? First role is, when I have to write in the exam, role of red phosphorus, what is that? It allows the reaction to move in forward direction. This is the main thing. Okay, forward direction, done. What is the reaction now? This iodine, this phosphorus combines with iodine. So it's going to form a product called Pi3. Now let's balance this. Now 2, 3, 2. 2 phosphorus, 2 phosphorus, 3 to the 6 iodine, 3 to the 6 iodine. So when it's combining or when it's trying to form a compound, phosphorus triiodide, it will block iodine. When it's blocking iodine, what happens? The reaction proceeds only in the forward direction. It will not go back. Thus, we get the required product. So this is the question, and this is the reduction of alkyl halides. So hope you would have seen the order also. So students, let me meet you again with the next reaction. Right. Now, next important reaction, that is we are going to prepare alkanes from acids. Now, what actually is this reaction? Let's clearly understand one step after the other. So, till now we have learned 2 reactions. One is Wood's reaction, and after that I've taught you what is the reduction of alkyl halides. Done. So, here in this reaction from acids, I said. So, normally we have studied carboxylic acids, isn't it? Done. Here, I am going to use an important compound called soda lime. Okay. Right. What is that? We will write from. Okay. Let us not write from. We will write with soda lime. Okay. What is soda lime and which acid we are taking? Let's see. Soda lime basically is a combination of NaOH plus CaO. This is soda lime. Here we are going to take a ratio of 3:1 combination for the reaction. Here, first of all, whenever I say this reaction, I am going to take a compound called CH3CONA. What is this compound? Here, if I go back to this, I am cleaving this bond. Yeah, just see here, HOH. What is this? This becomes a CH3COOH plus NaOH. This is the parent atom from where it's coming from acetic acid plus a combination of a base, that is sodium hydroxide. With the removal of water, I get this compound. So this is an acid. So that's why I said we're preparing from acid. Now, when I come back to this compound, let me erase this so that it is not confusing you all. CONA. I'll take out this precursor also. Done. Now I've got this from an acid. So how should I name this acid? This is called sodium acetate. Okay. Normally we call it as carboxylate because acetic acid does come from acetic acid. I can call it as sodium carboxylate. Okay, what are carboxylate? Carboxylate basically are carboxylic acids. Basically, they're not a separate class of compounds. We give this name to compounds which have generic name like, as I said, acid, RCO minus, esters, RCOR, like this. For that, we give carboxylates, that particular name. Done? Right. So now, sodium acetate I'm going to take soda lime in a ratio of NaOH plus CaO. Okay. Now, this whole reaction, let me write like this. This is CaO. What ratio I've already written. So, when you're taking, what is the role of soda lime? It will keep the reaction dry. It will take out the moisture from the reaction. So, when you're taking, just see here, Na2CO3. Till here it's going to come out. What is going to come out? Na2CO3. Now what is left? This hydrogen goes and adds to the reaction. So that is CH3 plus H. Okay, can I write this as CH4? What is the name of this compound? This is methane. What are you observing? Whenever there is a reduction, whenever there is the formation of acid. So basically, this is the formation from alkenes from this acid. We are getting one carbon less, isn't it? So we have learned the reaction, that is, here I am taking sodium acetate, but here there are two carbons, but the product form is one carbon less. Done. Let me take one more example. So in the exam, you should remember Uts reaction, you will get two carbons, same carbon, same two carbon atoms, but here one carbon less. Let me take here, instead of this, C2H5CONA, now sodium hydroxide, that is soda lime, which makes the reaction dry. CaO, what do you get? Na2CO3 taken out. What do I get? Na2CO3. Now the leftover C2H5 is, this is C2H6. See here. Here 2 plus 1, 3 carbons were there, but in the product only 2 carbons are there. So what is the name of this compound? It is ethane. So whenever you're doing this type of reaction, you will get 1 carbon less alkane. Suppose if I take the third one. Here now I'm going to take a benzene ring. CONA. Sodium benzoate. Yes, right, carboxylate, as I told you earlier. Now I'm going to take NaOH and I'm going to take CaO in the presence of 3:1 ratio. Now take out Na2CO3. Okay, I should take C also. Na2CO3. This hydrogen comes and adds here. Now what do I get? When it adds, you're going to get benzene ring. This is your benzene, because that hydrogen is added, and what comes out? Na2CO3. This is a reaction. Now let's come back and see the next type of decarbonation. This is basically you're taking out carbon dioxide, isn't it? So this is carboxylation reactions or decarboxylation reaction. Now we're going to see one more electrolytic method, that is called electrolytic method after this. Right. Now we have seen already soda lime decarboxylation in the previous reaction. Now we are going to see electrolytic decarboxylation. That means you are removing out carbon dioxide. D means removing, carboxylation, that is removal of that carbon dioxide in the form of a vapor or the gaseous state. Done. So in Kolb's, or what is the name given to this electrolytic decarboxylation? This is called Kolb's electrolytic method or Kolb's electrolysis. Okay. Whenever I say electrolysis, that means you have an electrolytic cell. In that you have an anode and cathode kept. After the electrodes kept, you have an electrolytic solution also in that. Fine. So in that electrolysis process, or in Kolb's electrolysis, basically I said we are going to prepare alkanes from acids. And what do we learn in soda lime decarboxylation? There we have picked up carboxylate, isn't it? Sodium, acetate, sodium acetate we have taken. Here in the same case, I am going to take potassium acetate. Done. What is that? Suppose if I take a general reaction, just see, I am taking a general reaction, we will understand carefully. What am I going to take? I said acids, the precursor, means we are getting it from the acid, acetic acid which we have written. That means here I am going to take RCOO potassium, that is, see, instead of Na, I am going to take potassium. But here what am I going to do? I am going to take 2 moles of that. Now here electrolysis process means in the presence of water. Without water there is no movement of ions, isn't it? So I am going to add HOH. During electrolysis process, when the current flows, what happens? Just see the cleavage, how does it cleave? First of all, there is a cleavage exactly here. After that, just see, there is a cleavage here, there is a cleavage here, yes. So let us write the products one after the other. R, 2R, R and R. After that, carbon dioxide, how many? 2 carbon dioxides, 2 CO2, 2 O. This potassium combines with H. How many are there? 2. So 2 KOH. After that, what else is left? Hydrogen, isn't it? This hydrogen gas or this comes out as H2. Fine. This is your reaction. Now what actually is happening inside the electrolytic cell, we will see. In the electrolytic cell, we have 2 electrodes. One is anodic electrode, where oxidation happens always, and cathodic electrode where reduction happens. Now suppose instead of alkyl group, here I am going to take this as CH3COOK. This one I am representing like this. Done. Now when it breaks up, how does it break? It breaks up into CH3COO minus plus K plus. Done. Now I'm going to take this at the anodic part. Now see here I am going to only take 1 mole. Here I have taken 2, 1 also you can take, then show with 2 electrons. So take the CH3COO minus here, 1 electron. Done. Oxidation, loss of electrons. So when this is there, it's going to form CH3CO minus free radical. Free radical. Done. Now what happens? The CH3CO minus free radical further dissociates. There's a cleavage of the bond here, and this becomes methyl free radical and carbon dioxide is out. So carbon dioxide is evolved at the anodic compartment. Remember that. After that, now next stage. What is the next stage? Electrolysis process. These electrons from here, 2 means if I take 2 moles here, this will become 2 electrons. So those 2 electrons are picked up by water molecule. So I am going to take H2O, taken 2 electrons. Means because I have taken 1, done, but I am explaining you for 2 electrons. So when I take this, what will happen? Water molecule, this is like this, HOH. There is a cleavage, so I have to take 2 electrons, means 2 water molecules. So this becomes 2OH minus plus hydrogen gas. So hydrogen gas that is evolved at the cathode, carbon dioxide gas is evolved at the anode. Now what happens to this free radical? This free radical combines with 1 more methyl free radical and forms an alkane, CH3, see here, this alkane is formed here. Now let us cross check. Acetate is this one, which is already broken. At the anodic compartment, carbon dioxide I have got as a product. Here at the cathodic compartment, this free radical combines with 1 more forming alkane. And these 1 electron, if I take 1, if I take 2 here, this will be 2 electrons. These 2 electrons loss from the anodic compartment goes to the cathodic compartment. It is picked up by water. So 2 hydrogen comes out as hydrogen gas. This 2OH comes out as 2OH. Whereas this OH goes, this potassium whatever is there, K plus OH minus becomes, it's 2OH, right? So this becomes KOH, that is 2KOH. So this is your Kolb's electrolytic method or Kolb's decarboxylation reaction. Alright, now let's come back and see the next preparation of alkanes. So very interesting reaction here. Let's see. Here we are going to prepare alkanes by reducing the COOH group of fatty acid. The long chain fatty acid is there, whatever long chain fatty acid which we are going to take, that particular carboxylic group or the COOH group from there we are going to take out, we are going to reduce it to prepare an alkane. Right. So before going into that, reduction, whenever you see reduction, I said you need to use or you should have a reducing agent present in that. So basically in chemistry we have two categories of reducing agents. So when I say reducing agents, so remember this. So we have two categories, type 1 category and type 2 category. What are they? Type 1 category reducing agents are like lithium aluminum hydride, sodium borohydride. So what do they do? Basically type 1 category reducing agents, they are going to always reduce. Suppose if I take an aldehyde like this, they are going to reduce aldehyde into primary alcohol. That means what is this primary alcohol? It is nothing but RCHOH. What happened? R is here, C is here, H is here. This particular thing, reduction is nothing but addition of hydrogen. The bond is broken and hydrogen is added. So what should you remember? Whenever you have such type of reducing agents, aldehydes are going to get converted into primary alcohols. Suppose if you go with the second category of reducing agents like zinc amalgam HCl, or when you take reducing agents like your HI, what do? They are going to convert ketones, RCH3COCH3. This is an aldehyde, this is a ketone. They are going to convert ketones into, what happens? This is going to break and it will convert into CH2, CH3. That means whenever there is a ketone like this, RCOR, okay, R prime if I take, this is going to convert into RCH2 in this direction, this way. It's going to convert into an alkane. Remember this. These reagents will convert the carbonyl group into primary alcohol. If you find HI or zinc amalgam HCl, you will get converted into an alkane. Right. Now I am going, with this basic data, I am going to start showing the reduction. So here, with which category now HI is belonging to? HI is belonging to category 2. Right. Suppose if I take a carboxylic, means that particular fatty acid, this one, I have picked up this acetic acid. Right, then you can also take like this. Now I'm going to add HI, isn't it? I said what is the HI category? It belongs to the second category, type 2 reducing agents, where the acidic group or whatever group is there, that particular thing, it's going to convert into an alkane. Now what am I going to do? I'm going to take 6 HIs. So just simple, I'm just opening up the reaction and showing you. This is not the exact way, but for your understanding, it's like this. Please don't go, this is not the mechanism, I'm just showing it to you. Now what happens? First important thing, see here, water molecule comes out, this H2 and O. Okay, you can take any way, like this H2O, this H2O. Right? Fine. So water. Now after this, how many iodines are there? 1, 2, 3, 4, 5, 6. These 6 iodines come out. Right here, how many hydrogens are there? This hydrogen and this hydrogen comes out with this oxygen. These 2 oxygens are there, isn't it? So how many H2Os? 2 H2O. Now count how many are over. 2 to the 4 hydrogens are over. 1, 2, 3, 4. Okay. Now how many are left? Basically 1, 2, 3, 4 are over there. I am left with only 3. So these 3 come here. Just see. 2 oxygens are over with these 2 oxygens. 1, 2, 3, 4. Okay, 1, 2, 3, 4. 4 are over with this. Now what is left? This is left as CH3, CH3. That's it. Simple, isn't it? Now what is important here? Here you are going to get from acid, you're going to get an alkane. We are going to reduce it, isn't it? I'm removing hydrogen. So reduction or removal or reduction of the COOH group of the fatty acid to form alkenes. So what is this alkane? This is ethane. So simple understanding, 1, 2, 3, 4, that is 2 water molecules with this oxygen. The leftover 3 come and add here, that's coming out as ethane, and iodine, 6 iodines, 3 2s are 6. Right. We've seen the different preparations of alkanes, isn't it? I've taught you different types of reductions. I've shown you electrolytic electrolysis process, decarboxylation process. So please go through all the reactions, keep noting it, and keep first understand the reaction, then you'll not forget it. Now we'll come back to the physical properties of alkenes. What is this question? Why are the first 4 members, that is C1 to C4 gases, C5 to means C1, the first methane, ethane, propane, butane, why are they gases, and remaining are liquids, and the higher members are waxy solids? What is the reason? So when such reasoning questions are given to you, you should just be clear in answering. Just give answer to the particular question. Very small, short answer, important keywords should be there. Done. So first of all, whenever I speak about alkenes, what bonds do they have? They have carbon-carbon bond and carbon-hydrogen bond. Done. Right. Here when I have to see the electronegativity difference between carbon and hydrogen. Carbon, what is electronegativity? The electronegativity of carbon here, it is 2.55. The electronegativity of hydrogen is 2.2 only. Now when the difference of both is very less, isn't it? You see, there is a lot of difference. They start dragging the electron, means they start try to pull the shade pair of electrons. When they try to pull the shade pair of electrons, ions are created, polarity is created. Now the difference in first important point, electronegativity difference is very less. Electronegativity difference is very less, isn't it? Minimal. When the electronegativity difference is very less, what will happen? Will it exist as a polar molecule? No, isn't it? So alkenes are non-polar molecules. Non-polar molecules. So when it is non-polar molecule, what will happen to the van der Waals forces of attraction? If it is polarity, that van der Waals forces of attraction exist between them. But because it is non-polar, so they have weak van der Waals forces of attraction. So because of this, what happens? There are no forces of attraction to make the molecule stay together as a solid. That's why, because of this weak van der Waals forces, the elements are far away. Means they exist as gaseous. The physical state is gaseous because there is no force of attraction between them. That's the reason. Because of this, you will write these 3 points. Then you will finish off saying that hence C1 to C4 are gases, C5 to C17 are liquids, the higher members are waxy solids. Right, now let's come back and see the next reasoning question. What do they give us? Why are boiling point of N-alkanes increase regularly with increase of number of carbon atoms? So obviously, isn't it? Now as a carbon change, say methane, ethane, propane, butane, pentane, like that, the number of carbon atoms are increasing. They're asking for higher alkenes, means whenever the number of alkene or the carbon atoms are increasing, the boiling point is, why is it increasing? What is the answer? How should you write? 4 important things. First, you're going to write, as number of carbon atom increases means what? Molecular mass increases because you're adding carbon atom, along with that hydrogen also adds. So as the molecular mass increases, what will happen? The intermolecular force of attraction or interparticular force of attraction, molecular force of attraction increases. Done. Next, when the force of attraction increases, what will happen to the magnitude of van der Waals forces? Those also increase because the forces are increasing. Magnitude of van der Waals forces increase. When the magnitude of van der Waals forces increases, they're very close, tightly packed. What will happen? automatically boiling point increases. Isn't it simple? So this is the important thing. You're relating it to the forces of attraction, then you're relating it to van der Waals forces. After that, you're finally writing, coming back to the question, this is the reason higher alkenes or increase in number of carbon atom increases the boiling point. That is what they have asked us. Right. Welcome back, students, to the next set of reasoning questions. We've been doing reasoning questions of alkenes. Now let's see the next set, because whenever you're doing organic, not only the name reactions, not only the preparations, most important are the reasoning questions. So let's read the question and see what are the keywords we need to write in the question. Right. So why do isomeric branch chain isomers have relatively low boiling point as compared to corresponding straight chain? Okay, so they've given us three important things. One is they said isomeric branch chain, then they said corresponding straight chain, then they said low boiling point. These three things I need to concentrate and write the answer. So what examples are given? And they're given me two things. One is isopentane and one is neopentane. What is isomeric? Iso means similar, mer means unit. Fine. Now when I take this, how many carbons are there in this count? 1, 2, 3, 4, 5. Done. Here 1, 2, 3, 4, 1, 2, 3, 4, 5. Both are having 5 carbon atoms, so isomeric. But what is the difference? They are differing in the arrangement of the methyl groups. That means in one it is a straight chain with one single branch. Here it is completely branched. Now when we observe the boiling point, here for the branched chain, the boiling point is very less, means compared to that it is 282.5. here it is 300.9. This is what they're asking us. They're asking us, why do isomeric branch chain isomers have relatively low boiling point as compared to corresponding straight chain or one branch chain? Now let us write. So whenever I see, so you need to start your answer explaining about this. What are you observing? Here in branch chain, what is happening to the surface area? Here, see here, they're arranged like this, one after the other. Whenever you have to boil them, you need to break this bond, this, and gradually you need to break each and every bond. But here what happened? All the molecules are arranged in a spherical form, isn't it? So let's start writing that. In neopentane, what is this? This is a branched chain. What happened? You should tell me. Yes, simple thing. In a neopentane isomeric branch chain, first important thing, surface area decreases. When the surface area decreases, what will happen to the shape of the molecule? Yes, shape of the molecule or shape of this particular thing, shape of the molecule becomes spherical. Done. When the shape of the molecule becomes spherical, what will happen to the magnitude of London dispersion forces? That magnitude also will go down. Magnitude means measure, right? So magnitude of, I'm writing in short form, London dispersion forces or the van der Waals forces, that also will go down. So here surface area is getting less, shape of the molecule becoming spherical, magnitude of forces also, here means it is strongly packed, forces also decreasing. So once it is attaining a compact structure, it will tightly fit in the crystal lattice. Yes, when they tightly fit, let us write that also. Tightly fits in crystal lattice. These are the 4 key points which you should write. Surface area, shape, magnitude, tightly fits. This gives you a complete analysis of the whole concept. So because of these reasons, hence the boiling point is low. That's it. If you write this and underline, you will get complete mark in such questions. So this is how you will do reason the question. Let's come back into one more reasoning question. Now let's come back and do two more reasoning questions here. Both are of the similar type. Let's read. What do they give us? Why does CH18, that is, it has a melting point of 216.2, have higher melting point than C3H8, that is 85.3? Okay, it is almost 3 times, isn't it? Fine. So why is it like that? Why do C8H18 has higher melting point? Always remember, whenever they give you a boiling point question, a melting point question, your concentration should directly go into the branching concept, right? So let's recollect again. Always higher the branching, more is the boiling point. That's the first important thing you should remember. Let us write that clue there. What is that? Higher branching means higher BP. This is for the boiling point. When I have to speak about melting point, same thing almost. What is that? Basically, whenever a molecule is compact in nature, right? Once again, I'm coming in the other way. What is compact? It is very closely packed. When it is closely packed, what will happen? Yes, the intermolecular forces of attraction are very, very high, very compact. Means I need to melt the whole molecule, break that molecule, open it up, and then only melt, isn't it? So in this case, when I see C8H18, so what is that in this particular thing? Now that we are comparing between C8H18 and we are comparing between C3 and H8. So in C8H18, we see it is 216.2. Let us write that 216.2. Now here it is 85.3. What is more in this? When I see the molecule, in the molecule, the compact nature or the close packing of that molecule is very much more. Here it is C3H8 only. It is like this: 1, 2, 3 hydrogens, 3, 2 and 3. It is like the straight chain, no branching. But here when it comes to C8H18, there's branching in the molecule. Point number 1. An important thing is, you should remember, very close and compact packing. Compact means very close in nature, very means less space in between them. Compact packing of crystal lattice So what will happen because of this? Melting point will be high. Boiling point, listen. So melting point will be very high compared to C3H8. Simple, isn't it? So whenever you're writing that, speak in terms of compact packing or close packing, so that you can easily write the answer end of your answer. Here in this case, what is this? In isomeric alkenes, that is N-pentane, isopentane, neopentane, we have seen the earlier question in terms of boiling point. Now when I see the melting point, see here N-pentane, it is 143 Kelvin, straight chain. Isopentane a bit branched, that is 113 Kelvin. When it is neopentane, it is 256.4. The same reason, isn't it? As a molecule or the branching increases, very close packing increases. When the close packing increases, compact packing of crystal also is there. When the compact packing of crystal is there, obviously the melting point will be low. I need a lot of melting point to break those bonds and melt them. Yes, so you can write the same reason for both the questions. Right. Now one more question based on your melting point of view. Let's see what is this. So here they've given based on melting point. Let's see the question and analyze how to write it in the exam. What do they give me? Among odd and even number of carbon containing alkanes, okay, which has lesser melting point and why? So here they've given me two things. One is they said you need to compare between odd and even number of carbon atom containing alkanes. So I need to take an alkane which is odd in nature and one more which is even in nature. Right. Suppose if I take an example like, yeah, let us take N. Okay. N hexane and N-heptane. Okay, let us take this example. This is a very common example, so I've picked up. So what is N? Normal chain. So let's write. So I'm writing in the bond line structure, which I've already taught you how to draw bond line structure. Start from here. Hexane means 6, isn't it? So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Done. Here heptane means 7, isn't it? Now start drawing. 1, 2, 3, 4, 5, 6, 7. Let's count. 1, 2, 3, 4, 5, 6, 7. Done. Hexane means 6 carbon chain and heptane means 7 carbon chain. Now what is important, I should see which is odd and even. This is 6 carbon, it is even in nature. Here 7 carbon atom, it is odd in nature. Now they want us to compare between odd and even. Simple. Whenever they have, you have a concept of melting point, remember one important thing. Boiling point means more of branching, more of boiling point. Point number 1. When it is melting point, very closely or compact packed, this one high melting point. Once again, more of branching, more of boiling point. Compact packing or close packing, more of melting point. Remember. Now they said between odd and even. Now see which is compact packing, which is compact packing. This one is even, means evenly, one after the other, second after the other, second after the other, everything will get packed. But here in this case, odd electron, after the 6th one, this will again be branching. Okay, this will again be branching and that will not fit into the crystal lattice. Yes, so important thing, here it is even and it fits in the crystal lattice. Let us write here, it fits into crystal lattice. When it fits in the crystal lattice, what will happen? Yes, magnitude also increases, the forces of attraction also increases, and here melting point will be high, because you need to break the lattice and separate that. But when it comes to N-heptene, I said it is an odd electron, and does it fit perfectly into the crystal lattice? Yes, it will not fit. So let us write that sentence also, does not fit perfectly into crystal lattice. When it does not fit perfectly into the crystal lattice, should I use more melting point? Not required, isn't it? So melting point, what I require will be less. Done? Let's write that. So it does not fit perfectly into crystal lattice, so melting point is, or it will be lesser. So that's it. Which is having melting point? Lesser is this. Now let's write the order. Odd alkanes will have less melting point than even alkanes because of this is the reason. Right. Now let's see one more question based on your solubility. Till now we have seen question based on boiling point and melting point. Let's read this. Are hydrocarbons soluble in water? Simple. So hydrocarbons, I know they are alkenes, alkenes and alkynes. So when does this concept of how do we write the answer for solubility? Whenever you're speaking about solubility, we think or we tend to memorize, okay, polar solvent, non-polar solvent. That is it. So what is that thing? We've always studied like dissolves like. That means polar solvent like dissolves like. Means polar solvent will, if it is a polar solvent, it will be dissolved in polar universal solvent, that is water. If it is a non-polar solvent, nature is non-polar, then it will dissolve in non-polar solvents like carbon tetrachloride, acetone, kerosene, like that. Done. So what in hydrocarbons, what is the concept? When I take this hydrocarbon, so let us write that in hydrocarbon. Let us take one example, any example. So let us take, this is hydrocarbon chain. Okay, here you have hydrogens. Now what is this? When does this molecule dissolve? When it breaks up into ions, isn't it? When does that break up into ions? When you have a difference in electronegativity. Done. When I take the electronegativity of carbon, it is 2.55. Here for hydrogen it is 2.2. Now when there is no electronegativity difference, the drag or the pull of those particular atoms will reduce, isn't it? So the difference is very less. If the difference is more, it would try to drag the electrons towards it and create a positive negative charge, and this will become a positive charge. Whichever is dragging will become a negative charge, whichever is losing will become positive. Means deficient. So here in this case the difference is very less. That's the first most important. Electronegativity, En means electronegativity, difference is very less. When the electronegativity difference is very less, does it exist as poles, positive and negative? No, isn't it? Yes. So since, let us say, since electronegativity difference is very less, what will happen? The molecule or the hydrocarbon molecule, whatever is there, I've just taken an example, whatever is there, it exists as non-polar. If it has electronegativity difference more, it will exist as polar molecule. That means two poles, negative pole and positive pole. Due to this concept, they or hydrocarbons exist as non-polar molecule. So when hydrocarbon exists as non-polar molecule, what will happen? Just now I said polar solvents will dissolve in polar molecules will dissolve in polar solvents. Non-polar molecule will dissolve in non-polar solvents. Simple, isn't it? Done. Now we have already come to a conclusion. It is non-polar solvent or non-polar molecule. So they are insoluble in water, and are soluble in non-polar solvents. Like, what are they? Just now I said cis carbon tetrachloride, acetone, what do you say, kerosene, diesel, benzene. Okay, this is your answer. So your teacher expects you to write this word, underline this word, then you can write hence or hydrocarbons exist as non-polar, underline this word, and you can underline this word, put it in inverted commas like this, and this also in a box. That. Alright, now let's come back and start the chemical properties of alkanes. Done. So till now we have seen reasoning equations, we have seen the preparations of alkanes, we directly jumped at chemical properties. Now basically alkanes are called paraffins. Param means what? Little. Affins means reactivity, little reactivity, because it is non-polar in nature, we studied, isn't it? That. But in spite of that, it's going to show all these types of reactions, very, very important reactions. Let us learn one after the other. Let us see the reasoning equations also in this, and then note it. So I always request, whenever you're noting something, try to maintain a separate notebook for World of Chemistry, so that all the reasoning equations, whatever I give you, keep noting in that. That. So alkanes, as I said, they're going to show halogenation reaction, combustion reaction, controlled oxidation reaction, isomerism, stream reforming, crackling and pyrolysis, and aromaticity. We will see all the reactions one after the other. When I take the first reaction, halogenation reaction, these are also called substitution reactions. Okay, substitution reactions. So we have different types of reactions in chemistry, isn't it? Addition reactions, substitution reactions. When you're in grade 10, you have studied combination reactions, displacement, double displacement. So now this is again a different class, addition, substitution. In that again we have electrophilic, nucleophilic, different types of reactions. Now I've taken the basic substitution reaction, that is halogenation. So what if I have to write the definition of this? Halogenation is nothing simple definition. It is a displacement, or it is a replacement of a hydrogen by a halogen. Let us write that. The definition of halogenation is replacement of halogen. Halogens are nothing denoted by X, isn't it? X can be fluorine, chlorine, it can be iodine, also bromine, iodine also. Done. Yes, we will see in that variations. So replacement of halogen with hydrogen. So here how much will be the replacement? 1:1 ratio. Remember that. That means if you are removing one halogen, if you are removing one hydrogen, or automatically one halogen should be removed. Done. So next important thing what you should remember is, in halogens also, as I said, what is the criteria for reacting? What is that order? Very important order. Order is fluorine, when it undergoes halogenation, it is a highly explosive reaction. Yes, so fluorine reactivity is the highest among all the halogens. Next comes chlorine, next comes bromine. Okay, this is the order. Now, if I have to see with what ease I can take out the hydrogen, I said one halogen will replace the hydrogen, which will participate more faster. Again, the same thing here. Tertiary, it is easy for me to take out. Then comes greater is secondary, then comes primary. Hope you would have studied what is tertiary, secondary and primary in your school already. So the ease is tertiary hydrogen I can replace with chlorine, then comes secondary, then comes primary. Done. Now I said why fluorine? What actually is that in this particular thing? Whenever I have fluorine reactions, let me make one more table here. So whenever I have reactions with fluorine, whenever I have reactions with chlorine, whenever I have reactions with bromine, I said bromine iodine we will write. We will not write Iodine we will write. We will reason why bromine is not written. Yeah. So iodine we will write. Done. So when I take fluorine, I said it is a very explosive reaction. We will see the reaction also very soon. So here it is highly explosive. Shall we write that? Yes, it is highly explosive. Okay. Right. So now when I take chlorine simple halogenation I can do. That is by free radical halogenation reaction. Free radical halogenation, I can easily do it. So halogenation, N I'm writing. When it comes to iodine, if I have to do the iodination, means replace that halogen with a hydrogen, I'm going to use some oxidizing agents like HiO3. Use of oxidizing agents like HiO3, right? Now we will see the reactions for all one after the other. So take your next page and start writing substitution reactions or halogenation reactions of chlorine or chlorination reactions. Right. Let's start with the first reaction, that is halogenation reaction. So that halogenation reaction always proceeds through free radical mechanism. We will see. So that free radical will be showing the generation of free radical every time. So let's see how to start. But here the halogen which I am going to take is chlorine. I said fluorine, the reaction is very explosive. For iodine, I require oxidizing agents like nitric acid, hydroiodic acid or HiO3 also. Now I should not say hydroiodic acid, okay, HiO3, HNO3, done. So here when I speak about the halogenation reaction, that is, I am going to take chlorine, that's why it is called chlorination reaction. So what is this? This chlorination reaction and this, first important, let us write the first reaction which we have to learn, the main reaction. Here I am going to take a hydrocarbon, that is alkane. So the alkane which I am going to take, the basic one is methane. So this methane I am going to add chlorine. Chlorination is addition of chlorine and replacement by one halogen. So it's chlorine diatomic. This whole reaction, whenever you are speaking about free radical, this will occur or it requires sunlight to be there. In the presence of sunlight only free radicals are produced. There is a cleavage of this bond. Now here I said one chlorine and one hydrogen will be replaced. That means if I have to write this, it is something like this: methane, methane, methane. So one hydrogen will be replaced by one chlorine and this chlorine comes here. What do I get? I get CH3Cl plus HCl. Done. Ethyl chloride. So this is a basic reaction. So simple, instead of writing the whole thing, what will I do? I'll just make a box here and I'll write CH4 plus Cl gives me one hydrogen has come out and the other HCl has come this. This is the main reaction which we should know. Now this particular reaction is shown, or you need to study under different steps. What are the different steps? It's going to follow chain initiation reaction. Next, it will follow chain propagation step. Let us write initiation reaction now. Chain initiation step. Next is chain propagation step. Then chain termination step. So this particular thing follows in three different steps. We'll see that. So when I have to start with the chain initiation step, okay, let us erase everything now and start writing the chain initiation step. So initiating means you see how to start the reaction. So what do we say? It is following free radical mechanism, we said, right? So here when I speak about chain initiation step, most important thing is we have three bonds, basically carbon hydrogen bond, carbon carbon bond and chlorine chlorine bond in the earlier one, isn't it? But here I have taken only methane, so we have only carbon hydrogen bond, Cl bond. Now which one is stronger compared to these two? Here there is no electronegativity difference. Here there is a bit little less electronegativity. So here zero difference, here there is electronegativity. So the bond here is stronger compared to this. That's why this only will break. Done? Yes. So for chain initiation, you are going to just form, or important thing is formation of free radical. Okay. Which one free radical we are forming? We are trying to form the free radical of chlorine. Done. That is Cl and Cl. I said for free radical mechanism, what do you require? You require sunlight. We require sunlight, that is H nu. In the presence of sunlight, there is a cleavage of the bond and you get chlorine free radicals like this. And maybe I'm not writing L properly. Chlorine free radical, one more chlorine. So generation of free radical is over. Done. In the second step, when we start writing chain propagation step, isn't it? So let's write that. Let's make this chain. This is chain propagation step. In chain propagation step, what you should remember is now the chain should increase in length. Done. So what is this? Here we have written formation of free radical. Correct. Now what one more is? Now after that bond, what is the next one? Formation of methyl free radical. Let us write that. It is formation of methyl free radical. This is the second step which you should remember. First step is chloride free radical because there is no electronegativity difference. Next is formation of methyl free radical. How to form? Suppose if I take 1, 2, this is methane like this. Yes. Now what do we have? We have chlorine free radical which is formed, isn't it? So this chlorine, this particular thing, you write it as free radical also. So this first important thing, this free radical whatever is there, this particular thing is going to pick up this hydrogen. This comes out as HCl. But what is important, before breaking and forming, I should form a free radical, isn't it? So let us erase this and write. So what actually is this? Let's see. Right. So how will I form methyl free radical? Let's see. If I take methane here, H and H, I already got the free radical, isn't it? I'll pick that free radical like this. 1. So now what happens? This comes out as HCl, and what will happen? This breaks the bond here and we get methyl free radical in this case. So 1 and dot. This is the indication of free radical. So I've got methyl free radical, isn't it? Now further what happens? This methyl free radical, whatever is there, if I treat this with Cl and Cl like this in the presence of light, so this will lose out HCl again and this becomes CH3, H and Cl. So this goes on again and again till all the hydrogens are replaced. So this is the propagation step. We'll do one after another lot of reactions in the propagation till we lose 1, 2, 3 hydrogens. Right. Now further, just see the propagation step. What did we get in the earlier product? We have got this compound CH3Cl, methyl chloride. Now what happens is the chlorine free radical which was there earlier, isn't it? We had that chlorine free radical in the earlier reaction. Yes. So this is going to attack this methyl chloride, and as I said, this free radical very highly reactive, fast reacting species. It will pull out or replace one hydrogen from here. So when it replaces, I get CHCl. So this one will become CH2Cl. Isn't it? One has come out with this hydrogen as HCl, one hydrogen is CH2Cl. This will become this free radical now. Now in the second step, the same CH2Cl you will take with the free radical. This is going to again react with one more chlorine. As I said, as the bonds are weaker, now what will happen? Immediately this particular thing, just see this and this is there, isn't it? This is broken, so this will come out as Cl free radical. This is one Cl free radical used, Cl free radical again released for the next reaction. Now what will happen to the product? Add these two, CH2Cl2. Now further, this CH2Cl2, now this is one set of reaction. Now the same thing will happen. So instead of this, now I'm going to take the next set. CH2Cl2 again is going to combine with Cl free radical. Now what will this do? Fast reacting species, it will pull out one hydrogen. It will become HCl. What will happen to this compound? It will become, instead of 1, it will become CH. Right. Now one chlorine has gone out with this, isn't it? This chlorine has come out with this hydrogen. So what are we left with? We are left with CHCl2. Further, I said the same thing here. This will become the free radical. Now take that. See here, one hydrogen is decreasing. See, okay. CHCl2 free radical now combines with what? Cl and Cl. Again there is a cleavage of the bond. This free radical is out for us. One time HCl, one time free radical, one time HCl, one time free radical. So when this is breaking, this adds up to this. This becomes CHCl3 chloroform. Done. Next step is followed. So what is the next set of reaction? So take that CHCl3. Again you have the free radical which is there. It will combine with that. So what will happen, as I said, whenever you're using free radical, remember HCl has to come out. One H from here will come out as HCl. What will happen to this? This will become CCl3 free radical. Now that CCl3 free radical, whatever is there, again one more chlorine reacts, there is a breakage of this one, and finally I get free radical Cl, and this will add to this and I get CCl4, isn't it? Yes, so this is carbon tetrachloride, methylene chloride, chloroform, carbon tetrachloride. These are the propagation steps. So simple, remember, always one free radical, one molecule, one free radical, one molecule. Start with free radical, last end it with molecule. Then after here, HCl1, Cl1, HCl, Cl, HCl and Cl. Step by step it is losing hydrogen and replaced by chlorines. First we have taken CH4, now it has become CCl4. Now let's come back and finish off the halogenation reaction, that is chlorination with the chain termination step. So what did we learn? Chain initiation, that is formation of chlorine free radical, chain propagation, formation of methyl free radical, then chain termination. Let's see. So here in chain termination, basically it is combination of free radicals, combination of two free radicals. Done. So what are the two free radicals? We'll see. So it's simple. So chlorine free radical 1 combines with one more chlorine free radical and forms a CCl, 1 over. Next one, methyl free radical which we have got combines with one more chlorine free radical. It's a combination of two free radicals. They'll become CH3Cl. Now what is the last thing which we are trying to form? That methyl free radical, whatever is there, combines with one more methyl free radical to form an alkane. Okay, let me write this H3 here, form an alkane. So this is your ethane. So this is how it terminates, finally forming molecules. Right. Now let's see one more question, that is based on iodination. Till now we have seen halogenation, that is chlorination. Then bromination also, it will be almost the same, but slowly it will take, not as fast as chlorine. After chlorination, bromination, next comes iodination. So what about fluorination? As I said, it is a highly explosive reaction. We will see that also. So you will always watch in YouTube when you type fluorination reaction. You can see a wonderful video which shows an explosive in the lab. Okay, here in this case, let us read. Why is iodination of alkenes via free radical mechanism not possible? Why is it not possible? They're asking. Simple. So when I have to speak about iodination reaction, that means addition of iodine to alkane. It is, I'm taking an alkane like this, CH4. Now what will happen? This reaction, how does this do? There's a cleavage of the bond. This HI comes out and this I comes in link. This will become CH, HI plus HI. Correct? Yes. Now this such reaction or this particular reaction is a reversible reaction. So forward and backward. Suppose if I don't take out, means if I don't use any reagent or something there here, this particular HI, it will go back and it will get converted to the backward reaction, that is iodine again. But we want the forward reaction, isn't it? So what are we going to do? We are going to use oxidizing agents here. So the oxidizing agents which I am going to use, here is HiO3 and HNO3. So what we'll do, we'll take this, because I need only forward reaction, not backward. We will take that HI and add HiO3. We will take the same HI and we will add HNO3, nitric acid. So in both the cases, the products are almost the same, just like this, H2O and we need to balance the reaction. Iodine here also, H2O plus iodine plus what is there? Now NO3 will become NO2. So we need to balance. So what will happen? Because of this, we will only allow the forward reaction so that we get this product. So what will happen? We'll write this will allow only forward reaction. That's it. Right. Now let's see this. So chlorination we have seen, bromination we have seen, iodination we have seen. Let's see fluorination question. Why is it difficult to control fluorination reaction of benzene, or direct fluorination of alkane is not permissible? Permissible, why it is not permitted or not allowed? Why? Right. So fluorine, that is a concept. Let's start from there. So when I speak about fluorine, so atomic number 9, 1s2, 2s2, 2p. Let us write that. It's 9, 1s2, 2s2, 2p, 4, 5, 6, 7, 8. Okay, this is 5. 1, 5, 6, 7, 8. 5, 6, 7, 8, 9. Done. So are you not finding one lone pair of electron here? That is the main thing. So what happens? First important thing, fluorine has a lone pair. Okay. Next important thing, what is that? The atomic size of fluorine is very, very small. Okay, that. The atomic size is very small, and what will happen? The lone pair repulsion will increase. So lone pair repulsion increases. So when the lone pair repulsion increases, what will happen to the bond dissociation enthalpy? Automatically the bond repelling, isn't it? Okay, let us write lone pair repulsions increases. So bond dissociation enthalpy of this automatically will become less. When the bond dissociation enthalpy is less, what will happen to the reaction? It will be an explosion, isn't it? Reaction is an explosion. Explosion, isn't it? Yes. So what actually is the reaction with methane? Let's see. These are the main reasons. So what will happen when it reacts? Suppose when I take methane, as I said, it is an explosive, CH4. Here I am going to take 3 fluorines like this. When I take, what will happen? Just see, this this carbon and this fluorine will combine as CF2. Now what is left out? This hydrogen, and still we have fluorines, isn't it? F. Now count how many are there? 4 hydrogens, 4. Okay, F. That. Now count 4 plus 2, 6. 3 2s are 6. Hydrogens 4, carbon 1, 4. Right. This is what is causing the explosion for fluorine molecule. Because of these reasons, the reaction or the fluorination reactions are highly explosive in nature. A lone pair presence. Next important thing, atomic size is small. Because of that, bond dissociation enthalpy is less, means automatically the reaction is very fast and it is an explosive. Then, and next important thing, what you should remember, when I conclude the fluorination, iodination on all these reactions, let's see what is the conclusion for all this. So as I said, fluorination with methane. Let us summarize the halogenation reactions. So summary is methane plus fluorine is, what is that? It is an explosive reaction. Just now I told you the reason. Methane, fluorine, chlorine. It is easy to form, so it undergoes free radical mechanism or free radical halogenation. When I take bromine, it is also free radical but very slow reactions compared to chlorine. Last but not the least, when I take iodine, there is no reaction only. I told you, isn't it? It is a reversible reaction, it goes. So we prevent it using the oxidizing agent. So forward, directly it will not combine, but I said we will write no reaction, no, we will write use of oxidizing agents. What are the oxidizing agents which we have taken? HiO3 and HNO3. So we've already seen halogenation, we have seen combustion reaction. Let's come back to see oxidation reaction. So here there is one important thing, controlled oxidation. Here we are going to add oxygen with limited supply of air. So oxidation, what do we know? Addition of oxygen. Here what you should remember is, when we do controlled oxidation, alkanes may be converted to alcohols, alkanes may be converted to aldehydes, alkanes may be converted to acids also. So let us see. So for such reactions we require catalysts, very important. So catalysts, what do? They enhance or speed up the chemical reaction, isn't it? So the catalyst which I'm going to use here is copper at 523 or 25 Kelvin, 100 atmospheres pressure. And I'm going to use one more catalyst. What is the name of this? MO2O3. Just see, this is called, let me write, molybdenum sesquioxide. Molybdenum sesquioxide. Next catalyst which I'm going to use is CH3 taken twice, Mn. Okay, this is manganese acetate. Next catalyst, silver oxide. Apart from all these catalysts, we are also going to use limited supply of air or oxygen at high pressure. So next important thing, limited supply of air or oxygen at high pressure. Correct? These are the things. Now let's see the reaction. So suppose first one, when I said I'm using these catalysts, isn't it? Now first I'm going to take the basic alkane, that is methane. Here I'm going to use, okay, let me take like this, C, H, H, H and H. Here I'm going to take 2 moles. Now what am I going to do? I said limited supply of oxygen, so I'm going to use the catalyst copper at 573 Kelvin, 100 atmospheres, shows 75 Kelvin. Right. So now what will happen? Oxygen, I said oxidation. So oxidation, when I do, okay, O and O, O2, limited supply of oxygen. So what happens? Let's see here, there's a cleavage here, isn't it? Yes, this becomes CH3OH. Once again, there's a cleavage here, CH3OH. So what will we get? We get a CH3OH, methanol, 2 moles. Again, 2. Let's count. Carbon are how many? 2 here. Here also 2. Hydrogen are how many here? 3 2s are 6 plus 1, 7. If I see this, 1, 2, 3, 4. Okay, everything is, this one isn't it? So is a 7. Let us see, 3 2s are 6. 7, 8. Okay. Now 1, 2, 3, 4. 4 2s are 8. Done. Oxygens are 2. Here also oxygens are 2. So what is this? This is a conversion of alkene into alcohols. So this is methanol. 1 carbon. Now suppose if I take the next catalyst, the second catalyst, that is your molybdenum sesquioxide. Let's take. Now here what am I going to do? Again I'm going to take an alkane. Just see here, H and H. Again it is limited supply of oxygen and I'm going to use MO2, small o. First is capital, second is small. Now what happens when you do this limited supply of oxidation? Just see here, in this case you get a product like this, oxidation, isn't it? H, C, H. There's a cleavage here, H, C, H, O and H2O. Okay, right, let us write that. HCHO plus water molecule. So what is the name of this compound? This is called formaldehyde. Formaldehyde. So we have come back to alkanes to aldehydes in the specific. In the exam you should remember, in the presence of this you get alcohol, in the presence of sesquioxide you get aldehydes. You should remember the reagent and go. Right. Now we have seen what actually concept of controlled oxidation using which catalyst. I've used both your molybdenum sesquioxide as well as copper. Now let's see two sets more. What are they? I said I'm using the different catalysts, isn't it? Now here I'm going to convert, just see here, we are going to convert long chain alkenes into fatty acids. Okay, that is done. And one more thing, here I'm going to convert, but here I'm going to use a different reagent. The reagent which I'm going to use is manganese acetate. Manganese acetate or silver oxide. Now, next important thing, the last type of oxidizing agent which I'm going to use is, here in this case, I'm going to convert or use KMnO4, which is an oxidizing agent. It helps in oxidation. Right, let's see. Suppose if I take this, what is that long chain alkane? If I have a long chain like this, N, what is this? It's repeating and repeating and repeating. The chain, it goes on like that. Suppose if I'm using this catalyst, that is CH3, CO taken twice, Mn, and AgR, silver oxide, and heat. Then what will happen? This particular thing, there is a cleavage of the bond here. We are adding oxygen, isn't it? Yes. So when this particular cleavage of the bond, and this goes and adds here because oxidation, isn't it? So see, these two will go and add here. This becomes COOH. Okay, right, let's write that. CH3, CH2 taken N times, this becomes COOH. So fatty acids, long chain fatty acid. What is left out? There is one hydrogen gas, which is evolved out, hydrogen. COOH, and two hydrogens is hydrogen gas. So that is a long chain fatty acid. Suppose if I take KMnO4, I said it is an oxidizing agent. Done. Here you will take any example. Basically, I am taking this example, which is a specific. Okay, CH red hydrogen. You're going to anything, any chain you can take and do. Here you can extend the chain. Here you can extend, not a problem. So here I'm going to use KMnO4 as an oxidizing agent. Here what are we going to do? Oxidation process. So I'm going to add nascent oxygen here. This nascent oxygen goes and adds. So basically what is this compound? 1, 2, 3, 4. Correct? So it is 2-methyl. This is, if I take 2-methyl, 3-carbon propane. Now this oxygen goes and adds to this hydrogen in the presence of KMnO4. What do I get? Write the same here. CH3, C, CH3, CH3, OH. Now what will happen? 2-methyl, let us write 2-methyl propan 2-ol. 2-methyl propan 2-ol. So what is happening here? We are taking alkane. In the presence of our oxidizing agent, we are getting alcohol. Alkanes to alcohol. So simple thing, remember, in controlled oxidation process, we have used all the four. What are all the four? The first one is copper catalyst, where alkenes are converted into, yes, I told you, just recollect, go back and see. Copper alkenes are converted into alcohols. Then after copper, we've used molybdenum sesquioxide. There alcohols are converted to aldehydes. Then I'm using next type of catalyst, that is manganese acetate. There the alkenes are converted into acids. Last but not the least, here we have used an oxidizing agent, that is KMnO4, where an alkane is converted into alcohol. So this is your controlled oxidation, student. Let me come back and meet with isomerism reaction. Yes. Right. So welcome back, students. We've already studied halogenation reaction, that is, I've taken the chlorination part. And I've also taught you what actually is bromination, how is bromination undergoing free radical mechanism. I gradually took you into the concept of iodination reaction, and I also showed you what are the oxidizing agents used. I also gave you a small note on the question on fluorination of benzene. So fluorination is done, bromination is done, chlorination is done, and iodination also is done. So next comes combustion. I've shown you again what is the process of combustion, that is heating in the presence of oxygen. Then I've taught you the concept of controlled oxidation reaction, where I've used different cheminophore. I've used molybdenum manganese acetate. I've used molybdenum sesquioxide. I've used. So I've showed you conversion of alkenes into alcohols, conversion of alkenes into aldehydes, conversion of alkanes into acids also. Now we'll come to the next concept called isomerism. So let us write the heading, isomerism. So what actually is this? Iso means same, mer means unit, merism means the property of showing. Right. And now when I have to write about the definition of isomerism, let's see. So it is simple, nothing. Compounds having the same molecular formula but different arrangement in molecular structure. Right. So let us write compounds having same molecular formula but different molecular structure. Okay, we have written such a big sentence here. Let's see what it is. Now suppose if I take an alkane, because we are studying alkane chapter, let us speak about that. Alkane, when I have to speak about the basic alkane or any alkane rather, not other than methane, so or even the propane part. So when I speak starting from butane, so these alkanes, what do they have? They have the property of showing isomerism. What type of isomerism? I already did a video on types of isomerism. Structural, stereo, and that again optical, all these types of done. So alkane basically are going to show or give us, like, they show a type of isomerism called structural isomerism. That means they exist with the same molecule or can exist in two or more forms. Right? Suppose if I take the basic example, let us see. Right. So suppose if I take N-butane, then what is N-butane formula or structure? It looks like 1, but means 4 carbons, 1, 2, 3 and 4. So fill in all the hydrogens, 3 here, this is 2 here, this is 2 here, this is N-butane. The same N-butane can exist as a different arrangement. Now what am I going to do? I am going to take this and shift it here. How does it look? Now CH3, I am going to take this and shift this CH3 here. Okay, CH2. Okay, now this becomes CH3, this becomes CH. 3 plus 1, 4. For this carbon, 1, 2, 3, 4. 3 plus 1, 4. 3 plus 1, 4. Now what is the name of this compound? This is called isobutane. Done. So now what is happening? The compound has the same molecular formula but different arrangement in the structure. It is called structural isomerism. Done. Now this property, or this is called isomerism reaction. But what is important here, when you are converting the same butane to this one, I require a Lewis acid in the presence of a catalyst, that AlCl3. Done. Let us take one more example. The same thing, this particular isomerism can be shown by N-hexane also. And what is N-hexane formula? N is normal hexane. It's 6 carbon atom. 1, 2, 3, 4, 5, 6. Now fill in the hydrogens. This is the hydrogen. This is also hydrogen here. This is 2 hydrogens, 2 hydrogens, 2 hydrogens, 2 hydrogens. 1, 2, 3, 4, 5, 6. The same N-hexane. Right, okay, let us write the formula also. So this is C6. Count the hydrogens: 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Isn't it? Let us cross check. 3 plus 1, 4, correct. 2, 3, 4, correct. Because carbon is tetravalent in nature, it should have 4 bonds around it. So this carbon, 2 plus 2, 3, 4, correct. For this carbon, 2, 3, 4, correct. For this carbon, 4, correct. For this carbon, this. So now count 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So C6H14. That is N-hexane. This N-hexane can exist in 2 different isomers. What can I do? There are 2 possibilities. I can take this methyl group and shift it to this carbon. Point number 1. I can take this methyl group and shift it to this third carbon. Why? Suppose if I do the third combination, I'm taking this, again shifting here, it will be the same 2 methyl. If I'm taking this and shifting to the same to this 3 methyl, so only 2 combinations I can do. What is that? I'll take 1, 2, 3, 4, 5. Now 6th one is there. I'm placing in the second position this. Now next option, next isomer, 1, 2, 3, 4, 5. I'm placing in the next position. Now what did I do? Here the carbon or the methyl group was in the second carbon. Here the methyl group is in third carbon. Let us fill in hydrogens. This is CH3, 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 H, CH2, CH2. Now here let us fill the hydrogens. 3, this is 3, this is CH3, CH2, H and CH2. Now name the compound. This is 1, 2, 3, 4, 5. Now name the compound 1, 2, 3, 4, 5. Now how to name this? This is 2-methyl 5-carbon chain pentane. This is 3-methyl 5-carbon chain pentane. 2-methyl pentane and 3-methyl pentane. These two are the isomers of N-hexane. So what did N-hexane do? N-hexane undergo isomerism and it has formed two products. Let us write 2-methyl. This is 2-methyl pentane. The next isomer 3-methyl pentane in the presence of a Lewis acid, that is a catalyst, that is LaCl3, aluminium chloride. So this is the process of isomerism in alkanes. Because they have the tendency to show structural isomerism, I have written the lesson. So when you have isomers of pentane, it is a very important question. I have also done a video on isomers of pentane. I have shown you a worksheet. Yeah, I have done a worksheet on isomerism. There I have shown you pentane isomers, possible isomers for hexane, possible isomers for butane. Please watch the video for further information. Right. So welcome back, students. Let us come back. We have done the isomerism concept. Let us start with steam reforming now. So basically steam reforming, what is the main important thing you should remember? Steam reforming of methane. This particular process. I have taken this from Google. Right. So the main method or the main reason or main use of steam reforming is this is used for a large scale production of hydrogen. So let us write that. It is a my marker is not so proper. Okay, large scale production of hydrogen gas. So this is used for the large scale production of hydrogen gas. Suppose they ask you for 1 mark question, what is the use of steam reforming? You can write it is used for large scale production of hydrogen gas. Done. So basically what is important here? Here we are going to take, or we have different units in the reforming segment. What are they? We have a furnace as it is shown here. Furnace, a steam generator, the most important thing. And in the furnace, what are going to happen? This is the process. Right. So in this particular furnace, we are going to just send the fuel. What is the fuel? Here, the fuel used is methane in the form of a gaseous state. I'm going to use methane. Now, this fuel is sent or fed into the furnace. So we have taken that feed is nothing but the methane. Here it is allowed to undergo pre-treatment, right? So this gas, whatever this impurities are there, everything is removed and it is pre-treated earlier. Now then next what happens from the furnace, that feed is combining with the steam. Here water is taken, this methane gas is going to combine with water which is in the form of a steam. Done. This whole process in between, you need a catalyst, that is nickel as a catalyst. So when we are using nickel as a catalyst, what happens? These two combine together, fine. And during this process, what is that? First feed, which is happening here. Then it is taken to reforming process where your steam is generated from the steam generator and it combines. This feed combines with the water, whatever is there in the form of steam. Both will be combined, and during this process, there are two things which are released. What are they? One is carbon monoxide, which comes out as a waste, and the hydrogen gas, which is used or which is required, comes out in the large scale production of hydrogen. Simple. First it is fed, then it is pre-treated in the furnace. From there it is taken to the steam generator where steam combines with this in the reforming process. We call it as reforming, where the gaseous methane combines with water, or the water in the form of steam. Finally it's get converted into gaseous state. Whatever gaseous state is sent for purification. In the purification all the wastes are sent out and the hydrogen gas which is used in the large scale is released. This is your steam reforming of alkanes or methanes. Let's balance. 4 plus 2 6. So here this is 3. This is how the hydrogen gas, or this is how is a steam refining process. Now let's come back and see crackling or pyrolysis process of alkenes. Right. Now, already we have completed these reactions. Let's come back and see the process, the most important reaction of alkanes and the most famous reaction also. I think it's very easy, but most of the students get confused here. So, we're going to learn what is meant by cracking or pyrolysis, right? Okay. Lysis means smaller fragments. Lysis means breaking into pieces. You just slice the things in a carrot. Suppose if you're cutting a carrot, you break into smaller pieces. So lysis means you're breaking into smaller fragments. So if I have to write cracking also means breaking into smaller fragments. So let us write the definition of cracking first. Right, it is a process. Okay, it is a process of breaking. Let us write that word because I'm transforming that process into this. It's a process of breaking higher or hydrocarbons. What hydrocarbons? Hydrocarbons means higher hydrocarbons. Means butane into propane, like that. Higher hydrocarbons into lower hydrocarbons. Lower hydrocarbons. That too, very important thing is this lower hydrocarbon should have a lower boiling point. That is important. With lower boiling point by strong heating. So we are going to use almost 973 Kelvin temperature to heat this and break into fragments. Suppose if I take N-butane, okay, N-butane is when I use, I'm going to strongly heat it at 973 Kelvin. It's going to break up into smaller fragments. But what is important? Let's see. First of all, you can write the different combinations of cracking products here. Done. First of all, N-butane, let us write the formula. Butane 1, 2, 3, 4. Done. So CH3 here, CH3, CH2, CH2. So what is the formula now? C4, 3, 4, 5, 6, 7, 8, 9, 10. C4H10. This is the formula for N-butane. This is going to crack or pyrolyze or break at this particular temperature into, it can break into ethane, it can break into ethene product. Why only these? We will see. It can break into your methane and it can break into propene. It can break into butane. It can break into, or the next door is hydrogen gas. Now, why only these? Let's see. Now, what is the formula of butane? It is C4H10. It has to break up into two pieces. That is, suppose if I take ethane, 1 carbon, 2 carbon, 3 and 3 ethane. Ethene, 1 double bond. This is alkene. So CH2, CH2. Done. Methane, CH4. Propane, 1, 2, 3 carbons. It is propene, this is it. So 2 double bond. 3, this is 3, this is 1 H. This is butane, 1, the same butane here. Okay, let us write this 1, 2, 3, 4. So 3, this is 3, this is 2, this is 2. Okay, now what is the concept? This is C4H10. It has to break up into pieces, but at the same time you will get the formula back when you just join. We are not just asking you to join, but during pyrolysis, whatever is the formula, it will break into compounds which have together make again the same molecule. What is that? Here carbons are 1, 2, 3, 4. Done. 4. Hydrogens here are 10. Now count 3 plus 3, 6, 7, 8, 9, 10. So together C4H10 is a formula. So this C4H10, higher hydrocarbons are breaking into smaller hydrocarbons. Higher hydrocarbons are breaking into smaller hydrocarbons with low boiling point. Let us go with the next one. Next set. Here methane and propene. Carbon is 1 here. Here carbons are 1, 2, 3, 4 carbons. So 4 carbons done. Hydrogen should be how many? 10. Let's see this. 4. 5, 6, 7, 8, okay, 4, 7, did we write something wrong? Let's see. So, this is 1, 2, 3, 4, 3 plus 1, 4, 3, 6, 7, 8, 9, 10. So, let us make this as, I think we have to change this. Let's see. Yes. So one important thing, I've written a mistake here, isn't it? Okay, what did I do? I've written propene formula, propene product. This is methane. This is right only, but formula while writing I've written wrong. What is that? Propene 1, 2, 3, 2 carbons. So this is 2 hydrogens here. This is 1 hydrogen. This is 3. Now methane formula CH4. Let's count. Carbon 1, 2, 3, 4. C4, H10, 4. 5, 6, 7, 8, 9, 10. That's why it is breaking them into two similar, means two different lower hydrocarbons. Suppose if I take the last one here, butane 3, okay, carbons are 1, 2, 3, 4, done. Hydrogens are 3, 4, 5, 6, 7, 8, 9, right? So 3, 6, 7, 8, 10, okay, 9. So here the leftover is how much? It is only hydrogen gas, isn't it? So what is important here is breaking the higher hydrocarbons into the lower hydrocarbons is called cracking or pyrolysis. But what is important? They have to have, or they should be broken at very high temperatures only, right? So that is important here. So very high temperatures, they'll break up or pyrolyze into smaller product. That is what is called pyrolysis or cracking. Now let's further see different examples for pyrolysis or cracking based on this. Right. So let's come back and learn the next reaction, aromatization. Done. So first of all, whenever I have to define aromatization or speak, you would have studied this aromaticity property in benzene, isn't it? That is your closed chain structures. The benzene shows the property of aromaticity where there's a transfer delocalization of pi bonds. You would have studied that, right? Not a problem. We'll be studying the same concept in benzene in the aromatic compounds, the last topic of the chapter. So aromatization means what? So if I have to define this, basically it is a process. Let us start writing and understand it later. It is a process of converting straight chain hydrocarbons. Okay, this is the key word here, converting straight chain. Okay, I've written the spelling wrong. Straight chain hydrocarbons. What am I going to do? I'm going to convert straight chain hydrocarbons into a cyclic structure or a ring structure. Into a ring structure. Okay, I'm not using the aromaticity word here. I'll use it later stages. So converting the ring structures in the presence of suitable catalyst. In the presence of suitable catalyst. Done. So here what am I going to do? I'm going to use either chromium as a catalyst. Either I'm going to use molybdenum as a catalyst. I'm going to use nickel as a catalyst. So let us divide the page into two equal halves and take two examples here. Now basically I'm going to take hexane, N-hexane. Then I said I have to convert it. That's why I'm taking unity pentane also converted to cyclic structure. But here I've taken an N-hexane. So N-hexane is 1, 2, 3, 4, 5, 6. Now fill in hydrogens. 3. So 3, 2, 2, 2 and 2. So how many carbons? 6 carbons here. And how many hydrogens? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. N-hexane. Now what happens when I treat this N-hexane with a catalyst, any catalyst, a chromium, right? Suppose if I take CrO3, okay, cyclization or aromatization, we call it a cyclization. Let us write that, cyclization, done. So this is going to convert and it's going to form a ring. How does it form a ring? In this way. Let's see, 1, 2 carbons, 3 third one, 4, 5, 6. Now join all with single bonds like this. Now fill in the hydrogens. For this carbon, H2. For this carbon, H2. Now count the number of hydrogens. Carbons are 6, but hydrogens are 2, 4, 6, 8, 10, 12. Here how many carbons were there? They were 14. It is C4, 6, H14. Now this has become C6, H12, isn't it? Yes. Now how many hydrogens are less? 1, 2 hydrogens. That is, it comes out in the form of hydrogen. That's it. So this is the process of converting a straight chain into a cyclic structure. That's why cyclization. Now I'm going to use the word aromatization. How? What am I going to do? I'm going to take the same that is your hexane ring, 1, 2, 3, 4, 5 and 6. Now fill in hydrogens. This is 3 hydrogens. This is 2 hydrogens, 2 hydrogens, 2 hydrogens, 2 hydrogens and 3. Now this is my hexane, N-hexane. That means I've written in the form of a ring. Now what am I going to do? I'm going to use the same chromium trioxide, and that is the required catalyst, the specific catalyst for this. And this process is called cyclization, isn't it? Now during this process, what happens, as I said, there's a bond formed here in this case, and you get a cyclohexane. Now what am I going to do? I'm going to do the process of aromatization. This is cyclization, this is aromatization now. So adding the pi bonds to the structure. When I do the aromatization, this cyclohexane gets converted to benzene with alternate pi bonds. This one. Now what I can further use this. I can use, suppose if I'm using HNO3 and sulfuric acid, you will be studying this in grade 12th. So I'm using the nitrating mixture. Immediately you get a compound from that, or this is called nitrobenzene. So what am I trying to do? I'm converting the straight chain compounds, converting straight chain hydrocarbons into the ring structures. So I can do cyclization, I get cyclohexane. Then I can do aromatization, I'm adding the pi bonds forming benzene. Benzene further treated with nitrating mixture, that is nitric acid, HNO3 and sulfuric acid, I get nitrobenzene. We are converting the straight chain into aromatic compounds in this case. We are converting the straight chain into cyclic structures in this case. So this is called aromatization process or cyclization process. Right. So we have almost completed the preparations of alkenes. Almost all the combinations are over. Right. So remember one thing, student. Whenever you're learning organic chemistry, when you understand or listen to organic chemistry, it will be very, very easy, very interesting also. But unless until you practice it on daily basis, you will not find it so easy. It should become a habit. To see, you get up in the morning, brush your teeth, or you drink a glass of warm water, you go for walking. Everything is routine because you've been practicing that. Nothing to learn or nothing to teach you every day. But in the same way, organic chemistry also should be like a daily routine. You should get up every day, try to practice whatever video. Suppose every day I'm uploading or sending you a video. So whatever data you have studied, next day morning you need to revise it on daily basis. Remember, everyday organic is good for your health. We have learned as a child, isn't it? An apple a day keeps doctor away. But I'm again telling you, everyday organic is very good for your health. I'm telling you, very good for you to score that 70 out of 70 in your board exams. Done. So here, next and last preparation of alkene, controlled hydrogenation. What is hydrogenation? Hydrogenation is addition of hydrogen. So whenever we say addition of hydrogen, what should you remember? Now, addition of hydrogen or removal of oxygen is nothing but reduction, isn't it? So reduction. So here for reduction, we need some reducing agents specific. So I'm going to use here a very important reagent or catalyst called Lindlar's catalyst. So according to the reducing agent, Lindlar's catalyst also I'm going to use, right? And apart from this, I'm also going to use sodium in the presence of ammonia. What is Lindlar's catalyst? Lindlar's catalyst is nothing but palladium over calcium carbonate or charcoal. This is your Lindlar's catalyst. Done. Now I'm going to take this and try to hydrogenate. Let me take certain examples and see. Let me divide the board. I'm going to take the first example here. I'm going to take the second example. I'm going to take the third example. Now I'm giving you the basic examples, but you can always try, keep experimenting with different examples as and when you study. Now, first of all, I'm going to take the basic alkene ethene. Now I said these are going to, whenever you see Lindlar's catalyst, you should just add hydrogen. So I'm going to use Lindlar's catalyst. I'm going to write like this, Lindlar's catalyst, and or it can be sodium in the presence of ammonia. What are they going to do? They're going to add hydrogen. Where will they add hydrogen? So first important thing is here, this hydrogen is added. Here they're going to break this bond and do. But here we are preparing alkenes. So I should not take alkenes. I'll take alkynes now. This is done. So one hydrogen adds here, breaking this bond, and one more hydrogen adds here, breaking this bond. What do I get? I'm going to get CH2 double bond CH2. This is your ethene, which I have prepared from alkyne, that is ethyne. Simple. Now let me take one more example here. Suppose if I take this example 1, 2, 3, and this is a quite common example which is there also in your comprehensive. 3 plus 1, 4, done. The same example here. What is this? Now let us count. 1, 2, 3, 4, 5. Pent. Which pent is that? 1, 2. Pent 2 ine. Isn't it? 1, 2. Pent 2 ine. The same thing. CH3, C, triple bond C, C2H5. This is also pent 2 ine. Now we said controlled hydrogenation. I am going to control the hydrogenation, the addition of hydrogen using different reagents. But here, suppose in the question paper, if you see Lindlar's catalyst, right? So that is, what is Lindlar's catalyst? It is palladium over calcium carbonate or charcoal. In the exam paper, if you see sodium in the presence of ammonia, nothing. Here, the major product. I am going to take the major products only. Simple. What will this do? This will add hydrogen. Where will this add? Around this triple bond. This is going to break this bond. One hydrogen adds here and one more hydrogen adds here. Done. So when this adds, what will happen? Triple bond will break up and become double bond. So let us write CH3 single, C double bond C, C2H5. But where is the hydrogen added? Yes, this is where is important. Now see here, this C double bond C, 1, 2, 3, 4. Your CH3 is here. Your C2H5 is here. Now the hydrogen which is there adds around this carbon here and here. What is this product? Hydrogens are on the both same side. So this is cis product. Cis isomer. Now, the same thing if you have NaNH3, you're controlling the reaction with sodium and ammonia. What will happen? It's going to add hydrogen. It's going to add in between the double bond, sorry, triple bond, where it will break this triple bond. One hydrogen adds here and one more hydrogen adds here. Same product, C double bond C, but you have to be careful here. Here, what happens is this CH3 is here only. Now, in the presence of NaNH3, when you're controlling the hydrogenation reaction, you're fixing that. We are going to pick up the major product. Lindlar's catalyst, the major product is cis isomer. But here, when you take sodium NH3, the major product will become trans. See here, hydrogen and hydrogen are in the opposite direction. So cis means same direction, trans means opposite direction. So you will be getting a trans isomer or trans product. Done. So this is called controlled hydrogenation reaction. You have to be very specific when your teacher gives you. Simply, she will give you an alkyne, she will give you hydrogen. You have to see the catalyst. Okay, if it is Lindlar's catalyst, you get cis product. If it is NaNH3, you will get trans product. So this is your controlled hydrogenation reaction, students. Thank you for watching. I'll meet you again with the most important reasoning questions of alkenes, that is physical properties of alkenes. Then gradually I'll be taking you into a concept called chemical properties, where I'll be doing comparative study between symmetrical alkene and unsymmetrical alkene. So you'll not find that in your textbook also. I've made a tabular column where both I'll be comparing and teaching you. So thank you for watching. Have a wonderful day. Right. So students, we have successfully completed the alkanes topic. We have studied the structure, we have studied the hybridization, we have done the nomenclature, we have done the concept of isomerism in that. Then I taught you the preparations. Then I've also taught you the concept of, I've given you the information about chemical properties of alkanes. There is one important topic left with alkanes, that is conformers or the Newman conformations of ethene molecule. Very important, Newman projection, Sawhorst projection, all these I'll be teaching as a separate video. Very interesting, but I didn't want to mix up with this. I'll get back to you at the last part of the chapter. Last part, when I complete the whole chapter, then I'm going to do that. Right. So next topic of your hydrocarbons is alkenes. Done. So in alkenes, we very well know the general formula of alkenes is CnH2n, isn't it? I told you, isn't it, the other day? N is equal to, here it's going to start from 2, not 1, because it is a bond, double bond formed between two carbon atoms. So if N is equal to 2, C2 H, 2 into 2, that is C2H4. So the basic alkene is ethene, CH2, CH2. So this is ethene, the basic alkene. Now these alkenes are going to show, we're going to prepare the alkenes by different methods of preparation. That is, first, dehydrohalogenation reaction. Very important. What is dehydro? D means subtraction, minus. Hydro means we are subtracting hydrogen. Halogenation means X. X is denoted, halogens are denoted by X, isn't it? Fluorine, chlorine, bromine and iodine. So the removal of HX is one. By removing HX, I am going to prepare alkene. Next, dehalogenation means D means minus, halogenation means X. I am going to take out X and shift that bond to form a double bond. Dehydration means removal of water. Hydration means H2O. Remember that, don't get confused. Controlled hydrogenation means here addition of, there is no D given, so it is controlled hydrogenation, addition of H2 in the presence of a catalyst. So I'll be teaching all these reactions. Watch it carefully, keep noting it, right? So let's come back and meet with the first reaction, that is dehydrohalogenation reaction. Yes, we will see with one I'm going to take out HX. So welcome back students to one more session of your alkenes. So till now we have started the hydrocarbons chapter. We've been doing different types of reactions. I've taken you through a journey of different types of concepts, right? So today we are going to start with the preparations of alkenes. So I hope you've seen the earlier video where I've taught you what are the different preparations: dehalogenation, dehydrohalogenation, hydration, like that, right? So before I go to this particular reaction, let us see. Basically in organic chemistry, you know, there are a lot of reagents which you should remember. When you go to grade 12, there are a lot of reagents. Based on the reagents only, you'll write the type of the product also. So being in the grade 11 student, you'll feel a bit difficult for you all to remember. But as and when you know, as and when you practice, it will become very easy for you all to know the reagents and also the products formed. So in this particular reaction, the first important thing which you should remember is, see, we have studied alkanes. That is what knowledge you have about alkanes. Alkanes is methane. The basic alkane is methane. Like that, I have again taken you to one more class of compounds. What did I say? From alkane, suppose if I take this, it is like this. Now I'm going to introduce or take out one hydrogen and replace with halogen. Then it is called alkyl halide. Okay, done. Now we are going to speak about this alkyl halide only. So in this particular reaction, most important thing which you should remember is the raw material, the product which we require. Just now I said we are going to require an alkyl halide. Just now we heard what it is. Along with that, I'm going to use a very important reagent, that is alcoholic KOH. Okay, done. After this, along with this alcoholic KOH, this particular alcoholic KOH is a very important reagent. What is its mode of action? We will see in a while. So along with this, I am going to introduce C2H5OH. Ethanol will always be there accompanying that. We will see what is the importance of this, why am I taking ethyl alcohol, and it is almost, you know, 353 Kelvin to 363 or 373 Kelvin, almost 363 Kelvin temperature. Done. So what is going to form actually? Let's see. So when you find such thing in the paper, question paper, only thing you have to remember is you're going to get an alkene, you're going to form KBr is out in water. Okay, such big reaction. Let's analyze what actually is a reaction. Done. So alkyl halide. Let us take three different examples. We already know what is alkyl halide, isn't it now? Yes. Suppose if I take, let me take the first example here. Let me take the second example here, and let me make a table. Okay, as my board is so much, I just divide into three. The first one, I'm going to take ethyl bromide. Okay, this is an alkyl halide. In the next case, I'm going to take alkyl. Let us take, after ethyl it is propyl, isn't it? Okay, let us take propyl bromide. Then let us take isopropyl bromide. Isopropyl bromide. You can take any example to show. Done. So first, now I know what is ethyl bromide. Let us write. Eth means two carbons, isn't it? 1, 2 and bromine. Now let us fill the hydrogens here. 3. Let us fill the hydrogens. 1 H here, 1 H here. You already know, I believe, around carbon there should be 4 hydrogens. So this carbon has 3 plus 1, 4. Done. For this carbon, 1, 2, 3, 4 bonds. Done. And Br. Yes, hope it's clear, students. Now what am I going to do? I'm going to introduce alcoholic KOH, very important. So alcoholic KOH, we have two different reagents, alcoholic KOH and aqueous KOH also. Remember, alcoholic KOH always, okay, important is, this is going to show us elimination reactions only, right? Okay, let's write the product and then come back. Here I'm going to introduce C2H5OH and the temperature is already written. Now what happens? Alcoholic KOH, before it reacts, what should we remember? Here there are two types of carbons. The carbon which is immediate or adjacent to the functional group is called alpha carbon. The one which is adjacent to this is called beta carbon. Alpha carbon is something which is immediate to the functional group, or whichever, like now here the functional group is halogen and the carbon adjacent to that is beta carbon. So what should you remember? Here the concept is, every time there is elimination of hydrogen from the alpha carbon, elimination of halogen from the alpha carbon and elimination of hydrogen from beta carbon. Once again I'm repeating, what should you remember in these reactions? Important thing and important concept which you should remember. I said always there is elimination or removal of halogen from the alpha carbon. So halogen is removed from alpha carbon, done, and hydrogen is removed from beta carbon, okay, done. So that's why we call this as beta elimination reaction. So simple. Shall I write dehydrogenation as / beta elimination reactions also? Done. So simple, beta elimination reactions. So remember, halogen from alpha carbon, hydrogen from beta carbon, over. Now let us take out. So I said, hey, this one, this HBr from here and this H. This hydrogen, let me write it as 1, 2, 3 like this, H. Done. So this H and this H comes out, okay. That particularly dehydrohalogenation we said, done. So this Br comes out with this K as KBr. This hydrogen comes out with this OH as water. Now what happens? This bond immediately shifts here. So what do I get? CH2 double bond CH2. That's it. What is the name of this compound? This is called ethene. Simple, isn't it? Right. Now let us try with one more example. Here propyl bromide. Propyl means 1, 2, 3 prop and bromine. As usual, fill the hydrogens. 3 hydrogens here, 2 hydrogens here, 2 hydrogens here, done. Now I need to introduce alcoholic KOH. Alcoholic KOH means immediately you should remember it's going to show us beta elimination product. Right. So in this occurs with same temperature here, C2H in the presence of C2H5OH. Now same story. Halogen should be removed from the alpha. Now this is alpha carbon, this is beta carbon. Halogen will be removed from the alpha carbon and hydrogen will be removed from the beta carbon. So let us write, this is beta, let us write this H as 1 H here and 1 more H here. Done. So first this Br comes out with this potassium as KBr, done. This hydrogen comes out with this OH as water. What will happen? This bond from here, this is broken, isn't it? This bond from here shifts here. Now what do I get? I'm going to get a product like this, CH3, CH. Now H has gone out, so I'm going to get double bond. Fine. So next left over is what? CH2. Now let us count. C2 plus 2, 4. Now 1, 2, 3, 4. Now what is the name of the compound? This is called propene. So once again observe, halogen is removed from alpha carbon, hydrogen is removed from beta carbon. That's it, finally giving an alkene. Now let us try with this isopropyl bromide. Fine. So isopropyl bromide means iso group we very well know, then propyl 3 carbons, but the bromine is in the isopropyl position. Let us see what it is. So 1, 2, 3. This is your isopropyl position and your Br is here. Now fill in hydrogens, 3 and 3. This is 1, 2, 3. This is hydrogen. Right. Now you should remember again the same concept. The carbon with the functional group is alpha carbon and the one which is adjacent to this is beta. This is also beta. So you can remove from both the sides, not a problem. Done. Now let's see. I need to introduce what? I should have this alcoholic KOH, isn't it? Because that's the most important thing. It is a less basic than ethanol. We will say that also in a while. Now, what should be the temperature is same, and ethanol should be there being a stronger base than KOH. Done. So I said we have to remove HBr, so we should remove KBr. From where should I remove? I have to take out bromine from the alpha carbon. Remember, halogen from alpha, hydrogen from beta. Suppose if I take out Br from here, if I take out hydrogen from here, what will happen? First thing, KBr is out, then water is out, and then hydrogen also is out as water. Now what are we left with? This bond shifts here, so I'm going to get C double bond C. Fill in that C double bond C, and then becomes your CH3. Now fill in hydrogens. 1 2 2 1 2 3 4. Now what do we get? We have again got a propene, but which propene? One propene, isn't it? If I count from here, it is one propene. This is how we are going to do beta elimination reactions. Now with this beta elimination concept, let us learn one more concept, that is Seismond rule. Very important rule, Seismond rule. Let's take one example and see. Now I understood the concept. I know this is beta elimination. I know what is the requirement. Why should I take alcoholic KOH? Okay, I should also take ethanol. So now important thing, remember here alcoholic KOH, when I compare, this is also a base, this is also a base. What should you remember? Among these two, ethanol is a stronger base than that. Okay, it's a very stronger base. So what does this do? Immediately this potassium hydroxide, whatever is there, this will go and try to eliminate, because this is stronger base, so a lesser weaker base than that, it will try to break out like this, in this way, and it will go and remove. What will it remove? It will eliminate halogen from alpha. Done. And the OH picks up the hydrogen from beta. That's the most important thing. Done. So now I have to learn with the same concept, that is Seismond rule with the same concept. Beta elimination reactions easily we can study. But here what is important for us is what? Let's see. So for me, I have to be clear while learning. Suppose if your teacher is asking you to explain what is Seismond rule. One important concept which you should remember is, okay, let us first write so obviously you have to write the heading, isn't it? Right. Seismond rule. Okay. In some books it will be written as Seismond, not a problem. Right. Suppose if I have an example like this, let me see. 1, 2, 3. Okay. Let me take one more, 4, like this, and I have a group. Done. Now let us fill the hydrogens. Here 3 hydrogens for this carbon, 1 hydrogen for this, 2 hydrogens for this, 2 hydrogens, and Br. Let us name the compound now. So it is, yeah, so here 1 2 3 4. 1 bromo, 3 methyl, 1 2 3 4 butane. Done. Or okay, 2 methyl I have to start, I believe, because that is a order 2. Okay, so 2 methyl. Done. Now important thing, for such examples, suppose if I have to do beta elimination, I need to take alcoholic KOH, that is understood. I also require C2H5OH, that is also understood. I told you the reason just 2 seconds back. I should also use a temperature which I have written. Now the concept is, for such compounds you will be getting 2 different types of products. Done. Why? First of all, okay, here this is alpha hydrogen. Correct? This is alpha hydrogen. This is beta hydrogen. Right? So as I proceed, gamma hydrogen, like that, isn't it? Fine. So in this particular reaction, most important concept is, you can eliminate or take out bromine from this part and hydrogen from this part. No problem. Suppose if you have a group like this, let me take, if you have a group like this, and if you have this, okay, here if the condition is like this, I can remove, this is alpha, this is beta. You can remove, what can you do? You can remove Br from here, you can remove hydrogen from here and drop the bond. Right? Suppose if I have an option like this, I'm going to take out this carbon, and here I'm going to introduce the same Br, right? Okay, let me take this group. Here I'm introducing. Now what is the difference? Little bit movement of this. Now here what is the condition here? This is the alpha carbon because bromine is here. On either side you have beta carbons, isn't it? Beta This is beta. Problem starts here in this condition. If you are having alpha at the end, not a problem. But if you have alpha in the center and beta occupied by those, it's going to give us two different products, and we should remember which is the major product and minor product. How should you start? Suppose if I take out bromine from here, done. I can also take out hydrogen from here. Then what will happen? This bond will shift here. Condition number 1. Let's write that. First is CH3, second is CH2, third is now, okay, this should be H only, right? Okay, H, CH3. I'm taking out Br from here, right? So CH, a double bond, and this is CH2 because I've taken out hydrogen from here. So now this will become 2, 3, 4, 1, 2, 3, 4. For this 1, 2, 3, 4, correct. For this 2, 3, 4, correct. Right. So what is this one? Here you have got a product here with a double bond placed the last. That. Suppose if I take out halogen from here and remove hydrogen from here, okay, now what will happen? This bond is going to shift in this direction. Earlier it was in this direction, now it will be in this direction. Let's take that. 1 CH3, 1 is CH2, 1 is CH3, double bond, CH2, single bond, CH3. Let us count. For this 3 plus 1, 4, right? For this 2 plus 2, 4, right? For this 1, 2, 3, 4, right? For this 2, 3, 4, 5. So this should be H only. Then 3 plus 1, 4. Done. So now what will happen? Let's see. Here when I count 1, 2, 3, 4, 5. Let us write the name first for this, then it's easy for me. What is the name of this parent chain or this particular thing? Here you have bromine. If I have to start 1, 2, 3, 4, 5. Name this. It is 2-bromo 3-methyl 1, 2, 3, 4, 5. Pentane, isn't it? 2-bromo 3-methyl pentane is a compound. Done. Now if I have to start from here. Now this is 1, 2, 3, 4, 5. Name this. 1, 2, 3, 4, 5. Isn't it? Now name the compound. Again it is pent. But here what happened? You have a 3-methyl pent 1-ene here. But in this case 3-methyl pent 2-ene here. Isn't it? There's a double bond after 2, so 2-ene. Here there is a double bond after 1-ene. But when I have to speak about the major product, remember this is the minor product and this is the major product according to Seismond. This is where your Seismond comes into picture. So what is it? Why are we consider as a major product? Just see. According to Seismond rule, now I'm going to give you a definition. Understand? According to Seismond rule, the double bond or the carbon which is highly substituted is the major product once again, or according to Seismond rule, the carbon around the double bond which is highly alkylated, means which has a maximum number of carbon atoms around it, forms the major product. Once again let us redo it. According to Seismond rule, what is a major product? Let's compare. What is the comparison between this one and this one? This is CH3, this is CH3, done. This is CH2, this is CH2, done. Here it is CH, here it is C, okay. There is again CH, okay, this is CH and there is a double bond here. Here there is CH, there is a single bond here. Your whole concentration should be on this around the double bond. Here your concentration should be on this double bond. Now see here. According to Seismond or Seismond rule, the carbon around the double bond which is highly alkylated, which has the maximum number of carbon atoms or the alkyl groups around that is the major product. Here see, around carbon atom or the double bond you don't have any alkyl groups. Alkyl group is present in the adjacent, so that's the minor product. So this is your Seismond rule, and which you will be seeing only in such combinations. So thank you for watching, students. Hope the concept is clear. Whenever your man gives you, or whenever there's a question like this, whichever is highly alkylated, give it as a major product. You'll be getting perfect mark for that. Right. So welcome students to one more reaction. We'll see one more interesting reaction now. So we have studied in the last reaction beta elimination of Seismond rule. Now they've given us a target, that is vicinal halides. Okay, what are vicinal halides? Now basically we are going to prepare alkenes from this reaction, because that is a preparation which you're going to know. So do we know what are vicinal halides? In chemistry basically we have two types of combination, that is gem halides, that is geminal halides, one is vicinal halides. Let's see what it is. So first of all, I've given you the answer. We are going to get alkene from that. Along with that, I'm going to take out ZnBr2, zinc bromide. Now vicinal, remember, okay, first of all let me say dehalogenation means, D means minus, halogenation means I'm going to take out X, that is halogen of vicinal halides. I should know what it is. Done. Suppose if I have just a carbon, single bond carbon. If I have a halogen atom here and halogen atom here, then it is called vicinal halide. Okay. Now I'm filling hydrogen 1, 2, 2 here, 2, 3, 4 for this. Done. This is vicinal halide, vis halide. Shortcut we write it as vis halide. Suppose if I take the same, but I have again two carbons. Now in this case I am going to have halogen in the same carbon atom. Now I am going to fill 3 here, 1, 2, 3, 3 here. Now what is happening? Halogen is present in the same carbon atom. Then I call it as gem halide or geminal halide. Okay, now I have learned today gem halide or geminal halide, vis halide or vicinal halide. Done. Now what are we going to use? We are going to use this particular vicinal halide for this, because that is what it says. Now, so suppose here I'm instead of X, I'm going to take Br. So introduce that Br here, introduce that Br here. Now what am I going to use? Very important thing. Here I'm going to use zinc. I have to take out halogen. Why zinc, ma'am? Why or nothing? Why nickel? Why not copper? Why not platinum? Why not silver? Most important thing you have to remember is here the bond between your zinc and carbon, it forms a strong covalent bond. Basically, when zinc is forming a complex, that covalency or the covalent bond between this one and this one is very, very strong enough. Then, so because of that, we have picked up zinc metal. The covalency of zinc and carbon, that is zinc carbon bond is highly covalent in nature. It forms a strong bond. So before we get the product, it's going to form a complex here with zinc. Zinc is going to form a covalent bond with carbon and then finally gets eliminated. Yeah. So that's why I'm using zinc. Now what happens here? In this case, Br2 comes out as ZnBr2, simple. So this bond comes out with this ZnBr2. What is left? This bond is going to shift here. So I'm going to get an alkene. See here, I have prepared an alkene, that is ethene. Simplest reaction, isn't it? Vicinal halides. So this is nothing. Once your teacher gives you, take out the halogen from there and suppose if you have 3 carbons. Let me try if I can get 1, 2, 3. Now 2 different bromines here. I'm going to take Zn. Same story, whenever you see Zn, I said the bond is highly covalent in nature. Covalent means you already know, isn't it? Sharing. The bond formed is due to sharing. Done. So Zn comes out as ZnBr2. This bond shifts here. 1, 2, double bond this, and ZnBr2 is out. Fill in hydrogens 3, 1, 2, 3 and 4 and 2. Now what is the name of this compound? This is propene. Yes, this is interesting, isn't it? Fine. So this is how you will learn the reactions. I think I have not written Br. Very important. So this is the second preparation of alkane. Now let's come back and learn one more preparation of alkene. Right. So now one more preparation of alkenes. Chemistry, you know, it's like it's a big ocean. More and more we study, more and more practice we get. So we've already seen beta elimination reactions. Hope it is clear. I've taught you Seismond rule also in that. Then I've shown you what are vicinal halides, isn't it? Then I told you why are we taking zinc? Why not other metals? Done. So now next important reaction, that is acidic dehydration reaction. So the same thing you'll be learning in grade 12. There is a mechanism for this also. Dehydration, acidic dehydration of your alcohols. So dehydration, there was one particularly, I think last but 1 year. This mechanism was given. So grade 12 students, compulsory you'll be getting all the 5 mechanisms in the exam. Any one will be asked. Done. So here in this particular dehydration, first see what is important. What do we write as a heading in the exam? How to remember this also I'll tell you. So here we have written dehydration. First of all, what is D? Means minus. Hydration means I'm going to remove water. But when are you removing water? In the presence of an acid. What acids am I going to use? So we are going to use reagents or acids like H2SO4, which is a dehydrating reagent. It's going to remove water from whichever you add. One more, H3PO4 is a dehydrating agent, right? In some cases we also take aluminium trioxide, Al2O3 also, right, as a drying agent or the dehydrating agent. Done. So this is your acidic dehydration. I'm going to remove water. So here I picked up 4 examples, so that's easy for you to explain. But what did I write here? Here I've written beta elimination. By now you would have understood what is alpha carbon. You would have understood what is beta carbon also, isn't it? Now what am I going to take? Suppose if I take this example, ethanol. Let us write 1, 2, this is ethanol. Propan 1-ol, 1, 2, 3, that means in the first carbon there is OH. Propan 2-ol, that means in the second carbon, first write the parent chain, 3, and the second carbon you have OH. Cyclohexanol, so this is your cyclic group with OH. Done. Now, first of all, I should fill the hydrogens, 3 here, 2 here. 3 here, 2 here, 2 here. Here in this case, 3, 3 and H. Done? Yes. The hydroxyl group, the carbon to which the functional group is attached, is the alpha carbon and the adjacent is beta carbon. The carbon to which the functional group is attached is alpha carbon, the adjacent one is beta carbon. The carbon to which the functional group is attached is alpha carbon, the adjacent is beta carbon. The carbon to which the functional group is attached is alpha carbon and the one, this is beta. This is carbon here, isn't it? So this is beta carbon. You should remember one important thing whenever you are doing acidic dehydration reaction. Hydroxyl group is removed from alpha carbon and hydrogen is removed from beta carbon. This one, if you remember, it's over. Simple. Now take out hydroxyl group. Now what should I add? This whole thing occurs in the presence of these reagents. Suppose if I take sulfuric acid as a dehydrating agent, that means it removes water. What temperature I'm going to use? I'm going to use 443 Kelvin. Now during this process, OH from here, H from here comes out. Okay. Now let me open up the chain and show you. H here, H, H. H from here, OH from here comes out and this drops here. What do I get? I'm going to get CH2 double bond because this has shifted here. This is CH2. That's it. So plus water. This is where this is doing this role. What is the name of this compound? This is ethene. Ethanol to ethene. This is your dehydration reaction, but acidic. Now same thing, I'm going to use sulfuric acid here, 443 Kelvin. Now what should I do? I have to take out, according to this, OH from the alpha carbon and hydrogen from the beta carbon. Now let me open up this hydrogen here and show it to you. How many are there? 1 hydrogen from here, 1 hydrogen. H from beta carbon, OH from alpha carbon, and immediately what will happen? This bond drops in. CH3, C double bond, CH2 plus water. 1, 2, 2. What is the name of this compound now? Let us see, count. 3 plus 1, 4, correct. 1, 2, 3, 4, correct, correct. So right. So this is propene or propanine. Same. Now let us go with this. Again the same story. OH from here, H from here or here. Not a problem. Either way. So I need to again take sulfuric acid. I'm going to use 443 Kelvin temperature. So what should I see? I have to take out this OH from here and H from here. Either way. Suppose if I open up this ring like this, H and H. So this is going to get eliminated and I get water. Never take out from the same carbon, please. Alpha and beta, remember. So if I take out from here, this bond drops in here. So what do I get? I get CH3, C, double bond, C. Now let us add the hydrogens. This is 1 and this is 2. The same thing I have got now. So propene only I have got. Suppose if you take out from this side, same thing, propanene. Done. If I take with cyclohexanol, now I am going to use here phosphoric acid, H3PO4. That is the temperature condition, the reagent which we are going to use. Here the temperature which I am going to use is almost 573 Kelvin to 583 Kelvin. Now simple, I need to take out hydroxyl from alpha carbon. I need to take out hydrogen from beta carbon. So when that is eliminated, H2O, what do I get? This bond drops in here and I get this compound. Simple? Yes. So this is your dehydration or acidic dehydration, students. Hope the concept is clear. What should you remember? You should remember whenever your teacher gives you this dehydrating agents, remember simple, you have to take out water. From where should you take out water? OH from alpha carbon, hydrogen from beta carbon, and finally form what? Finally form alkenes only. Thank you for watching, students. Students, to one more session of your hydrocarbons chapter. So gradually, we've been doing different topics. We've studied about alkenes, we've studied about the preparations of alkenes, and chemical properties of alkenes. Then I went to next topic, that is alkenes. Now there also I've taught you the structure, hybridization, preparations, isn't it? Last topic was Linder's catalyst, that is hydrogenation reaction. Now today we'll be starting with the chemical properties of alkenes. So basically, whenever I speak about alkenes, what is the first important thing you have to remember? In an alkene, basically when I take, alkenes are double bonded compounds, isn't it? Right? So when I take an alkene, it's a C double bond C, isn't it? Right. So up around alkene, we have the tetravalent C. So 1, 2, 3 and 4. 1, 2, 3 and 4. Done. Here, when I have to speak about alkene, what types of bonds are there? One bond which is there is a sigma bond which is present in alkene, and the other bond which is here is a pi bond, isn't it? Yes. Now, so whenever you're trying to show a chemical reaction, done. So suppose let me take, there is one reactant A, B, okay. This is going to combine with this. What will happen? The reaction, or first important thing, sigma bond is stronger than pi bond. So what will happen? There is a cleavage of this pi bond, and this also there is a cleavage of the bond here. One A or this one goes in, one reactant reacts here, and one of the one of the atom comes and reacts here. How does it look? It becomes C, single bond C, because the bond is broken. Here again, this is the bond where you get A and you get B. This is how the alkene is reacting. So based on this types of reactions, so the types of different types of reactions or the characteristic reactions which alkene shows are the most important reactions, is it is going to show as addition reactions. So because of the presence of double bond, so addition reactions it's going to show. After that, alkenes are also going to show as substitution reactions, that is allylic substitution reactions, that we will be learning. And after substitution reactions, it is also going to show as oxidation reactions. Done. So alkene also shows oxidation, very important reactions of alkenes which we'll be studying under using oxidizing agents under KMNF4. After oxidation, it's going to show as polymerization reaction, where one alkene molecule forms a number of chains. It's going to form chain like polythene, polyester, polyvinyl chloride, like that. Okay, let us not waste the time. Let us further go to the reactions. Now I'll be starting with the first type of reaction, addition reactions. So in addition reactions, when I take, okay, let us start naming that. So first of all, addition, what type of addition reaction does it undergo? So whenever I take alkene or this one, the double bonded C double bonded alkene, it's going to show addition reactions of type what? Here I'll be teaching addition reactions for both types of alkenes. That means I'll pick up both symmetrical alkene and I'll be showing unsymmetrical alkene also. Okay, what is symmetrical alkene? Let us see. So symmetrical alkene, that means it is C double bond C. Okay, so in symmetrical alkene, what are you observing here? Okay, this is only single bond, isn't it? 1, 2, 3 first, 1, 2, right? Symmetrical alkene means when I take the double bond, on either side you have equal number of carbon atoms. That is symmetrical alkene. Suppose here if I take 1, 2, 3. Now suppose if I break the double bond, here how many carbons are there? 2. Here how many are there? 1. So if they have unsymmetrical carbon atoms on either side, it is called unsymmetrical carbon atom. Here 1 is to 1, but here it is 2 is to 1. So this is unsymmetrical alkene. Done. Now next important thing. And these I'm going to show you the different types of reactions. What are the different types of reactions it's going to show? See, in addition reactions, we'll be learning how does the hydrogen add around both. So these are common reactions of both. I'll show you how hydrogen is added. I'll be showing you how you're going to add this one, HCl to this. Yes, I'll be showing you how we'll be adding halogen to this. X here can be bromine. Yes, I'll be picking up bromine and showing you the reactions. And after that, after hydrogen, after HCl, after HX, because of the double bond, I'll also be showing you how you are going to add sulfuric acid to this. You'll be studying all these. We'll also be learning how to add water to this. Like addition of water. We will also see how alcohols are formed, because how should I break? The procedure is the same as I showed you earlier. Then I'll be showing you how are you going to add HOCl to this. What is HOCl? It is called hypochlorous acid. Hypochlorous acid. Right, student? So let's start with the addition of hydrogen. One after the other we'll be noting, and we'll be seeing how should I add the hydrogen around the double bond. How should I add HCl around the double bond, halogen around the double bond, sulfuric acid around the double bond, water around the double bond, and HOCl around the double bond. Right. So first of all, let us start with the first type of addition. I said both symmetrical and unsymmetrical alkene we'll try. Right. Now the first example which we're going to learn is how to add hydrogen, addition of hydrogen, the simple basic hydrogen I'm going to take. Your teacher also may be giving you hydrogen or H2 dihydrogen. Right. So first of all, whenever I take an alkene, I said we'll be doing with both symmetrical and unsymmetrical. Right. So let us first take and divide the page into 2 equal halves. Okay, I have my scale. Let me divide into 2 equal halves. Now, first of all, I'm going to take a symmetrical alkene here, as I showed you, and I'm going to take an unsymmetrical alkene here, which I showed you. Symmetrical alkene is C double bond C, equal number of carbons on both sides. Done. So fill in hydrogens, CH2, CH2. What is the name of this compound? This is called ethene, because there are two carbons. Now I'm going to add hydrogen to this. Here unsymmetrical alkene, I'm going to take propene, 1, 2, double bond 3, fill in hydrogens. This carbon has already 1 bond, so this becomes CH3. This has 1, 2, 3 and 1 H. This has 2, 1, 2, 2. Total should be around carbon 4 hydrogens. 3 plus 1, 4. 1, 2, 3, 4. 2 plus 2, 4. Done. So here I'm going to again add what now? I'm going to add hydrogen to this. Right. So here in this case, when I take hydrogen, because it's going to break and add there only, isn't it? Right. Let us see this. How we are going to add. Now, whenever you are adding hydrogen to this, the most important thing we should remember, you need to have a catalyst. Okay, because why? Addition of hydrogen, that is, reduction. Reduction always requires a reducing agent, isn't it? So, the catalyst which I am going to use here is finely divided nickel, means powdered nickel, or it can be platinum, or it can be palladium. So, that's why you are adding in the presence of a catalyst, the reducing agent, which hence we call this addition of hydrogen as catalytic hydrogenation. Catalytic hydrogenation, addition of this one. So let us write the heading as catalytic hydrogenation reaction. Okay, hydrogenation reaction. Done. So here catalytic hydrogenation reaction, what will happen? There's a bond broken here. What do I get? I'm going to get CH3. Okay, now this bond is broken. One hydrogen goes and adds here. One more hydrogen comes and adds here. CH3 single bond CH3. What is the name of this compound? This is ethane. Okay, right. So next, suppose if I break here, how should I break? I'm going to break. One will add around the double bond. One more will add here. So I get CH3 single bond CH2 single bond CH3. So this is propane. Simple. I've just added around the double bond. So this process is called catalytic hydrogenation. So in grade 10 we also studied, isn't it? It is used like hydrogenation reaction for preparation or manufacture of vegetable, manufacture of vanaspati ghee, the what do you say, unsaturated vegetable oil to saturated one. Means we have prepared it from vegetable oils, isn't it? So this process, basically hydrogenation, we are converting vegetable oils into vanaspati ghee. This is the vanaspati ghee. This is the procedure. Okay, done. So simple hydrogenation we did. Now we are going to see how are we going to add halogen to this. Let us turn the page and see. So now I am going to write the heading addition of halogens. Okay, addition of halogens. Fine. So when I take addition of halogens, halogen is denoted by which one? X. X can be here. I am going to take bromine. Done. So you can also add chlorine also. Fluorine, okay, high electron is not possible. So you can add chlorine also, chlorine, bromine. Right. So now, suppose if I take both, let us again divide the page into 2 equal halves. So I am going to divide the page into 2 equal halves, and where I am going to take one symmetrical alkene, that is CH2, double bond CH2, and one more unsymmetrical alkene, CH3, single bond CH, double bond CH2. Now what am I going to do? I am going to add to this bromine. Here also I am going to add, here what did I do? I have picked a bromine. Here also you are going to add bromine. So both, this also, this presence. Now we are going to take an solvent for this. What is the role? What is the use of this? I am going to take an inert solvent. So carbon tetrachloride is an inert solvent. So that it does not react, means that particular thing, it easily forms the product. It's inert. Its role is nothing to react with the reactants. Done. So what happens in the presence of this? This Br2, as I said, how is this Br2? It is basically bromine and bromine, isn't it? There is a cleavage of the bond here. Here also there is a cleavage. One bromine goes and adds here. One more bromine comes and adds here. Okay? Yes. Now here also the same condition. Br and Br, there is a cleavage. One bromine comes and adds here. The other bromine comes and adds here. What do I get? What product do I get? I get now one bromine. This is carbon. I have written this carbon, isn't it? So that CH2 is there only, isn't it? No change, CH2. So Br has come and add. Now double bond has become single bond. CH2, Br has come and added here. Now in this case, this CH3 is here, CH3. Then this CH is here. But there's one bromine which is added, Br, single bond, CH2. Yes, the bond has broken. So CH2, then one more Br comes and adds here. Over, isn't it? Now let us write. What is the name of this compound? Here we have 2 ethyl groups. Okay, right? That is ethane basically. So where are the positions? This is 1 and this is 2. Now name the compound. This is 1, 2. Okay, 1, 2 dibromo ethane, isn't it? 1, 2 dibromoethane. Now let us name this compound. When I name this compound, again, this is 1, this is 2, 3. We already know it should get the minimum number. So name it 1, 2 dibromo. How many carbons? 3 carbons. So it is propane, isn't it? Done. Fine. So now what will happen? We very well know, like whenever you are adding bromine, this is basically bromine test, isn't it? This wherever you have double bond, we add this bromine in the presence of inert solvent. So this basically is a test for unsaturation. We said whenever you're using bromine in the lab also, we said test for unsaturation. How do we know that this is unsaturation is present or not? What happens is whenever you are adding bromine solution, right? So what is the color of that? The reddish orange color, isn't it, of this bromine? This reddish orange color of bromine is discharged out. And whenever you are adding that bromine to this, whatever color you have, whenever there is double bond, whenever there is unsaturation here, that reddish brown color or reddish orange color, everything is discharged out and it becomes colorless. So this will give the test for unsaturation. So bromine water test is always test for unsaturation. So it will clearly tell whether the compound given to us is unsaturated or not. Unsaturated means double bond and triple bond, isn't it? Fine. So it's going to tell us whether the compound given to us is unsaturated or not. So this is your bromine water test. Careful. So orange red solution will wane out or fade out, saying that or indicating that it is means the given compound is unsaturated compound or not. Now that is also over. Now let's see next example. What did I say? After that, after addition of hydrogen, halogen, now we'll come back to the next important example, that is addition of halogen acids. The third important example is addition of halogen acids, right? Halogen acids, right? So when I take addition of halogen acids, nothing. Halogen acids means halogen is present together with an H plus ion. Acid is nothing but which has H plus ion. So example is, you're just adding HCl to this, halogen acids, or it can be HBr, okay? It can be hydrobromic acid, it can be HI also, right? Whenever you are reacting, okay, whenever you're taking either this, first of all you should know the order. What is the order which will react faster among this? HI, right? HI reactivity is greater than HBr reactivity is greater than HCl, right? Right? So here, whenever I take the example, now I have to show you the example, how are they going to add around alkene, correct? Right. So suppose if I take a symmetrical alkene, let me say, take one example. Now I'm going to take a symmetrical alkene, CH2, double what? CH2. Now I'm going to add HCl, let me take HCl. So, like, any example, what order is this? But I've picked up HCl. So as soon as this is done, there's a cleavage of the bond here. There's a cleavage of the bond here. Now what will happen? This hydrogen goes and adds to this carbon, and this chlorine adds to this carbon. Now what product do I get? I'm going to get CH2 will become, adding this hydrogen becomes CH3. This will become CH2Cl. What is the name of this compound? Name it 1, 2. So this is chloroethane. Chloroethane. Done. Yes. Now not a problem. Simple it is. Now the problem starts when you start adding halogen acids to an unsymmetrical compound. This is where you have to be careful, right? So now in case of an alkene, like when you have an unsymmetrical alkene, for example, unsymmetrical I showed you 1, 2, 3. This is unsymmetrical alkene, right? Now let us fill the hydrogens. 3 hydrogens. Here 1, 2, 3, 4, 1, 2. What is the name of this compound? This is nothing but propene. Now to this propene molecule, right? Suppose if I have to add unsymmetrical alkene, I have to add the halogen acid. Let me take HBr, right? So now, sorry. Now what will happen? Here I'm going to provide, or first take the condition. What condition is this? Here the reaction or this unsymmetrical alkene, okay, it occurs in the presence of, or it is the reaction between propene and HBr. This one is occurring in the present in dark, right? And we are not going to take any, means basically we study unsymmetrical alkene in the presence of peroxides, with peroxides and without peroxides. Okay, ma'am, what is this peroxide? Now without peroxide also we'll learn. So there are two conditions. One, I'm going to take the same alkene with HBr and with dark. Okay, now no peroxide. One more example, I'm going to take one more unsymmetrical alkene with CH3, CH double bond CH2, HBr. Now what am I going to do? I'm going to take the reaction forward within the presence of peroxide. Remember, both the conditions, both are propenes only, right? Now, suppose when I take this propene in the presence of no peroxide and in the presence of peroxide, what products we get? We will see, right? So here the main concept, a Russian chemist, okay, Markovnikov. So Markovnikov, spelling M-A-R-K, Markovnikov's rule came into existence for studying unsymmetrical alkene addition to halogen acids. When did he take this? In 1869, he has framed a formula, that is a rule called Markovnikov rule. He was a Russian chemist. He has framed this rule called Markovnikov rule. First, we will see the product and start defining. So here, what happens whenever HBr is there? There is a cleavage of the bond here. That is only the pi bond. There is also a cleavage of the bond here. When it comes, there is a cleavage of the pi bond. I should not write this, only the pi bond. Again, there is a cleavage of HBr. Now, what happens? In the presence, in the absence of peroxide, it's going to show two different products. First, what will happen? Yes, just see here, two products are formed. in the first case or in the major product, this is H plus, this is minus. This is H plus, this is minus. So in the first case, the negative part, once again, this is positive, this is negative. The negative part or the negative addendum goes and adds to the carbon having lesser number of hydrogens, right? So what does it do? It will go and add to the carbon having lesser number of hydrogens. So around double bond which has lesser number, this is 1 hydrogen, this is 2 hydrogens. So this is lesser number of hydrogens, this one. Right, in the next case, fine. So it's going to add like that. What product do I get? I get CH3, single bond, CH. This is Br, this is CH3. Okay, because bromine and add here, hydrogen is going and adding here. And then one more. In the next case, here you will have the negative part adding to the carbon. Now, first case this is over. In next part, what will happen? The negative part goes and adds to the carbon having more number of hydrogens. This one. Initially, less number of hydrogens. This one. Second, more number of hydrogens. This one. So, what do I get? I get CH3, CH2, CH2, Br. This is the thing. Now, hydrogens added to this. So, what is the name of this compound? This is 2-bromopropane. Why did I write this 2-bromopropane? Because 2-bromopropane, 3 carbon. Now, what is the name of this compound? This is 1-bromopropane. 1-bromopropane. Now, when I see both the things, okay, that too in the dark without peroxide, the major product is 2-bromopropane. Remember that. So, what do we get after addition? We are going to get, right? So, what is the name of this compound? This is called 2-bromopropane, isn't it? So, 2-bromo. Why did I write 2-bromo? Because 1, 2, or either side, whichever side you count, it is 2-bromo. 3 carbons are propane. Now, next, after this, I said here negative part adds to the carbon having lesser number of hydrogens. So, first condition is negative adds to lesser number of the carbon having less number of carbon hydrogens. Okay, less number of hydrogens. Remember that. So here this has 1 hydrogen. Here this is 1 hydrogen. This is 2 hydrogens. Just remember. Now next important thing here in the second case, negative adds to the carbon having more number of hydrogens. So here we get CH3, CH single bond. This is 2, and you get CH2 Br. Right, this is 1-bromopropane. 1-bromopropane. So now what happens here? The negative part adds the carbon having more number of hydrogens. Right. But what is major among these two? When I compare both, this is the major product. This is 90%. 2-bromopropane is 90% of the product, and here 10% is 1-bromopropane. So what is the first important thing you have to remember? In according to Markovnikov rule, whenever you take an unsymmetrical alkene, and when you add HBr, and that too in the presence of it is dark and there is no peroxide, you get 2-bromopropane as a major product. 1-bromopropane is a minor product. Done. Now suppose if I take the next one, next condition, this is condition 1, next condition is condition 2. Now again I am taking unsymmetrical alkene, but here I am going to add same thing again. I am going to add HBr, but now I am going to take peroxides. Important thing is peroxides. So here organic peroxides. So it can be benzoyl peroxide, right? Just like that. I am going to take peroxide. When I take peroxide, what will happen? There is a cleavage of bond here, positive and negative. In this case, in the presence of peroxide, the negative addendum adds to the carbon having, just see, you have double bonds, isn't it? Now, opposite to this, negative addendum adds to the carbon having more number of hydrogens. So here, when it adds more number of hydrogens, what do you get? You get CH3, CH2, single bond, CH2 Br. Now, this is, what is the name of this compound? This is 1-bromopropane. Okay, now 1-bromopropane is a major product which we get. Now, this rule where you take an unsymmetrical alkene, you add HBr in the presence of a peroxide. This is called anti-Markovnikov's rule. Okay, anti-Markovnikov addition. So anti-Markovnikov addition. Okay, now let me summarize what I said just now. Let us take a page which has line already. So what should you remember? You have to remember in Markovnikov, Markovnikov, Markovnikov addition. Okay, and next important thing you have to remember, in anti-Mark MARKOW NIKO, anti-Markovnikov of addition. So first important addition. Okay, I'm not writing the full form. So in Markovnikov of addition, do we require a peroxide? No peroxide. Here in anti-Markovnikov of addition, yes, peroxide, in the presence of peroxide. This reaction occurs in dark, isn't it? Wait, sorry, a little bit, no, uneasiness. Okay, fine. So this reaction occurs in dark. This we said only in the presence of peroxide. Now next important thing, what are we going to take here? We are going to take unsymmetrical alkene. Here also we are going to take unsymmetrical alkene. Here what is the major product which we get? You get 2-bromopropane, because you have taken, this is a major product. Here what is the major product? The major product is 1-bromopropane. 1-bromopropane. Okay, this is a major product. So remember this. This is, if you remember any type, anything given to you, answer. Any Markovnikov reaction is given to you, you can easily write. So according to Markovnikov, 2-bromo is major. According to anti-Markovnikov, 1-bromo is major. Now we are going to, in my next video, I'll teach you what is the mechanism of, or how should you do Markovnikov addition and anti-Markovnikov addition with the mechanism clearly. Thank you for watching, students. Let's meet again in the next video. The most important part of alkenes, Markovnikov addition reactions. What steps should you follow? First of all, you need to write the definition of this. You need to take an example of this. And after that, you need to finish off with a mechanism of this. After finishing off the mechanism, you also write what is the order of following. Like means how are this? What is the order in which it occurs, or what type of addition reaction which alkene will undergo. So let us learn everything. So first of all, I have to write the definition of definition of Markovnikov addition. Let us start. So whenever you are writing the definition, first, as I said, let us take an example. I'll be jumping to this example, then write the definition. Now, first of all, I said Markovnikov addition or anti-Markovnikov addition, you will be doing it or will be showing it in an unsymmetrical alkene. So let us take an unsymmetrical alkene. I'm taking an example. Unsymmetrical means around the double bond, the number of carbon atoms is unequal. So if this is the double bond, if I put my pen like this, here there are 2 carbons, here there is 1 carbon. So this is unsymmetrical alkene. Now fill in hydrogens, H3. Here fill in H, here H2, right. Now I'm going to add hydrogen HX to this, halogen acids, as I said. So it can be what do you say, HBr. Yes, as I showed you in the earlier video, HBr, then HCl, isn't it? Done. So first of all, let us write the charges. This is partial positive charge and this is partial negative charge, isn't it? Right. Now what is this? This is an unsymmetrical alkene. That is unsymmetrical double bond, unsymmetrical alkene. It is propene, unsymmetrical in nature. Now what happens? Right. Now let us start. First of all, during addition reactions, these are all addition reactions, isn't it? During addition reactions or addition across the double bond. Yes. Now just see here, the negative addendum adds to the carbon or attaches itself to the carbon atom having carbon atom carrying less number of hydrogens. Once again, the negative addendum attaches itself to the carbon having lesser number of hydrogens around double bond. And obviously, the positive goes to the carbon having more number of hydrogens. Now, what do we get? Here we are going to get a product called CH3, CH. Now this one has added to this, so this becomes X. This becomes, now the bond is broken, isn't it? So this becomes single bond. This is CH3. What is the name of this? This is an addition product. I have not written anything, so this is just an addition product. Now let us write the name of the definition of this. Let's start. Now we should write during addition reactions. You're going to start your Markovnikov this one with during addition reactions. Let us write during the addition across which alkene is this? Unsymmetrical alkene, or across unsymmetrical double bond. Unsymmetrical double bond. So what will happen? The negative addendum, isn't it? Okay, the negative part, okay, negative part of which one? The negative part of the adding molecule, okay, negative part of adding molecule. Where does it attach? It attaches to molecule attaches itself to the carbon atom, attaches itself to the carbon atom, carrying what? Carrying lesser number of hydrogens, less number of hydrogen atoms, less number of hydrogen atoms. That's it. So this is your Markovnikov rule. So lesser number, negative part adds to the carbon having lesser number of hydrogens. Remember that. So this is a major product too. Now let us start with, now I've written the definition, I've written the example. Let us start with the mechanism of this. So when I have to write the mechanism or Markovnikov addition mechanism, first important thing is you should write step by step. Remember. So first of all, let us write mechanism of addition of halogen acids to, which one are we adding? Which alkene are we adding? Unsymmetrical alkene. Okay, right? So symmetrical alkene and unsymmetrical alkenes also we will write both symmetrical and unsymmetrical alkenes. Unsymmetrical alkenes, both we will learn. Unsymmetrical alkenes, right? So we are going to see how are we going to add. So your concept of Markovnikov starts with unsymmetrical only. So when I take a symmetrical alkene, let me start with the first one. I am going to take symmetrical alkene. Fine. So here let me teach you step by step. So in the step 1, so first let me take step 1. In step 1, first important thing is I am going to take symmetrical alkene, C double bond C, single bond, this is also single bond, 4. Now I am going to add halogen acid HX, this is partially positive, this is partially negative, right? As I said, there is a cleavage of this bond, there is a cleavage, not this one. So in the step 1, remember cleavage of the bonds. So I'll write cleavage of the bonds, right? And what will happen in the first case? This also, the positive thing comes and adds to this carbon, okay, right? And what do I get? I am going to get a formation of, okay, when this is broken, when hydrogen is added, how does it look? Let us write that first. This is added, so this carbon H, and this will become plus. Now what will happen? This X minus is here. Done. Now in the second thing, I'm going to take step 2. Now this carbocation, whatever is there, which carbocation is this? This is ethyl carbocation. So I am going to take that carbocation plus, this is also hydrogen here, and the second step, the X minus is going to attack. Now this is positive, so this goes and attacks to this carbon. So what do I get? I get X, and this is hydrogen. Right. So now this addition of HX or halogen acid to alkene, what it is do? It's going to take under, means carbocation, means the carbocation as an intermediate. This is most important. This formation of carbocation is important in this. So it occurs, the symmetrical addition occurs through which one? It occurs through carbocation intermediate. Carbocation intermediate. Remember that. So now let us start addition or taking the unsymmetrical alkene, that is your Markovnikov addition. So now I am going to show the mechanism for your Markovnikov addition. So Markovnikov addition, right? Markovnikov addition. So addition reaction. Done. So first of all, in Markovnikov addition reaction, as I said, we have what possibilities? We have two possibilities, two products formed. What are the two products formed? So basically, in Markovnikov, as I said, one major product and one minor product. That is what we have, isn't it? Right. So when major and minor product means, first of all, how does it look? We're going to take unsymmetrical alkene, CH, double bond CH2. Now I'm going to add HX to this. This is partial positive charge, this is partial negative charge. So there is a cleavage of the bond, as I said, Yes, so during the cleavage of the bond, first of all, what happens, it's going to show two different products, path 1 and path 2, right? So first there's a cleavage of the bond here. When there's a cleavage of the bond, like I said, first always this H attacks, then comes X. So in the first case we get CH3, formation of carbocation. Here also there's a cleavage of the bond. This becomes plus, and this hydrogen goes and adds here. This is CH3. Now, this is path 1, this is path 2. In the next part, what do I get? There is a cleavage of the bond. Yes, so just see. When there's a cleavage of the bond and added CH3, CH2 and CH2 plus. Now what happened here, just see, in part 1 hydrogen added to this carbon. So I got CH3 and this has become plus because it has lost the broken bond part is shaded out. In the second case, hydrogen is added to this carbon, this one, and this has broken the bond. So this has got plus, isn't it? Understood? Once again, in the first case, hydrogen is added to this carbon. So I got CH3 and this becomes a carbocation. In the second case, hydrogen adds to this carbon and this becomes the carbocation. So what type of carbocation is this? This carbocation is secondary carbocation, and this carbocation is primary carbocation. Right? Understood? Yes. So both the cases are there. Now among these two, we have already seen tertiary more stable than secondary, secondary more stable than primary. So among these two, secondary is more stable than primary. Okay, this is the order of stability. So let us write order of stability. Fine. Now I'm going to take secondary. I said this is more stable, right? The expected product CH3. I'm going to take the secondary carbocation CH3 and add this X minus. Now X minus goes and attacks the carbocation. So it will go and attack this carbocation. I'm going to get 3X and CH3. So this is the major product. Secondary carbocation is stable, so picked up. This is the first one, this is the second step. So according to this, what do we get? I said the secondary carbocation product is always a major product, so I've taken that thing. So this is your part 1 and part 2, right? So here what happens, if I have to explain the same concept, remember, if you remember this concept, the product formed also will be major. This is the simplest. The earlier one we have taken one example, isn't it? Let us take the example now and see. I said CH3, CH2, or CH double bond, CH2. Right. So to this I said, if you are going to add HX, if you are adding HX, there are two types of products as I showed you. So I get one product as CH3, CH2. If I take this, suppose if I take the first one, so let me take like this, CH2X, one product. Now in the second one, 3 CH X and CH3, two products I have got. So among these two, this is primary, this is secondary, isn't it? Right? This is primary carbon and this is secondary. So among these two, which is the major? This is the major according to the mechanism. What is this compound? Let us take this is 2. Let us assume X as bromo. Okay, so you can take it as halo. 2 halo. Sorry, it is propane. Or you can take halogen, whichever halogen, bromo, chloro. Now here this is 1 halo propane. Okay, 1 halo propane. So according to the mechanism, which is major? This is the major product. This is the minor product which we are going to get, because secondary carbocation is more stable than primary carbocation. Right. So this is your Markovnikov addition. Right. So here, suppose if I have to take the addition reaction takes place like intermediate. We have shown the formation of stable carbocation. So according to this, what is the order of reactivity of alkenes? Remember, so order of reactivity of alkenes is, when I take the so decreasing order. Now we are going to write decreasing order of reactivity of alkenes towards electrophilic addition reactions, towards electrophilic addition. Okay, so what is the electrophilic addition reaction? This one. First is R2 C double bond Cr2. Okay, this is greater than R2C double bond CHR. This is greater than R2C. We will just write there this one and then C. Greater than RCH double bond CHR. Greater than RCH double bond CH2. Greater than CH2 double bond CH2. Right, so the decreasing order. So this is the minimum one, this is the maximum one. Okay, it is decreasing, the order is decreasing due to addition reaction, towards addition reactions. So here in this case, so how is it undergoing? What type of how is the addition undergone? Let's see that. Suppose if I take the same unsymmetrical alkene, right? You can take any example, anything like any other propane we have taken, to propene we have taken, like that, substitute. Now I said this is the maximum one, this has the maximum, it shows maximum towards electrophilic addition, this is minimum I said, so I have to take this example. Now what am I going to do? I am going to take two double bond, C double bond, okay, C, this one. This is over. Now I have to take around this C double bond C, I have to take the alkyl groups, two alkyl groups. So now what am I going to do? I'm going to take this two. This is CH, this is CH3, this is CH3. Now see here, I have taken this, I have taken two alkyl groups here, right? So here one hydrogen, means just I'm trying to show, I'm relating this thing, this one here. So what is this name of this compound? This is 3-methyl, it is 3-methyl-but-1-ene, isn't it? 3-methyl, see 1, 2, 3, 3-methyl, 4-carbon-but-1-ene, right? I'm going to take this and show how is the addition product formed. Let's see that. So this is the example which I picked up. Fine. So with this example, first of all, in step 1, what happens? So to this, I'm going to add HX. I said we need to add HX, isn't it? With the HX only, it's going to just show like the product formed. So what do we get? First of all, I'm going to take CH3, CH. And HX. So X minus. Done. So here there is a cleavage of the bond. Right? When there is a cleavage of the bond, in the first step, as I said, the hydrogen, this is partial positive charge, this is partial negative charge. So there is also cleavage of this pi bond here, right? So what should I get? What condition? I said I should get the formation of a secondary carbocation formation, isn't it? Secondary carbocation formation, yes or no? Right. So first of all, when there is a cleavage, you get, or hydrogen adds here. What do I get? I'm going to get CH3. This is CH. Now the bond has broken here, so this becomes CH3. So automatically this one, this is already CH and it becomes a carbocation. Now secondary carbocation. Now what will happen here? There is 1,2 hydride shift. Very important thing this is, 1,2 hydride shift. So there is a shift of, now see here, this is hydrogen bond, there is a shift of hydrogen. When it's shifting, how does it look? You get a product, this is CH3, see here, how am I shifting? CH3, C, now this is your CH3, this hydrogen from here, this is one, sorry, this is first carbon, this is second carbon. From here, the hydrogen is going to shift here, 1,2 shift. This one, I get CH2 and this is CH3. Now I get plus. Now this is what? This is secondary carbocation. This is tertiary carbocation. Why? Because you have 3 alkyl groups. This is tertiary carbocation. Now this is over stable form. Now X halogen is going to come and attack this. This halogen comes and attacks to this carbocation and I get CH3C, CH3, CH2, CH3 and X. Okay, this is the product form. So this is how it's going to show the Marconic of addition. I have taken the definition. I have taken the mechanism, I have shown you with an example. So this is your Marconic of addition, students. Thanks for watching. Let's come and meet again with anti-Marconic of addition. We'll be learning the concept of anti-Marconic of addition in our video. So very interesting concept, students. Earlier we have seen the formation of or the stability of secondary carbocation over primary carbocation, and that's the reason we have got 2-bromopropane as an example as a major product. Now when I take anti-Marconic of addition reaction, first of all, anti-Marconic of addition, the same thing again. You have to write the definition, you need to write the example, and you need to write the mechanism. Done. So when I have to write the definition, let us write the heading definition, right? So before that, I'll take you to the example and then we will understand the example and then write the definition. For anti-Marconic of addition reaction, as usual, it's the same. We are going to again take an unsymmetrical alkene, right? So here I've taken an unsymmetrical alkene. This unsymmetrical alkene is propene. Now to this, I'm going to add halogen acid, HBr, hydrogen bromide. Now, anti-Marconic of addition reaction always occur in the presence of peroxide. Okay, so we will see what is peroxide. Here, I am going to take an organic peroxide, that is benzoyl peroxide. Benzoyl peroxide. Then, now what happens? There is this is partial positive, this is partial negative. There is a cleavage of the bond here. The negative addendum goes and adds to the carbon having more number of hydrogens in the presence of peroxide. Remember, you should speak about the negative addendum. So negative addendum adds to the carbon having more number of hydrogen. Now what do I get? I get CH2, borders broken, CH2, Br. So what is the product? This is 1-bromopropane is a product. This is a major product. Now let us write the definition. In Marconic of addition, 2-bromopropane is a major product. In Marconic of addition, so 2-bromopropane major product. In anti-Marconic of addition, 1-bromopropane is a major product. So what is the definition? How should I write? It may be noted that what do you say? When an addition or during the addition, let us write in the same way. During the addition, let us make a box for this. Addition across unsymmetrical double bond in the presence of peroxide, right? What will happen? The negative part of adding molecule attaches itself to carbon atom, negative part attaches itself to carbon atom carrying more number of hydrogens. That's it, isn't it? So negative part to more number in anti-Marconic of rule, negative part to less number in Marconic of addition. Right, this is the definition. Now let us write the mechanism for this. So fine. So when I take the anti-Marconic of addition mechanism, first important thing, I said this is going to occur in the presence of a peroxide, isn't it? What is the role of peroxide? Now we will see. So mechanism, let's write anti-Marconic of addition. Let us write the heading also. Anti-Marconic of addition reaction. Let us underline this. Fine. Now I said this occurs in the presence of peroxide. What peroxide I am going to take? Here the peroxide which I am going to take is organic peroxide, that is benzoyl peroxide. So benzoyl peroxide, what is the formula? It is, see here, peroxide, peroxide. See here in the name only you have. So you have on either side. In the center you have two oxygen or single bonds, this. So this is over. Peroxide is this group. Right? Now benzoyl. Benzene formula is what? C6H6, but benzoyl means C6H5CO. On this side also CO, C6H5. This is benzoyl peroxide. Done? Yes. Now what am I going to do? I'm going to add around, in the presence of this benzoyl peroxide, I'm going to perform the reaction. Right. So this particular thing, or this anti-Marconic of addition, is also called, because we are doing it in the presence of peroxide, this is also called peroxide effect. Peroxide effect, or this is also called as Karash effect. So you can also write it as Karash effect. K-A-R-A-S-C-H. Karash effect. So all the three names are same. Karash effect, peroxide effect, anti-Marconic of addition. That. Fine. So Karash effect applies to addition of HBr and not to the addition of HA or HCl. Remember, HBr only this is going to add. So in the first step, when I take step 1, you're going to take this benzoyl peroxide. See, I'm going to club everything. COO. O, see here, COO. COO. This oxygen is here, and I'm going to take CO6H5. Now what am I going to do? First, I'm going to show homolysis. What is homolysis? Homolysis is equal cleavage on either side. So take your pen, put your pen like this, equally, this side also equal, this side also equal, there is a cleavage. So how many are there? This is 1, this is 1. So I'm going to write 2 C6H5COO free radical. Here I'm going to get peroxide free radical. In Marconic curve, we had the formation of carbocation, secondary carbocation, and then tertiary carbocation, right? So here we are going to get through free radical. Anti-Marconic of addition occurs through free radical. In the second step, I am going to take one of the free radical and I am going to allow it to react with HBr, right? When it reacts with HBr, what happens? There is a cleavage of the bond here, H goes in, it's here. What do I get? I am going to take benzoic acid back, and now there is a release of bromine free radical, right? So this bromine free radical, right? Just see here. Sorry, I am going to take an now let me take with an unsymmetrical alkene. So unsymmetrical alkene, I am going to add this bromine free radical. That what will happen? First of all, there is a cleavage of the bond here. This goes and adds to this carbon. So what do I get? I get bromine and free radical here. One more free radical is avoided. Now in the next step, you are going to take, or you're going to add HBr to this. Plus HBr. So again, homolysis means the same step is continuing. See here, first step only again is repeated. So homolysis, there's a cleavage of the bond. Fine. So what was here? This was Br. So you get C Br H plus Br minus. Now your Br free radical is again released out. Once again, let's see. Benzoyl peroxide free radical, benzoyl the peroxide free radical. You're getting acid, benzoic acid, and bromine free radical released. This free radical goes and attacks. Then again, in the next step, what will happen? HBr attacks here, bromine free radical is released out. So steps 3 and 4, they are going to repeat again and again. Suppose if I take a unsymmetrical alkene, I'm going to take the unsymmetrical alkene and show the addition of HBr. So what am I going to take here? Let's take, I'm already adding. There are two possible ways, because in case of unsymmetrical alkene, addition of bromine free radical. So here what am I going to do? Instead of showing all the steps, I'll be taking directly to this step. This here you have this step. This here already unsymmetrical alkene. This is broken, and you're getting the product here. This step I'm directly going to take. So how does this look? Unsymmetrical alkene. I'm starting with step 3, CH3. Okay. This is CH, CH2, Br. Okay, free radical. Okay, I think I'll not go directly. Better I show you from this first step. Little bit, I think it should not confuse you students. Let's start. So here I take the unsymmetrical alkene. I'm sorry for that. Unsymmetrical alkene. I said I'm going to take the bromine free radical from there. Which step? From here. See here. I'm going to take the bromine free radical and I'm showing you. So this part is symmetrical. This part is unsymmetrical. In both the cases now bromine. So bromine free radical attacks here also. Here also bromine free radical attacks. So now what happens when I attack? So here two possibilities are there, right? First possibility, this is the first product, where what is the type of free radical here? This is secondary. Now in the second case, here I am going to get this one. This is broken and Br has added to this, so this has become the secondary free radical. Now in the second case, HCH2, here bromine is getting added here. In the first case, bromine got added to this. In the first case, bromine got added to this carbon. In the second case, bromine has got added to this carbon. So first case is this one. Second case is this one. So this is case 2. What type of radical? Now I've this one. This is primary free radical. This is this is your secondary free radical. This is primary free radical, isn't it? Now what do we know? Since secondary free radical is more stable than primary, we know secondary free radical is more stable than primary free radical. So which is a major product? Hence the reaction major product is secondary. So the reaction proceeds via secondary only. So what should I take? Secondary, I am going to take the second H2Br plus HBr, right? So just see, why did I take this? I said this is the major product, secondary free radical, this one, and this major product, because of that only I have taken that product and kept. So what do I get? See, bromine free radical is again walled out. So anti-Markovnikov of addition, it does not occur in case of HCl, HBr. Why? Though you use peroxides. Why? Because whatever chlorine free radicals are formed, they're not formed in step 1. Why? Because HCl bond is very, very strong. And if I have to say, like, to break that HCl bond, okay, suppose question is asked, I'll frame it in this case. Why? Okay, let me frame the question, then explain you. Why HCl or HBr is not added or not added to unsymmetrical alkene in anti-Markovnikov addition. So this answer I'll be giving it in the next video, students. So we will learn in the question if it is asked why HCl and HBr are not preferred. Why only HCl and HBr are not preferred? Like which is like more? If I have to say which is more preferred, that is better in the addition reactions. So let us see that answer in the next video. Thank you for watching. Students, to one more session of your hydrocarbons chapter. So today in this topic we are going to study the most important concept of alkenes, that is oxidation reactions of alkenes. So what actually is oxidation? It is nothing but addition of oxygen. But whenever you're doing some oxidation reactions, you require something called oxidizing agent. Very, very important, right? So reducing agent you require. Now oxidation of alkenes, let us see under which headings are we going to study. We are going to study the oxidation reactions under combustion reactions. Combustion is nothing but burning in the presence of oxygen, isn't it? Right. So I'll be teaching you the next type of reaction, that is controlled oxidation reactions. Okay, this is without any control. It directly burns off. The oxygen is there, right? So whenever combustion reactions are there, they're going to form carbon dioxide and water. Now in the second case, whenever I have to say take the next type of classification of oxidation is controlled oxidation reactions, with which one I said we require an oxidizing agent KMnO4. Very, very important, right? This KMnO4 again you're going to study under 3 headings. What are they? Here I'm going to take cold, dilute. Okay, I'll be teaching you cold, dilute conditions. Okay, cold means the KMnO4 whatever we are taking is cold. the KMnO4 which we are taking is dilute, because I am going to teach you again one more. What is that? Cold dilute KMnO4 is one condition. Next, opposite to cold is hot. Then dilute. Now the opposite to dilute is concentrated. Then KMnO4. So once again we are going to study under cold dilute KMnO4 conditions, and we'll be studying under hot concentrated KMnO4 solution. Right. So again, cold dilute, you have two more things which you should remember. It can be acidic condition as well as alkaline condition. Okay, it is also sometimes we also use neutral conditions, also alkaline and neutral conditions. Okay, this is how you're going to study the whole oxidation reactions of alkenes. Very important oxidation reaction. I'll explain gradually. Please try to keep noting it. Done. So once, let us start with the important thing one after the other. One more thing also is there. You have what? We have one more type of oxidation reactions. Let us write in the next page. That is ozonolysis reactions. So ozonolysis reaction. So that also we will be learning. Right. So let's come back and learn the oxidation reaction. The first type of oxidation reaction is combustion reaction. Right. So now I said combustion reaction, isn't it? So let us write the heading combustion reaction and start off. So when I have to speak about combustion reaction, what actually a combustion? Combusting means burning. Burning in the presence of oxygen. That's the most important thing. Fine. So alkenes. What is the most important thing? Alkenes have double bonded, right? Just like alkenes also undergo combustion reactions. Alkynes also undergo combustion reactions. So alkenes, whenever you're heating or when it undergoes in the presence reaction in the presence of oxygen, what are the things? Always remember, combustion products are carbon dioxide and water. Right, but important thing is, this is what is important, large amount of heat is evolved. So that's why combustion reactions are always, let us write that, combustion reactions are highly exothermic in nature. You have to mention this. With the evolution of heat only, combustion reactions are occurred. Right. So let us balance this reaction. So here this becomes 3. Okay, then this becomes 2 and this becomes 2. Okay, this is balanced, isn't it? So this is your combustion reaction which is highly exothermic. Now, after combustion reactions, the products, please remember, combustion products are carbon dioxide and water always, irrespective of the hydrocarbon taken. The next important thing, now we'll be learning the important concept, that is oxidation reactions. Oxidation reaction with dilute KMnO4. Right. So now, what is the role of KMnO4? KMnO4 is an oxidizing agent. It's going to release out nascent oxygen. So that nascent oxygen will help in oxidation process. So let us divide the page into 2 equal halves. In the first page, what is the condition? I am going to take cold and dilute KMnO4. Okay. So dilute KMnO4. Okay. Cold and dilute. Now opposite to this, cold becomes hot. Okay, right. So now we'll do first thing. First we'll not take hot, we'll do cold dilute KMnO4, and this is under acidic condition. And next one I will do the same, cold dilute KMnO4 under which condition? Under alkaline condition. Okay, right. So in the under acidic condition, if I say what am I going to take? This occurs in the presence of dilute sulfuric acid. Suppose if I say alkaline condition, this occurs in the presence of sodium carbonate, Na2CO3. Now, what is important to note here, just see. Whenever you are taking an alkene along with this, okay, you are taking alkene and you are taking under this condition KMnO4. So, what will happen? This KMnO4, what is the color of KMnO4? We know KMnO4 color is purple in color, right? Purple. So, in acidic medium, the purple color of KMnO4, it gets converted or it will turn into colorless. Remember this. So, the first important thing you have to remember, the color of KMnO4 becomes colorless in acidic medium. Now, suppose if I take an alkaline solution, that is with sodium carbonate, again the same thing here. First, we said KMnO4 is purple in color. Suppose if you are taking an alkaline solution, this purple color first becomes dark green. After that, this is going to convert into dark brown PPT. dark brown PPT. So this is how it converts. So this is the whole procedure of KMnO4 getting converted. So you need to remember, acidic medium, it's going to get converted to purple to colorless. In the alkaline medium, it converts into purple, first converts purple to dark green, from dark green to dark brown in color. Now let's see the reactions which are involved in both the cases. Yes, hope please note this, very important. Based on the color only you can say, tell your teacher, ma'am, this is an acidic condition, this is a basic condition, when the color changes. Now let's see the reactions. So let us again divide the page into 2 equal halves. I'm taking my scale and dividing the page into 2 equal halves, and let's start. Suppose first thing, if I take, now what is this condition? This is cold, this is dilute KMnO4, and what is this? This is acidic condition. Then this is cold, dilute KMnO4, this is base, this is alkaline solution, isn't it? Alkaline solution. Now let us write the reaction. First of all, what is the use? Why are we taking KMnO4? So KMnO4, now important thing to remember, whenever you have KMnO4 in the solution, I said it is used, or it is an oxidizing agent. How does it break and why are we using that? Let's see. First of all, KMnO4, whenever it is dissolved in water like this, it will break up into, just see here, KOH plus MnO2, and it's going to release nascent oxygen. First let me balance this. This is 2, this is 2, this is 2, this is 3. Yeah, right. Now this is where is important, because of the release of nascent oxygen, this KMnO4 is used, or it is used as an oxidizing agent and hence used in oxidation reactions. What is this called? This is called a nascent oxygen. This is where acts or helps in oxidation process. Done? Yes. Now the same thing here, also the same, here also the same. This is a common reaction for both. Okay, this also same. Let me take certain examples. Suppose if I take the first example, right, I'm going to take here ethene. Okay, ethene. Now what did we say? We said we are going to take the reaction of KMnO4 because it is yielding, or it is giving us nascent oxygen. Here what am I going to do? I'm going to take ethene and again water. Now what did I say? We have nascent oxygen here. In the presence of nascent, okay, we'll add nascent oxygen also, which we have got. And what are we using? We're using dilute KMnO4. So let us write dilute KMnO4. And what is the temperature KMnO4? 273 Kelvin. So then what happens? This double bond breaks here, right? This double bond breaks, and this oxygen, whatever is there, it goes and adds to this. Okay, this nascent oxygen adds around these two, means of this particular double bond. What do we get? I get a product, that is, this is water also is here, CH2, single bond CH2, this is hydrogen, isn't it? There are 2 hydrogens, 2 oxygens. Once again, 2 hydrogens, 2 oxygens. So one will add as OH to this, one more will add as OH to this. What is the name of this compound? 2 carbon, right? So this is called ethane 1,2, 1,2 diol. Okay, diol means alcohol. So this is also called as, or it is also called as ethylene glycol. Ethylene glycol. Ethylene glycol. Done? Yes. Now suppose if I have to take, or if I have to write the ionic reaction of this. Okay, let me turn the page and make an ionic reaction of this, then you will further understand. So ionic reactions you will study in grade 12, but I am writing it here. So CH2 double bond CH2, it's going to combine with water, and from this is MnO4, because KMnO4 dissociates into K plus and MnO4 minus, isn't it? MnO4 plus. Now I said acidic medium, so redox reaction chapter will teach you this, right? So an acidic medium is H plus. So when I take this, okay, when I balance this, first let me write the product. Yeah. So how many, this whole reaction, when I write, this double bond breaks here, I'm going to get CH2, single bond CH2, OH here, the same product which you have written, H plus Mn plus 2. So when I have to balance the whole reaction, this will be 5 here, this is 5 here, this is 2 water molecule, this is 2 here, and this is 6H plus. This also is 5 and this is Mn plus 2, 2. This is the ionic reaction of this. So the same thing you'll be studying in redox reaction, students. So redox reaction chapter will teach you what is the reduction reaction as well as oxidation reaction in that. And that too I have taken H plus, saying that it is an acidic medium. Fine. So remember, this is the ionic reaction of that. Now let's go back and turn take this page, because I have to teach you this. Now suppose if I have to take, if I have the same thing, I'm taking this in alkaline medium. Okay, alkaline medium. Now in alkaline medium, now again I'll write the ionic reaction, so that will be very useful for you. So for this alkaline medium, I'm going to take again CH2 double bond CH2. Now I said again KMnO4 dissociates into MnO4 minus. So water also is there. Here what will happen? This again forms products CH2. This is CH2 and your OH, and this is your OH plus MnO4 converts into MnO2 and basic medium we said, so OH minus. So I've directly written the ionic reaction. So 3 moles here, this is 2, this is 4, and this is again 3 because this is 3, and this is 2, and this is 2. Now what did I say? First of all, in the earlier thing I said, remember here, this first becomes purple to dark green to dark brown, I said. Now this is your MnO2 is your dark brown PPT. Dark brown PPT. Done. Now what will happen further? Let's see. This MnO2, that first one is formed into MnO2. Now in the second case, so what did I say? After dark brown, it's going to form no, first it forms dark green, then dark brown. Okay, I'm sorry, I have to write the reaction. So I think this will be the part B part of that. Now let me write part A. First of all, first thing what will happen in first step, CH2 double bond CH2 plus MnO4. Okay, that is from your KMnO4. So basic medium. Okay, OH minus. This forms CH2 single bond CH2. OH will add as we have seen. Now this converts into MnO4 minus 2. Okay, now this is your dark green color. Okay, this is your dark green color. So dark green color, let us balance this 2. So 2 OH. So 2 Mn. 2 OH are here, 2 OH, 2 Mn, right? So MnO4. Okay, this is also over. So I have to write this also 2 Mn. Done. So now see, come back to the reaction. So first of all, I said whenever there is alkaline medium, purple converts to dark green to dark brown. Correct? Now see here. This is from your KMnO4, and I said it is alkaline medium, so I have taken OH minus. The product is formed. First it forms dark green. From dark green, the same dark green thing here, I've taken that, and that dark green forms dark brown. So this is how is your reaction forming. So this is the reaction of cold dilute KMnO4 in acidic medium as well as alkaline medium. So this is the first step which you should remember. This is the second step which you should remember. Okay, this is the thing. So thank you for watching, students. Please note this. This will be A and this will be B. Right. Let me meet you again in the next type of reaction, that is hot concentrated KMnO4.